Okay. Let me share. Great. Okay, can everyone see this? Okay. Yeah. All right. Welcome back, everyone. We're at day 2, arguably even more exciting than day 1. Here's the link for the final schedule. Let me just tell you about a few things before we get started. As I mentioned briefly yesterday, I have a new learning site, but let me show you what it looks like. This is 200 plus videos. Maybe it'll be something like 240 or something very soon after this event, and a few more. And we have a total of, I think, 400, so we still have a bunch to put up. So, although I could be corrected on that, but this is what it looks like. You can search, and we have categories and not shown. There are tags you can search by and so on. All right, so big wealth of information. Many of the things, for example, Vaishak pointed out as highlights of different kinds of approaches in Neuro-Symbolic AI. We have them all, I think. We have representatives of all of the main ideas, and basically everything mentioned yesterday. You can find it here, different camps of ideas done. And I was pleased to observe that as people pointed out their highlights and ideas they use, that we have covered them. Okay, also toward our one of our ultimate ends, which is to kind of provide a one-stop shop for all of Neuro-Symbolic AI. And it's become more difficult to find stuff because it's, well, appearing rapidly, but in all conferences. And there are dedicated Neuro-Symbolic conferences, but there are also the regular conferences are all starting to have Neuro-Symbolic papers appear. So we have done a lot of work to curate, look across, I think we looked across 100 conferences or something, and by hand, but then Valency, we bumped into Valency, and so we're working on making it a feature on our website to use Valency to produce the latest. But you can also just directly go to Valency and use it yourself for Neuro-Symbolic search, or actually any other search. And their business model, again, is free for researchers. This is why we don't mind promoting their product. They make money from institutions, not researchers. And I want to highlight this. So part of that mission also to allow people to find stuff is BYOP. So this is where we will host ultimately, well, we have 3 levels. So one is you have your open source project, Neuro-Symbolic AI open source project. We call this the scholar level. And we'll give you a dedicated Discord channel. And remember, we have the largest Neuro-Symbolic AI community, online community, and it's on Discord. And also, we have this next level. If you start to get some traction, popularity, like 100 plus GitHub stars, then we'll also promote it, your project, give you a featured blog post. Blogs is something we We're going to start in earnest. And then the top level is the Centaur level, where if you want to host it, then in our GitHub, then all of the above perks. Plus, we'll feature you on our website, give you a section of our website. And then there are a few things we're spinning up. We will spin up a YouTube section, possible podcast, and GitHub sponsors. Okay, so this is what we mean by we'll give you some visibility. So, and the purpose for us is to make it easy for people to find Neuro-Symbolic AI open source projects, and with us serving as a hub. Okay. We want to do this for papers, also just a calendar of conferences. You'll see that soon, and so on. Okay. And if you have questions about all this, find Can on Discord, and he's the technical host of this whole meeting, and you can ask him more, or just, as always, email us info@centaurinstitute.org. Okay, now I think many of you are already joining us through one of these somehow, but connect with us on any of these others. LinkedIn, YouTube, GitHub, Discord. Okay, we have some amazing highlights. Turing Award winner Andy Bartow. We're going to have an intimate chat with him, so don't miss that. And we have a star-studded panel. All of our panels are star-studded, but this will be a particularly interesting one, I think, for general audiences. This is really about larger societal issues, and it's happening in industry right now with the current AI, you could say, for many LLMs. So check that out. We have prominent reporters, Ryan Grimm and Emily Forlini, and the ever provocative AI observer and participant, Gary Marcus. Okay, and just look at our schedule here, and we have some very exciting, to me, on the technical front, things that we've curated, and as very interesting developments, very strong developments, forming, in particular, a theoretical basis for the next generation, we feel. Okay, and that, that is a decent place to a nice segue to our next speaker. Well, we're slightly early, but maybe that doesn't hurt. I want to say, don't miss the next talk, which is Bob Kowalski. And is it okay we start a little bit early on Bob? Bob, are you ready?
Okay, I'm here.
Awesome.
Okay.
All right, let me just introduce Bob a bit. So I'm extremely pleased to have Bob. Bob, thank you so much for joining us today. This is truly an honor. For those of you who work in Neuro-Symbolic AI, you're probably using some of the popular tools are Problog and dProblog and ASP and so on. All these have roots that were created by Bob. So, and Prolog really is the root of many of these systems, and the roots of Prolog are due to Bob. So, and had incredible impact. Impact is actually not enough of a word. We wouldn't have symbolic AI and all the things that happened in symbolic AI without Bob's innovations, theoretical innovations that led to Prolog and other things. So, so truly, there is no better way to learn about logic in its pragmatic form that we use today than hearing it directly from the source, from Bob. So, Bob, with that, take it away.
Okay, well, thanks for that overwhelming introduction. I'm sure the only thing I can do for my talk is disappoint after all of that.
Mhm.
Anyway, since, as you pointed out, things go way back, in fact, in my case, back to the 1970s, I'd like to point out an early book of mine on logic for problem solving, which I believe is still worth having a look at. A more recent book on computational logic and human thinking, which will be the foundation for much of what I'll be talking about today. And I want to acknowledge my many distinguished collaborators. Alan Komrauer, who implemented the first Prolog system, Martin van Emden, who worked with me on the minimal model semantics of logic programs, Marek Saragat, who also worked with me on legal applications of logic programs and on the event calculus for reasoning about events and the way they change the state of the world. Fariba Sadri, who worked with me and Marek on the formalization of the British Nationality Act more than 40 years ago, and who has contributed greatly to much of the work I'll be talking about today. Francesca Toni, who helped develop the foundations of abductive logic programming and argumentation theory, which I'll be mentioning in my talk. Jacinto Davila, who also joined the club and has been working very closely with me and Miguel on both implementations of abductive logic programming and logical English, which is a syntactic controlled natural language sugar for logic programs such as Prolog. And last but far from least, the whole of the Prolog education group, which since its foundation or reincarnation, I should say, back in 2022, celebrating the 50-year anniversary of Prolog, has rededicated itself to teaching children how to think more logically. And logically means, more generally, how to be rational. How can a human or a machine be rational? If we ask Wikipedia, we'll come up with something like this. Rationality is the quality of being guided by reason, and it affects both acting rationally, having a good reason for what we do, and also for having rational beliefs based on strong evidence. So there's not just critical thinking, which we sometimes say is necessary in this age of AI in order to think critically about whether we're being hoodwinked by AI-generated so-called truths. But also rationality means that we behave rationally. So in my book, Computational Logic and Human Thinking, I try to bring together at the time much of what had been developed in symbolic logic-based AI and show how it could be applied not only by machines, but also by humans to enhance their own human intelligence. Today, I would call it maybe rational intelligence. First of all, we humans are animals, and as animals and all other animals, we react to changes in the environment. We observe what is happening, and we have our intuitive, instinctive responses, and these often result in thoughtless actions that have survived the evolution of our species. But if we have time to think, and if it's important enough, we can use neural predicates, let's say, to think about what it is that we're observing, and to try to understand whether there might be some underlying cause which explains what we've observed and which merits further consideration. And there could be many consequences of the alternative explanations, and we should perhaps consider which of those consequences are worth giving serious considerations to. And if there are one or two serious potential consequences, we need to decide critically what to believe. And those decisions about what to believe can trigger goals that require attention in order to maintain a harmonious relationship with the changing world. And that in turn will potentially force us to change the world in order to cope with what we've observed. So we could distinguish between goals that need to be maintained at all times and achievement goals which need to be achieved in order to maintain our higher level goals. And of course, there could be many ways to achieve our goals, and we need to consider alternatives and evaluate the alternatives by determining their various consequences, and depending upon the probability of those consequences, depending upon the utility of those consequences, we need to decide what to do. Take a very simple example. Suppose I've lost my wallet. I could, of course, just scream and shout, but maybe it's better to give it a little thought. And maybe I can reduce the explanation of the observation to two alternatives. Either I've simply misplaced my wallet, or the wallet has been stolen. I can ask myself, what are the consequences? If it's misplaced, I should go around, see if I can find it. If it's stolen, however, it could be more serious. Suppose I've decided, after considering all the possibilities, that the wallet has been stolen. And I have a maintenance goal that whenever an object is stolen, and the object contains a bank card, then I need to cancel the bank card. So that gives rise to an achievement goal, namely, cancel the bank card. And of course, I can do that in a number of different ways. Suppose I consider just two, canceling it online or canceling it by phone. Whatever I decide, I need to go ahead and do something. So what we've got is a view of a rational agent who has goals and has beliefs. The easy part of combining goals and beliefs, whether it be for a computer agent or for a human agent, is to understand how to structure and reason with beliefs. And I would argue, and will argue today, that beliefs are well understood as logic programs. And in this example, we had the belief that an object is missing if the object is stolen or the object is misplaced. I'll argue later that this is a very simple kind of logic program. We also saw that we could have a belief that says a person cancels a bank card if a person cancels online or cancels by phone. The hard part is, how do we understand the logic of goals, maintenance goals? These are not easily understood as logic programs, and I'll propose that we need to understand them as integrity constraints in abductive logic programming. But even harder, and something I'll have little time to consider in this talk, is how do we decide between the alternative ways of solving our goals, whether those goals be explaining observations or performing actions to achieve states of affairs. But if you want to delve into it more deeply, have a look at Problog, as Alex just pointed out to you a moment ago. So in this talk, I will be talking about goals and beliefs. I'll look at the way we can use logic programs, and in particular, a form of logic programming associated with both Prolog and its syntactic sugar, logical English, And I'll also be looking at how we can extend logic programs so that we can also represent goals, maintenance goals and achievement goals. As part of the inspiration for this approach that I'll be presenting, we look at production systems, which have been used by cognitive psychologists in order to understand human thinking. That, in turn, led to our development of what we call logic production systems, which is a special case of abductive logic programming. I highlight these in light blue because I'll only have a few minutes, if any, to spend on them. So let's start with the simplest case, the case of logic programs, which are horn clauses. And I'll do so in what I call logical English, in which is a syntactic sugar that makes logic programming very accessible, even to young children. So there are two components to a logic program. One is to represent the facts, which are in turn representing relationships among individuals, as for example, in the sentence, Alice likes logic. And the other is to have rules which have single conclusions, which represent a single relationship, and potentially multiple conditions, which represent a conjunction of relationship. And these we call horn clauses. They're horn clauses provided the conditions are simply positive and simply represent relationships and nothing more. And here's an example of a rule, of a belief, which has a single conclusion, Alice is happy, and multiple conditions, two conditions as it were. Alice likes the thing and the thing likes Alice, written in what we call logical English. And notice that a thing and the thing are really the English way in which we refer to variables. They stand for any individual. And the way logical English is constructed, the first time we refer to a variable in a clause or a sentence, we introduce it by the article a. Later occurrences of the same variable in the same clause are introduced by the. Variables are local to clauses, so when we say a thing in one sentence, then we don't necessarily refer to that same thing when we talk and say something else in another sentence. These are all features that we associate with Prolog and logic programs. So just to confirm that logical English is alive and kicking, Miguel and Jacinto have developed an implementation, and this is the second reincarnation of it, Logical English 2. This website will take you to it, and the code, including some of the vibe prompts used in generating some of this, can be found on the GitHub site. Notice that there are lots of examples, and many of these are oriented towards teaching young children how to think logically and rationally. Others are oriented towards legal applications. If you look at the example that I showed you a moment ago, we have on lines 9 to 11, we have a rule that says Alice is happy if Alice likes the thing and the thing likes Alice. Very similar to the rule I just showed you, but I've added another rule. Alice likes a person if the person likes logic. So what we have here is underlying also a kind of typed logic where a thing and a person are types of variables, because in natural language we don't generally have untyped variables. And in this system you can store queries, you can store scenarios, you can put scenarios and queries together and run them by pushing the button. You get an explanation, and you can also play a game, which I'll show you later. Of course, logic programs and logic in general is these days, or for many years and now many decades, are more commonly written in a symbolic syntax. And that symbolic syntax can be quite intimidating to many people. In this case, taking the same sentence, Alice likes the thing, and the thing likes Alice, therefore Alice is happy. Here we would have what we call the universal quantifier, and we'd have to have parentheses to indicate the scope of the quantifier, etc. And it can be quite confusing because you may not be sure whether it's for all x or whether it exists in x. And in fact, it turns out that for all x and existent x are logically equivalent if you just get your parentheses right. I'll say no more than that. In Prolog, we don't have quantifiers because we know that all variables in a clause are universally quantified. So let's not get confused when we have variables in the conditions which are not in the conclusion, because they can be thought of as existentially quantified with scope the conditions rather than scope the whole clause. Now, this, as a first approximation to the semantics of logic programs, we can say that a clause with variables stands for all of its ground instances, and that if you want to understand what a clause means, take its variables and replace it by any non-variable instance that you might be appropriate to your application. Now, of course, you may remember that when I showed you my first example, I didn't write a horn clause. I wrote a clause with a disjunction rather than a conjunction in the conditions. But that's just sugar syntax for having two clauses with alternative conditions. And this is another case where we often get confused about or and. So if we express this in ordinary informal natural language, we may be at a loss for words, not being sure whether we should say an object is missing and or if it's stolen or misplaced, or it can be missing if it's stolen and if it's misplaced. Whereas if we express ourselves quite carefully, we can see the relationship between those different ways of expressing ourselves. I'll be talking about how to extend this notion of logic programs, horn clause programs, to include negative conditions. And more generally, the approach I'll propose can be applied to conditions expressed in full first-order logic with even meta-level aggregation operators, but there won't be time for that. I did mention that we've done a lot of work in computational law, and I think it's fair to argue that perhaps logic programming is the dominant approach in computational law. And because law affects virtually all areas of human affairs, that suggests very strongly that logic programming and its incarnation in logical English in particular has a very wide range of practical applications. Also, it has a wide range of applications in combination with large language models in particular. And this is a very active area of research and development, which my colleagues are very busy developing. There are two approaches that we have been considering, using large language models to overcome the knowledge acquisition bottleneck to help us generate logic programs, and in particular, logical English from legal text. We've also been using vibe coding of sorts, agentic approaches to confirm that the reasoning that is performed apparently by a large language model conforms to the constraints of logic itself. I mentioned in my introduction that our work on legal applications goes back over 4 years to the implementation of a large portion of the British Nationality Act in Prolog. And that application was inspired in large part, first of all, because the act was being debated in Parliament and hadn't yet been put into effect, and there was no common law to determine how to interpret open-textured, vague concepts at the bottom of the hierarchy of rules, but also because it was so well written that it was almost written as a logic program, and in many cases, the conclusion of a sentence would come before the conditions. But when looking at it more closely, what you discover is that, in fact, the conclusion is not a simple conclusion. It actually hides other conditions. So a person shall be a British citizen not only if one of their parents is a citizen or settled in the United Kingdom at the time of their birth, but also if that person is born in the United Kingdom and that time of birth is after the act has commenced, taken legal effect. And it's curious that in ordinary natural language, or rather in well-written natural language for that matter, we often embed inside certain conditions or conclusions other conditions which tend to sometimes lead to ambiguity, although that's not the case here. Those are the three conditions that were embedded in the original English conclusion. We've done a lot of work in recent years, and some of it has been very hard going, in particular looking at swaps and derivatives and seeing how legal English compares with logical English. We've done a lot of work in the insurance domain, and we're continuing to do that work as well today. Now, one of the great things about logic programming, in addition to its enormous expressive power, and I'll show you how wide that power is in a moment, it also has an extremely simple form of reasoning, a variety of reasoning, which is easy to explain to even very young children. A logic program can be thought of as leading to a pyramid of ideas, where at the top of the pyramid we have goals, and at the bottom of the pyramid we have facts. And these facts could either be assumptions that we take in order to see where they lead, what conclusions they lead to, or they could be predicates which we can't define. They might be neural predicates which we can't put into words. And this idea of a pyramid for thinking comes about not only in the domain of logic, but it's also been proposed by people, including Barbara Minto, who are working in fields quite remote from computer science and mathematics and logic, who are interested in how to express thoughts clearly and how to regulate our thinking and problem solving to be more effective in domains such as business studies and business applications. Of course, the difference is that with logic programs, you can construct the pyramid top down or bottom up. Constructing the pyramid bottom up is what a philosopher, indeed Aristotle, might have called synthesis, putting things together to see what you can build, whereas breaking them down from the top is analysis, decomposing goals into sub-goals. And we call this either top-down reasoning or backward reasoning, and synthesis we call either bottom-up or forward reasoning. And of course, logic programs, the rules themselves, have the form of mini pyramids, and so you can string them together and construct whole pyramids. And here's an example of a little game that we developed for preschool children, so that they could learn to think logically and they could choose for themselves whether to think, as in this case, bottom up, forward to the goal, or whether they could prefer to reason top down. Okay. Now, logic programs come in a variety of forms. Prolog, for example, reasons top down, and it has the power of a Turing machine, the complete power of Turing machines, and clauses are interpreted and executed as problem-solving procedures, which reduce goals to sub-goals. Datalog, on the other hand, extends relational databases by the ability to define recursive relations. It has no composite terms of the kind that are associated with Prolog, and it typically reasons not top-down, but bottom-up. Answer set programming is more like a SAT solver. It solves constraint problems by instantiating and grounding all clauses with constants and then using a propositional logic problem solver. So I said that what characterizes Prolog compared with other approaches to logic programming is it executes clauses and rules and top-down as procedures. So for example, the clause, Alice is happy if Alice likes the thing and the thing likes Alice, could be turned into a procedure which is to show that Alice is happy, find a thing that Alice likes, and show that the thing likes Alice. This is if we execute the two conditions in the order in which they're written. But we get another procedure if we execute or try to solve the sub-goals in the opposite order. To show that Alice is happy, we can try to find a thing that likes Alice and show that Alice likes the thing. And from a problem-solving point of view, the more effective procedure might depend on the cardinality of the two sets. Does Alice like a lot of things? Do a lot of things like, if Alice is very popular, then maybe there are a lot of things that like Alice, and you shouldn't start looking for things that like Alice before you check whether or not Alice likes that thing. And this ability to solve problems in different ways using the same beliefs can be thought of as a way of understanding algorithms as having two components. A component which is declarative and which simply displays the underlying logic, and another component which is the control component, which determines the way in which you use that knowledge in order to solve problems. I mentioned that prologue clauses can include data structures such as lists, and one of the most popular ways of introducing prologue at university level in computer science courses is to show the append example, where you append two lists, and you can use the same definition either to put two known lists together or to take a list and decompose it into a variety of different lists, which when appended create the list you started with. But the success, if you like, of Prolog as a programming language has had some unfortunate side effects. Namely, it has distracted attention from the fact that Prolog is very suitable for teaching very young children, and that teaching recursion with lists is one of the worst ways to introduce children to logical thinking. However, another feature of Prolog, which is often overlooked, which is essential for teaching young children, which would be considered extremely complicated and could only be introduced possibly at a higher level in a computer science course or a logic course, is that it's homo-iconic. That is to say, it can include sentences that talk about themselves. And when people sometimes say logic programs are first order or Prolog is first order, they've missed the fact that Prolog is homo-iconic. And I'll give you an example. So one of the examples we've developed for our children's stories is a variation of the Alice in Wonderland tea party, where Alice attends the tea party, the dormouse attends the tea party, but only Alice is invited to the tea party. We have a rule that says it is forbidden that a creature attends the tea party if it's not the case that the creature is invited to the tea party. We have another rule that says a creature is punished if the creature attends the tea party, and it's forbidden that the creature attends the tea party. Do you see these two conditions? The first condition is a simple condition. The creature attends the party, and we have two such creatures, Alice and the dormouse. And the second one, however, talks about or is a propositional attitude concerning attendance at the tea party. If a person attends, in particular, it allows us to predicate that it is forbidden that a creature attends the tea party. And if indeed it is the case that a person or creature does attend the tea party, but is forbidden to do so, then the creature is punished. And this is an example of homo-iconicity, which can be thought of either in higher order or meta-level terms, but is certainly not first order. So I'm maybe halfway through my talk, but so I better be careful how I go from here. I want to say a few words about the intuitive semantics, which is very natural, and because semantics is often considered hard, I won't spend a lot of time on it. The main thing to say is that the bottom-up way of thinking about synthesizing conclusions from assumptions, gives us a very intuitive semantics for Hornclaw's logic programs, which can be extended to logic programs with negation, and even to logic programs with homo-iconic self-reference, if you like. A program, however, for this purpose, to get a very intuitive variant of the semantics, what we want to do is restrict ourselves to logic programs, all of whose variables in the conclusion occur also in the condition. So the conclusion never introduces new variables, new universally quantified variables that are not already constrained by the conditions. And the set of all facts that you can derive bottom up, starting with range-restricted facts, which have no variables because there are no conditions that could contain variables. So starting from facts without variables and using these ground facts to reason forwards, we generate ground conclusions. And in a pyramid fashion, we derive more and more ground facts. And in the end, there is only one set of facts that we can derive, and that in turn turns out to be the minimal model according to classical logic. In classical logic, there could be other models, but this is the smallest model, which makes the least number of facts true. And this in turn is maybe what could be thought of as the canonical model. Take this little program here. Alice likes logic. Alice is happy if Alice likes the thing and the thing likes Alice. That's range restricted because there's no variable in the conclusion that's not in the conditions. Alice likes X if X likes logic. That's range restricted because the variable X in the conclusion is also in the conditions. And it has a very simple canonical model. Starting from the ground fact that Alice likes logic, you can derive that Alice likes Alice using the second rule. And from the fact that Alice likes Alice and Alice likes Alice, you can derive that Alice is happy. So there's only one canonical model. Interestingly, in this canonical model, it is not the case that logic likes Alice is true. You could say it's a consequence of the logic program. It's a property of the logic program that in the canonical minimal model, it is the case that logic does not like Alice, which could be written in a variety of different ways. And this is a form of what we call sometimes the closed world assumption or the database assumption. It's the same assumption made in relational databases that a negative statement is true if the positive statement is not true. And we can extend this to so-called stratified logic programs with negative conditions. Again, we get a very simple intuitive understanding. Here, Alice likes logic, and Alice is sad if Alice likes a thing, and it's not the case that the thing likes Alice. And it has the canonical model, Alice likes logic, which is the ground fact we start with, and it has only a simple single conclusion that Alice is sad. And this is stratified because the predicate Y is sad is at a higher stratum than the predicate Y likes X. So what we do is we evaluate the truth of predicates at the lower level, lower strata, before we determine the truth of predicates at the higher level. And this gives us a very natural, very simple way, a very intuitive way of understanding the negative conditions. It also gives us a way of giving us semantics to homo-iconicity, the same example we saw before, and the canonical model is defined in exactly the same way as we did for horn clauses. You simply reason bottom up, match the facts you've already derived against the conditions of rules, derive conclusions, and you're finished. You can see this example and many others on that Logical English page I pointed you to. So, and what runs the programs underneath are just plain Prolog. So Prolog is not first order. Let's talk a little about abductive logic programs. I've not left a lot of time for that, but let's see where we can get. So the first thing I want to say is that we have a competitor, or an apparent competitor in the case of production systems. Production systems which don't have a logical semantics and don't pretend to have a semantics and don't claim to have a logical semantics. So here's a simple example of a production system where we might have a working declarative memory, which is like a couple of facts: you're hungry and you're sleepy. And then we have these imperative rules, or conditional imperatives. If you're hungry, then eat. So that's an imperative, a command. If you're sleepy, then sleep. So normally in production systems, these are characterized not as declarative sentences, but as procedures for that matter. And we would have candidate actions: eating and sleeping. But as you can imagine, it's not possible for most of us to eat and sleep at the same time, and therefore production systems have an approach called conflict resolution, which is carried out and which totally destroys any logic that you might have initially associated with the production rules. But abductive logic programming, which I now will spend a few minutes on, provides us with a logical way of thinking about production systems. Beliefs such as "you are hungry" and "you are sleepy" are statements that can be that take place, that hold true at times, and so we have to associate them, let's say, with a time zero. Production rules are maintenance goals, which need to be maintained true. If at any time you're hungry, then you eat from some time, and this is what makes the logic possible. The variable anytime in the conditions is followed by another variable, which I haven't spelled out, sometime in the conclusion. So there's a combination of universal and existential quantifiers. If you're sleepy at any time, then you sleep from some time. So you can satisfy these two goals, these two integrity constraints, simply by choosing different times at which you eat and sleep. But you mustn't eat and sleep at the same time. For all times t, it is not the case that you eat from t and sleep from t. And you can make these goals true. You can make both the active integrity constraint, the maintenance goal, and the prohibition goal true by performing actions, by having candidates actions, which in abductive logic programming are called abducibles or assumptions, and you make them true in order to make your goals true. So abductive logic programming is a combination of logic programs, integrity constraints, which constrain the abducible assumptions you can make. And another way of looking at it is that abductive logic programs combine beliefs, goals, and candidate assumptions. In theory, a goal can be any sentence of first-order logic, but in practice, the most useful goals are maintenance goals and prohibition goals. In the general case, maintenance goals are if-then rules, an antecedent, and a consequent. All variables are universally quantified, just the same as with logic programming, except, and this is a very important exception, all variables in the consequent that are not in the antecedent are existentially quantified. On the other hand, prohibition goals have all of their variables universally quantified. Oops, going in the wrong direction. There's a bottom-up semantics for ALP, and there's a top-down implementation of ALP. I won't bore you by going into the details, but in the bottom-up semantics, we simply make assumptions, reason bottom-up, and see whether or not they satisfy our goals. And that's the reason why the goals, in theory, can be any sentence of first-order logic. But this kind of reasoning is totally unfeasible. Dreaming up assumptions out of the blue doesn't work. As Sherlock Holmes said, in solving a problem of this kind, the great thing is to be able to reason backwards. It's very useful and very easy, but most people don't do it. In everyday life, they tend to reason forwards, and so backward reasoning tends to be neglected. And this is our experience too. We need to teach children, we need to teach computers, we need to teach adults how to combine forward and backward reasoning. There are several classic applications of abductions, namely to explain observations, and I won't go into the detail, time is short. Another application, which is not very commonly known, is to reason backwards to achieve goals. If you want Alice to like you, and you believe that Alice likes a person if the person looks cool, and that a person looks cool if the person wears sunglasses, then one way you can get Alice to like you is to wear sunglasses. And if your belief is true, then your conclusion will be true. But maybe Alice isn't as superficial as all of that. Maybe Alice likes a person if the person likes logic. Well, that would give you another alternative way of solving your goal. You simply read my book, and Alice, maybe, if you're lucky, will like you. So in general, there can be several ways of solving a goal using abduction. In the case of explaining observations, there could be several hypotheses. In the case of planning how to solve a goal, there could be several plans of actions. Different solutions can have different probabilities and utilities. Right. So I've jumped ahead of myself. Different solutions can have different probabilities, and I recommend the Problog online website for some nice examples of how you can put them all together. Right. I've so many nice examples that children love, but we don't have time for them, I'm afraid. I'll say a couple of words about negation. Negation is very controversial in logic programming. And negation is failure in particular. The way we implement negation in Prolog is controversial, and answer set programming has a different approach. Data log stratified negation is quite compatible with the negation as failure approach. But it also has an assumption-based argumentation, which is very, very helpful in practice because it generalizes negation as failure. An assumption in abductive logic programming can be deemed to be admissible if all attacks against the assumption fail. So, for example, if you're making an argument, the argument is admissible if you base it on assumptions and all counter arguments fail. And to attack an argument, what you do is you try to undermine it by proving the contrary of one of its assumptions. So negation as failure is a special case. If you want to undermine the assumption that not P, you prove the contrary, namely P. If you want to undermine the assumption that a person is innocent, you prove that they are guilty. If you want to undermine the assumption that a person is good, you prove they're bad. Abductive logic programming and its implementation in the form of logic-based production systems combines forward and backward reasoning. And I won't talk about it in the abstract. I'll show you an example very quickly. So here's a map coloring example in LPS, logic production systems. It has an abducible, an assumption that you can paint a country a color. It has some facts, which are the logic programming belief component of the application, the map coloring application. And it has some goals or integrity constraints which need to be made true. The first one is an active integrity constraint, an active goal. For every country, you must find a color that's existentially quantified, remember, and paint that country that color. But we also have a prohibition that if two countries, X and Y, are adjacent, then they must not be painted the same color. And if you look at this little collection of 4 countries, when you run this in LPS, you get this example. And just to show I'm not telling fibs, you can see it running in full time in this little video here. Now, you didn't get the same picture I showed you because in this example, I've initialized, I've had an initial event in which Oz was painted red. If I remove that, Oz will be painted yellow. Okay, to wrap up, computational logic for rational intelligence. So we have our own instinctive responses to changes in the world. But if what we observe can be put into words with the aid of neural predicates, shall we say, and if it warrants it, we can try to explain what we've observed. And we can compare the consequences of the alternative explanations, and we can decide what to believe critically. We can see whether that affects our goals, whether we need to achieve some future state of affairs. We can look at alternative ways of doing so. We can compare the consequences of the alternatives and decide which consequences have the highest probability combination of probability and utility. So I conclude, logical thinking underpins rational thinking. Logic programming and abductive logic programming provide simple yet powerful foundations for logical thinking, and they can both be used by humans and by machines to improve their own rational intelligence. And so I thank you, and I apologize for taking so much of your valuable time.
No, this is wonderful. Thanks so much, Bob. All right, we have time for a couple questions. One is, can you clarify what is meant by logical semantics?
Logical semantics. Okay, so in the case of maintenance goals, the great thing about interpreting production rules as logical implications is that there's more than one way to make them true. If antecedent and consequent can be made true in the obvious way by making the consequent true when the antecedent becomes true. But you can also make the maintenance goal true by making the antecedent false. So you make the antecedent false by preventing the antecedent from becoming true if the conclusion or if the consequent would force too much effort. And also going back to the truth table, you could make an implication if antecedent then consequent true by making the consequent true no matter whether or not the antecedent does become true. So you can proactively make a production rule true by performing an action to anticipate the possibility of the condition being triggered. And that's one of the virtues of having a logical view as opposed to a purely operational procedural understanding of goals in particular.
All right, and another question. Is there any formal proving that the computational logic for rational intelligence can generalize, and we ask for clarification, by generalize, the asker meant the framework, that the framework can handle a general case? And if so, what are the assumptions?
So first of all, the framework I've proposed, I suppose, is a logical variant of the cognitive model provided by production systems. And that cognitive model is intended to be a general purpose model of how humans think. So to the extent that it can cover what the conventional cognitive models cover, then it is perfectly general. There are, now I can say this though, there is no implementation that I know of, no computer implementation that incorporates all of these components. So from that point of view, LPS in particular is purely reactive. So it doesn't have these other, it doesn't exploit these other features advantages of the logical understanding of maintenance goals in particular.
All right. Well, I love that you showed that, and I think that's really important. What Bob described about giving a logical basis to production rules for a couple reasons. One is we're in the age now where everyone's trying to make LLMs work as agents. And I think many of us in neurosymbolic land think, well, if you're going to do agents, you should really be more careful about it and maybe consider some of our ideas here. And I think you just provided a very, very important linchpin possibly for that. And the second is we're going to actually see Bob again shortly in a panel, and John Laird, creator of SOAR, will be there. And so this is highly relevant to SOAR. So, all right. Well, thank you so much, Bob.
Thank you.
We'll see you shortly. That was amazing.
Thank you.
Okay. Next up, we have Emanuele. Thanks.
Hi.
Emanuele. So he's going to tell us about something that's actually, you could say, unique and very important for neurosymbolic. This problem of reasoning shortcuts, and he'll tell you much more, but a way to kind of understand why you really need to think about this is you can think of neurosymbolic, or one canonical way to think of neurosymbolic is system 1, system 2. You have this fast, quick and dirty pattern recognition, system 1, and you have the slow and careful and correct, system 2. But you could sort of, get things wrong in system 1, and and sort of, so because you have these two ways of going about things, you can screw things up. This is my short intro. So Emanuele, why don't you tell us all about this for real?
Sure. Okay. So, can you hear me well?
Yep.
Okay, great. Thank you, Alex, for the introduction. Thank you for the invitation. This is meant to be some kind of intro to reasoning shortcuts, which is an issue that I've been studying for some years. And I'm happy to share that we have a published review on this matter, recently published on a journal of AI research, with some of other collaborators which have been contributing a lot to the ideas behind. So very thankful to Samuele, who is my colleague, Emil van Krieken, who is a great expert in Neuro-Symbolic AI, my supervisors, Andrea Passerini and Stefano Teso, and also Antonio Vergari, with whom we started this idea of reasoning shortcuts. So the point is related to symbol grounding in Neuro-Symbolic AI. And this is an outline of what I will be discussing. So I'll try not to be very technical. It's very high level. All information, you can find it in the published article. So there are 5 items. To go from 0 to know a little bit of symbol grounding, and then see what happens with reasoning shortcuts. Then I will have some time, hopefully, to discuss how we can mitigate reasoning shortcuts, what are open problems. Yeah, and if other time, I will detail some extras. Okay, so this idea of symbol grounding is actually quite old idea. Comes from a paper by Harned in the 1990s. And the way I understand it is essentially the problem when we have an AI system which operates on a vocabulary of symbols with some rules, the problem is how does the model gets to associate a meaning to the variable it operates on, so to the symbols it operates on. And we can think that this system is given this knowledge from some experts, starts to interact with the word, to learn from it. So as we do with training neural networks, and has to determine by completing his tasks the meaning of different symbols he has given. So in this very simple drawing, some symbols can be related to objects in the world, and by interacting with it, the system has to figure out what is meant by an apple and dog, and so on and so forth. And this is one of what we could consider two of the prominent problems in Neuro-Symbolic AI. So there is a lot of focus in bridging the gap between continuous and discrete computation, which is how we can integrate neural processing with logical inference, with logical reasoning. And this is not much the focus of today. It's more about how we get latent symbol identification. So how the system, once we decide the integration of the Neuro-Symbolic model, identifies the latent symbols. And there are actually two cases where this can appear. So you may have some discrete optimization model, so something that's used for pathfinding and planning, and you may want to use it with some new instances. So you are given some satellite images, and you want to map these raw inputs to the symbols of your pathfinding solver and find the best path to move from one point to another. So this is a way of reusing existing softwares on top of neural networks. So neural networks are meant to extract useful information for these systems. And another case study is the one where we want to enforce logical constraints in neural network so that to increase trustworthiness. So, for example, you may think in autonomous driving, a scenario where we know the traffic rules, we know what an autonomous driving car should respect when planning its actions, direction, and we may want to enforce this. So this is not an ideal case. It's actually possible with this radar dataset where there are more than 200 annotated requirements with labels, symbols involving pedestrians on the streets, cars, and some other objects. So for now, we focus on this setting, just for reference, and we look at how these neuro-symbolic systems can be designed. So as I anticipated before, we have one part that is the low-level processing from the image, which is typically accomplished with the neural networks. And so here we have a faster CNN that detects some objects in the image and predicts a series of symbols if present or not. So just to be clear with what has been introduced before, so in the previous talk, there were also mentioned neural predicates. So you can think of this also as neural predicates. I will also call them concepts. I know that logicians do not like this terminology, but not to be confused to concepts which may appear in logic. So here concepts are the equivalent of neural predicates that the model defines. And upon extracting these symbols, the model uses the prior knowledge to combine this information and give you a prediction. And there are different ways to achieve this in practice. So you may want to use the prologue, which is an evolution of prologue, of what we saw before, semantic loss, and also logic tensor networks. So to be a little bit more precise, how can we formalize this? So we said that we have the first part, which is the neural extraction of the concepts. We have this module F, the neural network, that gives you the values of the concepts in the image. And from this, you use the logical reasoning, so with a function that we will call beta, to predict what is the final action of the car. And when you combine this, you get a probabilistic model that determines the conditional probability on labels, on final actions, given the input and the knowledge. So thing is that beta is often given while you want to learn F from the data you have. And this is achieved by training with maximum log likelihood to maximize the conditional probability on labels given the input. Okay, so given this setting that we only have supervision on the pairs, so on the input and the final action, we may encounter some problems. So imagine the setting that we had before. We have the same knowledge, and we let the neural network decide what is inside the image. So in the first image on the left, you see the autonomous car predicting there is a red light and give you the correct prediction to stop. What happens on the right is while you correctly detect a green light, the car mistakes the pedestrian for a red light. And this actually does not change the final prediction. So the prediction is still to stop and is correct, but here we have the problem. So this is a reasoning shortcut, and we are getting perfect accuracy on these predictions, but we are mistaking pedestrian for red lights. And so we are mistaking, in a sense, the meaning, the model is mistaking the meaning associated to red lights. So why this matters? Well, if you think to, let's say, add new rules to your system, so you want to reuse your neural network but update the rules, this is no longer possible and can cause a drop in the model performance. So if you have a rule that reads, if there's an emergency and there are no pedestrians, the car can proceed, of course, mistaking pedestrian for red lights can have dire consequences. Okay, so some reasons more why you should care about reasoning shortcuts. First of all, once we encounter a reasoning shortcut, a system learns a reasoning shortcut, the associated concepts that is predicting lose their intended meaning. So we can say that they are not reliable, that they do not mean what they are supposed to, and in a sense, we can say they have a twisted semantics. So this, as I motivated before, also implies that it's not always possible to reuse the concepts. So these concepts that don't have the intended meaning do not transfer, meaning that you may not be able to be correct in prediction once you update your rules. And finally, what can happen is that even if you don't plan any transfer, you can have a drop in prediction. So you may find that a system with a reasoning shortcut fails to support compositional generalization. So by observing a new combination of concepts that have been found in the past, the model is no longer able to predict the correct label from those. One thing that I want to remark is that reasoning shortcuts by no means undermine inference of the neuro-symbolic model, meaning that your neuro-symbolic model will still work, will still operate as engineered, but you may find cases where prediction do not match the expectations. And another thing is, which is something curious, and we don't have many, let's say, arguments, and this is an open problem, is that reasoning shortcuts may also affect training dynamics. So in a setting where the system is prone to learning reasoning shortcuts that can be different from one another, you may find problem in training the model at all. But okay, for this, we have only some empirical evidence, not much grounding on theory. Okay, so how can we define at this point a reasoning shortcut? So the kind of intuition we have on this problem is that for defining what is correct and wrong, we first have to think about what are our expectations, and so what is the ground truth neuro-symbolic model we wish to learn. So this is here on the left, a model that we may likely want to obtain. So with a ground truth concept extraction phase with the F star that gives the correct attribution to the concepts that the model can predict. And on the right, we have our learn model. So what we propose to look at to give a definition of reasoning shortcut is how the learn model essentially translates what are the ground truth concepts G into its predicted concept C. So this is what we call these alphas, and essentially embodies is a function that tells you once you give the model these ground truth concepts, this is what is going to give you in return. So the best case is if this alpha is the identity, then we can say that the model has acquired intended semantics, meaning that concepts are grounded correctly and they are predicted as the ground truth. So we may find a system that is aligned with the concepts that we will predict from the inputs. On the other hand, if we have alpha that is different from the identity, but still gives you concepts that give you correct predictions, then we are facing a reasoning shortcut. And well, I'm not going to the details of the formal definition, but this is essentially the intuition behind it. So let me explain this also in a very simple example. So we have, this is an MNIST addition. The task is to do the summation of two digits. So the model is given as an input, each digit knows the rules of the sum and has to predict the values of the digits so that to match the sums here. So this is, if you look closely, this is a case where we have 3 variables, but only 2 equations. So this is in algebra system that is not undetermined. And so there is not a unique solution. So what you can find in practice is something like this, that, well, you predict the 0 as 0, 1 as 1, and so on and so forth. But you can also collapse the prediction of the 0 and the 2 to the 1, and the 1 to the 0, and still get correct summations. And actually, this is often the case when you go in practice. So there is some evidence that learning this kind of solution is preferred to the intended solution. Okay, so at this point, you may wonder, okay, what are the driving factors behind the reasoning shortcuts? So if you have a problem with some prior knowledge, you want to train the model, when should you expect to observe reasoning shortcuts? What is causing their emergence? And there are actually 4 main reasons. The first one is related to the prior knowledge we're giving to the system. So in a sense, the kind of function we are engineering from the labels to the concepts is not explicit enough to carry enough information to give you the intended solution, so to give you correct concepts when training. So this happens when we may have many concepts in our systems, so many units, but only few labels. In this case, the signal is not explicit enough, is not informative enough to ground uniquely the concepts. Then there is also another element which is quite known in the case of, I would say, vanilla shortcuts, that is data can present a selection bias. So as we saw before, by only having two equations, we do not have enough information to tell the correct digits for the inputs. And now another factor is also what we are optimizing for. So in the examples I've shown you before, typically this is classification. So this objective may not be informative enough. So even given the prior knowledge, this is not sufficient to distinguish all the concepts. And the final thing is the architecture of the neural component plays a role. So if you have a model that is too flexible or is biased by construction, you may find different results. So you may find different, also in some cases, different reasoning shortcuts. And just to clarify, these 4 root causes are actually well specified by the when you characterize reasoning shortcuts. So it is possible to describe all reasoning shortcuts given the problem. So to tell, based on the extremes of the problem, if you have reasoning shortcuts or not. And you can see from this that these are the only 4 root causes causing an emergence of reasoning shortcuts. And it is also possible to give an estimate of how many reasoning shortcuts are present in the problem, and in return, what the theory tells you is also that if you can zero this number of reasoning shortcut, it is sufficient to learn right concepts all the time. Okay, so where you can find these reasoning shortcuts? Well, there may be everywhere in neuro-symbolic problems, but we have collected some data sets where we specifically engineered them to present reasoning shortcuts. So we have this benchmark, which is called the errors bench, and we have a different series of tasks. So these differ on whether they come with a generator, whether they support out of distribution generalization, so out of distribution data to check for generalization, and also continual learning. There are some other properties related to the complexity of the input, complexity of the knowledge, and whether the knowledge is ambiguous by definition. So these tasks involve arithmetic, logic, and high stakes. To give a very simple example, Kandinsky logic here is essentially a problem where, given these distinct input images, the AI system has to recognize whether they present or not the same pattern. So by same pattern here, I mean that, for example, we observe 2 shapes that are in common. One is different and different colors, and the same here. So this is true. And here there are a variety of reasoning shortcuts. So some of those also involve exchanging shapes with colors. So mistaking the semantics of what is a color with a shape. There are also some other tasks. So these are what we call the high-stakes tasks. So one is BDD-OIA, which I will detail shortly, and SDD-OIA, which is a 3D generated version of BDD-OIA where you have control on the generation. So this is more flexible if you want to have more data, shape out of distribution scenarios, and change the support of what are your images. So very relevant to what was the initial motivation is this BDD-OIA, which was one of the first. So maybe I can move this. Sorry. No. Which is one of the first data sets we tried at the beginning when we started studying this problem. And you have dashcam images with a lot of elements, so presence of pedestrian cars. And the target is to predict some possible actions. So among this, whether the car can move forward or has to stop, whether it can turn left or right, and the elements in the images are essentially collapsed to a series of concepts that include the presence of red lights, of obstacles, and all this comes with annotation. So what happens in this case when you give when you design the rules for autonomous driving is something actually very collapsed. So if you make use of a model that is trained without any supervision on the concepts, what happens is that the confusion matrices, so this thing that you see here, for the concepts appear quite collapsed to only few combinations. So these are concepts relative to forward action, to stop action, left and right. And what can be seen here is that with only these few combinations, the model is predicting actually correct action. So it has very high generalization in the test set. So this is also mirrored in when we go to study SDD-OIA, but here I want to also highlight another aspect, which is, well, for neuro-symbolic models, while you have high prediction in label, final label classification, you find low accuracy on the concepts. And this is something that we know, so this is because of reasoning shortcuts, but they also seem to affect models that are not neuro-symbolic at all. So when you study neural networks or foundation models, you can also say, okay, let's use some pre-trained modules to make the predictions and just learn like the projection had. What happens is something similar, but here, since there is no specific bottleneck for the concepts, what you can do is to check the accuracy on concepts by probing on the intermediate activation of the network. In any case, what we found is that for both neural networks, black box neural networks and CLIP, we couldn't spot these concepts specifically in the network. So I can be more precise on this if there are questions later. Okay. So given that we have this issue, it's good to know that there are different ways, different possible ways to mitigate it. And let me go very briefly here. The idea is to design some additional objectives that we use when we train our models that act on the specific root causes that increase reasoning shortcuts. So, as I said before, we have 4 different root causes, and we can target them by specific, by adding specific penalties to the model. So, for example, if you may heard of multitasking, this is something that acts, in the case of neurosymbolic models, at the level of the knowledge. So what happens is you pass more signal to the system, and you have more information to ground the concepts correctly. You can also think as passing concept supervision. This is ideal, but comes at the cost of collecting this additional annotation. And then there are also other possible ways to achieve that by acting on the objective and on architecture by of the model. So what happens in MNIST addition, the example we saw before, when we also make use of multiplication. So we ask the system to predict correct summation and correct multiplication. So we still have that the intelligent solution works, and what we had before no longer works. So you would not be able to predict correct multiplications by resorting to this reasoning shortcut of before. So in this case, what you find is confusion matrices for the concepts that are aligned to the diagonal. And there are a bunch of different mitigations that have been tried. So those that work effectively are those that comes with the extra annotation, and they essentially target both the learning objective, but also the dataset. So this comes with the cost of creating new rules in one case and collecting annotation in the other. There are a lot of other strategies that have been tried, but for those of this that comes without annotation, giving guarantees of removing reasoning shortcut is not possible in all cases. And okay, maybe I just said this. One question is, okay, we have strategy that we know works for sure, which is providing supervision of concepts or creating multiple tasks. But how can we lessen the cost, the annotation cost for this strategy? And our idea is to propose to make models aware of reasoning shortcuts. So to create neurosymbolic systems that can tell you whether some concepts can have twisted semantics. And what the problem that you may find in practice is that when you train a model like a deep problem to solve the task, it tends to be overconfident on the concepts, even if these are wrong. So in this image here, what we have is that the model is predicting with high certainty that red lights are red lights, but also pedestrians are red lights. Still works for prediction, but this is wrong. What we would like to have is a system that instead tells us, well, I'm not very sure what is meant by pedestrian or red light. And so here, the model can tell us whether it is unsure. So based on the picture here, the model is giving high entropy to prediction of pedestrian and red lights. And this is something that is possible to implement. So maybe let me skip this, by essentially creating an ensembles of different neurosymbolic models that all of them solve the task, make good predictions, but they're diverse in the sense that they think different stories about the concepts. So one model may think that pedestrian is present on the image, whereas another model tells you, well, there is a red light in the image. And the idea is to create this ensemble by first maximizing the log likelihood, so the objective, the final prediction objective, but also increasing the KL divergence between the new member of the ensemble and what is the average distribution of the ensemble. So to be as different as possible, and also encourage some entropy maximization here that forces the model to be as uncertain as possible on the concepts. What happens in the end is that if you have enough members in the ensemble that think different story, by combining all this information, you can find what concepts are predicted the same way, but all the models, and what concepts are not. So you have the information of what concepts you have this uncertainty. So one application is that if you use this uncertainty compared to strategies that do not include it, you can find faster and better annotation to steer the model toward learning the intended solution. Okay, so let me go to the conclusions of this. And so I told you a story about neuro-symbolic models, a specific class of neuro-symbolic models that have problems with the symbol grounding. So this symbol grounding is not unique. And we have a consistent picture of this for these neuro-symbolic predictors. So you predict the concepts and then you predict the labels. But it is a bit unknown what happens outside these models. So in a sense, we expect that this may also exist in other neuro-symbolic architectures. So for example, subnet, where you try to use satisfiability solvers in the model. There is also another thing that is, in some cases, you may not have the prior knowledge. So you still want a model that learns some concepts from the data and learns also how to combine this information. So learns both the concept extraction and the knowledge. This is the setting of concept-based models. And in this setting, what happens is that you find even more reasoning shortcut. You find something more complex that we termed joint reasoning shortcuts. And for what we have observed, this is a setting where previous mitigation strategy that works for neuro-symbolic models are not as effective in this case. So there is also an extension to neuro-symbolic reinforcement learning. And this is a case where essentially you design an agent to have some prior knowledge about possible actions, but can misinterpret concepts, so can pick reasoning shortcuts and exchanging the meaning of gem or pick X while still completing the task. And finally, since we're all interested in LLMs, we have some intuition that reasoning shortcuts may also appear in LLMs. For sure, in black box neural networks, in LLMs is more difficult task to show. And this evidence is scattered and there is no characterization. So this, I would say, is an open problem. Okay, so for the sake of the time, I will skip this intuition on concept-based models. As I said before, this is a setting where we also have a good intuition of what happens. We have more reasoning shortcuts, and the number compared between the standard neuro-symbolic problem and the problem when we also learn the knowledge tells us that there is a more than exponential increase of number of joint reasoning shortcuts as we increase the complexity of the problem. So while reasoning shortcuts are still many and difficult to deal in some cases, joint reasoning shortcuts, so the case when you also learn the prior knowledge, are even more complicated. Okay, so about neural networks and LLMs, one problem is we can study these systems, but it is difficult to ground a theory since we do not have the same exact terms. So, as I showed you before, we have a concept bottlenecks for prediction of the concepts, and we have our knowledge operating on them. In the neural networks, this is typically implicit, so it is not clear both where they are and also how they are used. But as I showed you before from some experiments on RSBench, we observe that black box neural networks and also CLIP are prone to not learning the concepts. And in a sense, this is not surprising for black box neural networks, as these models are less constrained than neuro-symbolic predictors. So you can think as neuro-symbolic predictors or neuro-symbolic models as more constrained versions of neural networks. And in this case, if these models, more constrained, have problems in identifying the right concepts, well, it is also the case that black box neural networks will share the same problem. And yeah, it is not clear what happens at scale. If something is working and makes reasoning shortcuts disappear, and I can say that there is some conflicting evidence. So on one hand, we have there is a lot in the literature about the linear representation hypothesis, so concepts that are encoded in a linear manner in the representations. There is emergent similarity between representation of large-scale models, but there is also evidence of symbol hallucinations. So if you try to ask a model to ground the symbols, you don't find correct values, and also very well-known lack of reasoning, especially for long chains of reasoning. Yeah, and mainly reasoning shortcuts have been studied in the setting of LLMs as symbol hallucinations and or connected to multi-hop reasoning. So what happens when you have some deductions in your data that depends on multiple steps? Okay, so let me wrap up. So what is symbol grounding in neuro-symbolic AI is essentially the problem of assigning correct semantics to the latent concepts, and reasoning shortcuts arise when this is not possible. So what is a reasoning shortcut is essentially a valid but alternative concept mapping that gives you optimal likelihood, but this is not intended. And you can mitigate reasoning shortcuts, but you typically require supervised strategies or make use of awareness to know where to act. Unsupervised strategies are limited, so not in all cases you can resolve this problem. And yeah, finally, if you want to know more and also expand this, you may benefit from RSBench also to define new tasks based on this idea of first defining a set of concepts and then aggregating them with some prior knowledge. So thank you very much for your attention.
Excellent job. Thanks so much, Emanuele. I think this is really, really important for our community, Neuro-Symbolic AI. So I hope everyone learns about this and look more to Emanuele and his colleagues for the great work they're doing on this. Let's see some questions. What would you say is the intersection of reasoning shortcuts and confounders? Datasets such as CONCON, which test a model's susceptibility to confounders in a task, seem adjacent to RSBench.
So you said sortability?
Datasets such as CONCON, which test a model's susceptibility to confounders in a task, seem adjacent to RS bench.
Okay, so there is a relation, of course, with shortcut benchmarks, but I must be clear that the kind of shortcuts we observe in these models are not only dependent on the inputs, so on the presence of confounders. So in many cases, in shortcut learning, you may have some watermarks or in general these confounders that does not give you enough information to tell you how you should classify some instances. In the case of reasoning shortcuts, the problem arises even if you have a complete data set without these confoundings, but your knowledge, the information you're using to learn the concepts is not sufficient. So, in a sense, there can be also biases in or confounding in the neuro-symbolic setting that makes arise more reasoning shortcuts, but these are not the only cause for them.
Okay. Formally, we have the break now, but we have a few. We can dig into the break a little bit to entertain a few more questions. There's a simpler analog in classical machine learning where models train on features that don't generalize, that accidentally correlate with the objective in the training set. For example, they could be due to leakage into the training data or coincidental correlations that don't generalize. Are there projections of the reasoning shortcut detection and mitigation strategies for these classical ML cases?
Okay, so let me try to answer this in both directions. So for me, what was the starting point was more, okay, let's try those strategies or those detection pipelines that work for classic ML systems in neuro-symbolic models. And that's why we tried a bunch of different strategies, among which reconstruction penalties, some multitask objectives, and also there's been an attempt with a prototype for concepts, which is something that worked well with the few-shot learning. And what I hope was clear before is that in this setting, the strategies that actually make a difference are those that give more signal to learn the concepts. So some strategies that you may think they work in practice, like reconstruction, are not safeguard against reasoning shortcuts. On the other hand, so I'm not sure if people have thought about maybe awareness. I think so in shortcuts by creating ensembles of models that think a different story about the data. And for me, the intuition is coming from theirs, what I showed you, that if you have models that focus on different parts of the data, you may find different reasons to give the same classification. I hope this answers the question.
One quick thing, just observation or a question that I have. So you actually evaluate some systems that are pure ML systems, right? So the scope of reasoning shortcuts is really not just neurosymbolic systems. It's anything that makes a prediction. So in other words, you don't need reasoning, right? You actually, in the system, it's really, you mean something like semantic shortcuts or something, arguably. So So, and then you can see a neurosymbolic system where you're coming with the constraints, say, or the other things that are true, should be true of the concepts if you got them right, like 0 plus 1 equals 1. These are actually like mitigation strategies, or you could say, right? Adding that prior knowledge is like a mitigation strategy. So, or examples of constraints. So, would you agree with that?
Uh, I think so. What happens is in practice you limit the expressivity of the model in some cases because you try to fix some parts of your model. So you may lose some expressivity um, while you're forcing some kind of bias in the model. And I was mentioning before that that is also one important part of, uh, of why reasoning shortcuts appear. So in some cases, if you don't have enough constraint, you may learn whatever. And I think, in a sense, this can also happen to neural networks, but there, there I think we have less intuition for now. So I think it's a very interesting direction.
All right. Well, thanks so much, Manuel. And everyone check out his work and those of his colleagues. And we'll now take a break. So see you all at the end of the hour in just a few minutes.
Thank you.
Hello.
All right. Welcome back from the break, everyone. Our quick break. Next up, we have a couple talks that really get into more foundational issues, and I'm actually quite excited about Logic 8 network. So, and have been. So, I think I maybe I'll comment later what I love about these models. But with that, maybe take it away, Fabian.
Yes, sure. So I'm going to talk about verification and reinforcement learning as well. So there are going to be 2 modules in this talk, and I'm going to talk how we use logic gate neural networks to kind of boost what we can actually verify. And if you don't know about logic gate neural networks yet, don't worry, I will talk about it, of course. Okay, so I'm currently a PhD student at the Institute of Science and Technology, Austria. I'm supervised by Christoph and Tom. And actually, Christoph is currently looking for postdocs. So if any of you are looking for a postdoc in a super cool group, I can recommend a lot. You can reach out to him or send me a message. And then I will just get right into it. So basically, I think you're all very familiar with this dilemma. We have very classical approaches where we have some hard-coded, hand-coded software, where we might even have a state machine, and these are very interpretable. They are very verifiable. There's been a lot of work on making like these classical approaches actually have guarantees. But the problem is, once we want self-driving cars, the classical approaches kind of hit a scalability limit. And this is where the deep learning approaches come in, right? These are much more scalable, and in conjunction with classical approaches might actually make it possible to have self-driving cars. But with using deep learning, there comes a cost, and mainly intuition is lost. If I give someone a neural network that has been trained on some data, we really don't have any idea what is going on inside of the network. And this is, of course, a problem the research community has picked up on. And one of the ways that tries to solve this problem is neural network verification. And so basically you have your neural network, which is basically a calculation, right? And the question is, can we trust the calculation the neural network is performing? So this is formalized as having some input set, and this input set could be an abstract set of all possible images of straight roads. And once we feed this input set through our neural network, are all outputs actually within a safe set? So are all outputs actually outputting a steering angle of 0 or something close to 0, where we keep driving straight on the road? Alternatively, we might be looking for violations of being in the safe set. So current solvers mainly look at the real valued abstraction. So basically here you have one reload neuron, right, where there are 2, it's piecewise linearity. And the issue is, if we want to actually analyze a reload network, even if we only have like 1,000 neurons, in principle, you would have to look at all affine linear regions that the neural network generates to actually look at the whole output set. This is often not actually necessary, and you can do a lot of pruning and only look at the relevant regions. And state-of-the-art solver like Alpha Beta Crown can, on some input-output specifications, solve neural networks with thousands of neurons. But again, the problem here is we are actually looking at an abstraction of as a neural network as a mathematical object where we have real valued numbers. But the problem is our neural networks are actually not deployed as a mathematical object, but they're deployed on digital hardware. And with digital hardware comes a problem, and the problem is that we have many more non-linearities actually in the deployed network than in the abstract mathematical object neural network. And this makes verification actually harder. So if we want to actually verify the digital implementation of our neural network, it's much harder than just verifying the abstraction. So their approaches only scale to roughly thousands of neurons. And here you would use a bit exact solver. So for instance, one way you can go about proving certain properties of these neural networks is you take your neural network and you convert the neural network into a circuit. And then you use a satisfiability solver, a bit vector solver to argue about what the circuit actually does. So you take the neural network, convert it to a circuit, and argue about the circuit. But this actually blows up very fast. So you need thousands of gates to represent a single multiplier. And of course, you will have many multipliers in your neural networks. On the other hand, what you could perhaps do alternatively is directly learning a Boolean circuit. And the hope here is that this Boolean circuit, this learned one, would be much more compact. And then again, you can use bit vector verification tools, established tools from circuit verification to argue about what your network actually does and establish trust in performing the right computations. And this is actually not a completely new idea, right? So already in the 80s, people have thought about learning logic gate networks because it's just much more efficient, because a multiplier needs many, many logic gates. So it would be maybe nicer if you directly learn on the logic level. So this goes really back to the 80s, but back then you really had a bunch of heuristics, and learnability was really limited. Like on MNIST, you get like 95% with these approaches, which is not really that great. And then in 2022, Felix Petersen came along, and I think he actually gave a talk last year at the summer school, and he introduced the differentiable logic gate neural network. So here, instead of just using some other heuristics, they use backprop. And it turns out with that, you can actually scale logic gate neural networks to work quite well on even C410. So you get 85% on C410, for instance, accuracy, which is not nothing, which is good. So first, I will now talk about how can we actually learn these logic circuits, and then I will go deeper into what we actually do with these logic circuits. So first, learning logic circuits, mainly Felix Petersen's work, then about verifying learned circuits, doing verification, and then about learning controllers in a reinforcement learning. Okay, so for logic gate neural network, we have some input, right? Some input image, for instance. This can be represented as integers, and then we can threshold these integers to produce a Boolean vector. So you just have to believe me here. We go from the image to Boolean vector. I think this is not very very complicated, right? And then we take this Boolean vector and we feed it through successive layers of logic gates. So each of these gates we want, and task of the learner is essentially to identify which logic gate do we want to use where. So each question mark should signify there could be an AND gate here, and I really mean a logically AND gate, or an XOR gate, or whatever gate. And we learn which gate to use where, right? All 16 possibilities are allowed everywhere. And then at the end, we have a pop count, and we count how many, like we have multiple output groups, and one output group votes for panda, another one votes for cat. And if we actually have a panda as an input, we want more votes for the panda than for the cat. And this is the learning objective. So we want more votes here. Okay, so how do we actually learn which gate goes where? Well, in Felix Petersen, they introduced this linear relaxation over all 16 possible to input Boolean functions. They relax every single Boolean functions. For instance, and is relaxed as x1 times x2. And then they use this relaxed function and learn a probability for using every 16 of the one probability for all. Just the likelihood of each gate being used. And then once training is done, so once we say, okay, training has stopped, we actually pick the argmax gate. So in this case, the probability for the AND gate is the highest. So at this position, we would use an AND gate. And then we actually get a hardened discrete circuit. And here again, we get some Boolean encoding. We feed the Boolean vector through our successive layers of logic gates, where we just have zeros and ones. There's no relaxation anymore, and then we get our output. And every time I'm reporting any accuracies or anything, I'm always talking about this hardened version that we actually can put as a circuit on an ASIC or an FPGA. Okay, and this is actually very cool because it's very fast and very energy efficient. This has been mainly the point of view, or this was why they were actually introduced, right? So you get like 24 nanoseconds inference on C410, which is crazy fast, versus like 3 orders of magnitude slower inference on a quantized neural network. And what we are mainly interested in is, can we then actually use this compact Boolean representation, which I talked about right earlier, to perform more efficient verification? So this is what I'm talking about now. And I'm mainly going to talk about this paper, Logic Gate Neural Networks Are Good for Verification, which was done by Emily, Christoph, Tom, and me. And we got a DARPA Disruptive Idea Award last year at News for it. And first, what are we verifying? So in this work, we are verifying a very hard property. So this is the property that is most commonly verified in normal neural network verification. You have a data set of data points. So these are all data points in your data set, right? And for each of the data points you have, you want to certify that in an epsilon distance. So you can imagine a picture of a panda. If you just slightly perturb the picture of the panda, you still want your classifier or your neural network to return that this is still a panda. So the output class shouldn't change. This is what's normally verified in neural network verification. And then 2 years ago now, some people came up with a different definition that is much harder, where we want to verify global robustness. Because you can imagine local robustness, it only certifies for a set of data points in a data set. And global robustness here is really now over all data points in the whole data set. So for any data point in your data set, if the data points are epsilon close, so this is some distance, and you were very certain about classifying your sample right, then the panda should still be a panda, right? And why do we have this high confidence? Because obviously every neural network or every classifier has basically a decision boundary somewhere where we have to flip from classifying as blue to classifying as red. And this is why we have this high confidence term here as well. So this was introduced in CUF 2024. And the problem here is that this is such a hard property that you can only train very, very small neural networks and still verify the property. So the prior work, they take some data sets, they train a neural network, and then they certify that this property holds by just doing, by using Marabou actually, and they just dispatch the satisfiability query, which is not a Boolean satisfiability query in the case of the real valued neural network, but they essentially search for counterexamples. But the problem is their neural networks are very, very small. They only have like 16 neurons or something like that, so that they can still certify this property. So our approach, on the other hand, we take the same data, we train now this Boolean circuit, this logic gate neural network, then we encode this in Boolean set, and then we dispatch a Boolean set query. And here, obviously, the nice thing is that people have worked on set solvers for decades now, and there are very efficient set solvers around. And so here in red, you can see the performance on different data sets of the floating point baseline that the prior work used. And you can see that in blue are our logic gate neural networks. So we have higher accuracy than the baseline because our networks can be much, much larger because we can verify them much more efficiently than the floating point neurons, right? So their networks are like 16 neurons. Our networks are scaling to this you have to take times 3 because it's the layer number of logic gates. So our networks are up to 900 logic gates and get much higher accuracy. Also, our approach scales to 5 output classes, which the prior work does not. So just to repeat again, we take our logic gate neural network, we take the violation condition, we encode it in CNF, then we use an off-the-shelf SAT solver, in this case KISSAT. We get either a counterexample, and so a counterexample would say, yeah, okay, actually we can find a violation of the property, or we get unsat and then we certify the property. And I want to give like one more concrete example now. So I want to talk about the German credit data set. So the German credit data set basically has 16 features, and it classifies if someone should get a loan or someone should not get a loan. So it's binary classification essentially. And again, the condition that we are verifying is that if 2 inputs are very close to each other, if they're epsilon close to each other, so that might be 2 data entries, one data entry, for instance, of a man and one data entry of a woman. And if they are epsilon close to each other and we are reasonably certain on the first data entry, so for instance, we are very certain that the man should actually get the loan, then we are looking for an example where we can find an example that is where the woman would not get a loan and it's still epsilon close, right? So in blue, you can see confidence values here. So here on the x-axis, you can see the confidence value for which we ran this query. So essentially, you can find counterexample if you flip the gender up to confidence of 0.62. And after confidence of 0.62, so if our network says, yeah, this man should get the loan with higher than 0.62 probability, then every woman would also get a loan if she's absolutely close. Right? There's no other example. And actually for age, we find that our classifier is actually fair with respect to age. So the main takeaways here are that with the help of logic gate neural networks, we can do like bit exact verification, because again, also the prior approach just verifies over a real valued abstraction of the neural network, but we really do bit exact verification of very hard properties, because this property is very hard, and we can do this at better accuracy than prior work when using logic gate neural networks, and it also scales to more output classes. Okay, so that takes me now to the second part of the talk, where I want to talk about how we use logic gate neural networks for control. So this is a work that we just presented at ICML. It's work by Christoph and me. And we have a very stereotypical reinforcement learning setup. So we basically look at continuous reinforcement learning, where we have continuous state space and a continuous action space. So we look at very standard Mujoko benchmark here. So we have some policy that interacts with some environments. So the policy gives some action to the environment gives back some state and some reward. And typically this policy is a trained neural network. And what we say is, let's throw the neural network out and let's replace it with a logic gate neural network. And why would we do that? Well, of course, first off, logic gate neural network is much faster. So you could do additional computations on the same chip that you're using to do inference on. And it's much more area and power efficient as well if you implement it on ASIC or FPGA, because you don't need any multiplications in the end. And also what we were thinking about in the back of our mind, maybe we can later do very efficient formal verification again when using this logic gate neural network policy instead of using floating point neural network policy, which is hard to argue about. Okay, so what did we have to do basically to make logic gate neural network work in the context of continuous reinforcement learning? So typically what you have, how logic gate neural networks are currently used is basically you have some input data set. This is a static input data set. So for instance, MNIST or CFAR10. Then you can pre-compute some binary mapping basically. And then you have some output class. And there you have this final pop count layer where you just have a majority voting basically. But for RL, it kind of looks different, especially if you have potentially a continuous action space. So we have some observations, some sensor inputs basically. And then during training, the observations shift, right? Because we explore different parts of the state space, but we still need an encoding into Boolean vectors, because this is what the logic gate neural network takes in. And then we output a real valued number at the end. So here you can see a logic gate neural network drawn with LUT tables here, because this is basically equivalent. And we basically had to adapt the input encoding and the output encoding. So what we did for the input encoding, basically, it's actually not very difficult to make it work in RL once you know how it's done, of course. But basically, we just do some running input normalization, which is often done in RL, but not always. So we just observe the mean and the standard deviation during training, and then we normalize and map to some fixed thresholds to actually obtain the Boolean vector. And we do some clipping at -10 and +10, but actually no values get there anyways because of the normalization. And then for the output head, we again have this voting group basically, which we reinterpreted as a scalar head. So we get our output bits, we sum them up, then we normalize them, and then we learn an alpha and a beta to rescale this latent C basically, and then we push it through a tangency particles. And If you look at this very briefly, right, you see that there's a multiplication now here, and you also have to compute the tangents and parabolicals. But actually, it turns out we can pre-compute this and just put it into an SRAM lookup. So we can just put it in memory, and we don't have to perform any multiplications on the final deployed network. Okay, and here I'm going to show you now how good does this actually work. So we look at the standard Mucho tasks, so at AND, half cheater, and importantly, we also look at humanoid. So humanoid is quite a challenging benchmark, and here you can see the results for soft actor critic, but in the paper we also look at PPO and DDPG. And what you can see in blue is the floating point baseline. So we used a clean RL baseline here, and in orange you can see a quantized baseline. And this is over 10 runs because you have a lot of noise, right, in reinforcement learning. And because of that, we report here over quantiles over 10 runs. And where the red boxes are, you can actually see the accumulated returns of the logic gate neural networks with different layer sizes. So we always, or with different layer widths, we always use 2 layers. And for instance, in red, you can see 128 logic gates per layer. So overall, the red models have 256 logic gates, and they perform basically already on par with the floating point baseline, which is already very nice. And then in one case, in half cheater, you actually have to scale it up to a very large logic gate neural network in order to obtain the same performance as the floating point baseline. But in general, you already get it very soon. Okay, I also have a video. I don't know if this will play nicely while streaming, but I will just show it real quickly. But basically what you can see, it's a trained humanoid policy that we trained with, where the controller is a logic gate neural network, right? Yeah. Here is a hardware overview. And here the most important column probably is the latency column. So we have a very competitive quantized baseline. So this baseline uses 2 to 3 bits and also only 16 to 256 neurons in the hidden layer. So this was all ablated. And you can see that actually the latency is only like around 30 nanoseconds for the differentiable weightless controller or the logic gate neural network controller, whereas the latency is much, much higher for the quantized version. And this has been compiled for an FPGA or synthesized for an FPGA. And this FPGA is actually very small. So this FPGA you can get for $35, which is not often the case for FPGAs, right? So it's really small FPGA here. Another nice thing is, because the extension of logic gate neural networks we actually use in this work learns the connectivity of the first logic gates to the input layer. So what we can actually observe is these are the input dimensions of humanoid. So there are 360 input dimensions roughly in humanoid. And what you can observe is that this is also averaged on 10 models, 10 different models, that there's very consistently some connections are never connected to by the logic gate neural network. So these are not relevant at all for the control task. These are discarded during the learning, which gives you some nice, maybe not interpretability, but inspectability. And then there are some dimensions that are connected to a lot. And this is also very consistent across seed runs. And these are the forward velocity connections mainly, or dimensions mainly. So here really the takeaways are, you can train a very small circuit as a deep reinforcement learning policy, at least on these continuous reinforcement learning tasks, which include humanoid. These are, of course, very fast, much faster than a quantized neural network. And to a certain degree, they're inspectable. And yes, with that, I actually want to go to my last slide, which it doesn't allow me for some reason. Well, nice that it stopped working now. And with that, if you have any questions, I'm happy to answer them.
All right. Thanks so much, Fabian. So, yes, love this topic because, well, it's extremely timely, of course, with everybody now highly aware of the energy issues of current neural net models. And in general, also just time costs. So I want to ask you. So, what is it? You mentioned as an ideal, you would do the verification in dynamic systems, even real time. First of all, do you mean as you're going, or somehow you stop and check?
So what we are looking into right now is mainly verification before deployment. But runtime monitoring, for instance, I think would also be extremely interesting for logic gate neural networks, just because they can be run so fast in parallel to your policy, right? Which is would be a very nice application.
And what would you say is the state of that, or what's preventing you from doing, that ideal?
Well, mainly time, because we're currently trying to essentially finish up work on doing verification with these controllers. And I think one of the promising next steps is for sure runtime monitoring as well.
Okay, and what would you say as far as the learning? What are the limitations right now?
Well, okay, there are a lot of limitations for the learning, right? So it only scales to C410 so far. I mean, I know there is some work on trying to scale it up further, but it doesn't scale to ImageNet, for instance. And this was also one of the inspirations of using it for RL, because in RL, typically you have much smaller neural networks, right? So the hope was that their logic gate neural networks would also work, and it turns out they do. But I think there's a lot to be done in trying to scale these logic gate neural networks. And mainly, like, there have been new relaxations proposed and stuff. So for the original Felix Peterson one, you need 16 logits per logic gate. This has been reduced to 4.
Okay. And I guess the inference part is easy. So
yes.
Now the verification, what research areas would you recommend for people who want to help on that problem?
Yeah, so I mean, the problem is for verification as well. The problem is that the convolutional logic gate neural networks are not really available. And this would be the most interesting next verification step, I think. I know that there are some models out there, but you only get like 70% on C410 or something like that. And I'm not sure that this is yet that attractive there. So I think you have to find some smaller, where you really need to verify small logic gate neural network, where you already only have small neural networks right now, because the logic gate neural networks don't really scale to larger examples yet.
And what about alternate formulations of verification? What's the whole spectrum of, you mentioned, local versus global, robust.
Robust, yes.
What would you say? Is there an even higher ideal?
There are like a lot of different verification specifications, right? I think it always depends a lot on the task that you're trying to verify, or it always depends a lot on the application. So what I'm mainly interested in is really, verification of closed loop systems where you have dynamics, and you might do this with barrier functions, with Lyapunov functions. So something we have been trying to work on is using logic gate neural networks as barrier or Lyapunov functions. And we weren't really able to make it work. But for barrier functions, at least, that should be possible. I think that would be a very interesting research topic.
Okay, excellent. All right, everyone, check out Fabian's work and that of his colleagues. And let's keep in touch. I think this is a great area.
Thanks a lot.
Both verification and the models themselves. So, all right, thanks. Hey, Ben. All right. So next, I'm very excited about this work. So this is in the category of, which I think is in a way one of the hardest places to work, and in this whole area of neurosymbolic AI, it's actually at this foundational interface between discrete and continuous, and this gets very mathematical. Okay, so but that, I believe, is one of these insight and progress there is essential to the next generation of techniques. So and so I encourage anybody who has interest in this kind of thing, get into this. This is where the deep foundations will be laid, in my opinion. I've mentioned this maybe in every summer school, trying to get people to work on it. So, and this is related to symbol emergence and other things I think people understand are very important. And another thing I love about this work is bringing in additional areas of math that we don't use as often in AI. So with that, take it away, Ben.
Right. Thanks for the introduction, Alex. Okay, so hi, everyone. So I'm coming from the physics of learning dynamics and the inductive biases in deep learning. Okay, so the central thesis of this talk is that the standard Occam's razor in deep learning is fundamentally geared toward continuous geometry. And because of this, it's not quite well aligned with discovering a discrete exact algorithmic rules. Okay, and many of the talks in the summer school focus on how to integrate deep learning with external symbolic systems, the Neuro-Symbolic pipeline. But this talk will explore a different path, right? So instead of combining with this external system, I want to explore how we can endow deep learning itself with an alternative inductive bias, right? One that can natively discover this exact algorithmic rules from the ground up. Okay, so let's begin. All right, so here's a quick background. So we all know that deep learning can achieve remarkable generalization. And the key mechanism for this is that it can discover a low-dimensional latent manifold to smoothly interpolate over the training data. Okay, so for example, natural images, they have massive ambient dimensions, but they reside on quite low-dimensional manifolds inside that ambient dimensions, right? And deep learning is extremely good at exploiting this geometric compressibility to find these low-dimensional representations. Okay. So despite this strength, the flaw is that the geometric compression is fundamentally, it's not interested in discovering any underlying rules or exact algorithmic structures. But so instead of discovering the true mathematical logics, like deep learning models such as LLMs are known to rely on a bag of heuristics, right? So for example, some surface level proxies such as digit co-occurrences or localizing pattern matching and so on, and memorize templates. Okay. So this algorithmic gap exposes a critical limitations on the current paradigm. Okay. So the core question I want to raise is there something beyond this geometric smooth interpolations, right? Is it possible that we are missing a fundamentally distinct mechanism for generalization? For example, a novel inductive bias aligned with discovering this exact algorithmic rules. Okay, so I don't have the full answer yet, but then I can show you that the answer seems to be quite positively yes. Right? So there are two types of inductive biases. So one is a hard constraint on the hypothesis space, which is built directly onto the model architecture, right? For example, convolutional neural networks have hard-coded equivariance to guarantee translation equivariance under that symmetry transformation. Okay, so it's a hard constraint. It's not very adaptive. So if your underlying data does not respect that symmetry, then such model can underfit the data, right? So a current trend in deep learning is to moving toward more highly flexible unconstrained models, such as transformers. And for these models, generalization more relies on the second type of bias, the soft implicit bias. Okay. So the model architecture and optimization conditions, they combine to induce a soft preference over the hypothesis space. Okay, which means they implicitly define a certain simplicity metric known as the Occam's razor, so which guides optimizations toward a certain space in the model space, such that it can exploit the underlying compressible structures in the data. Right. So earlier we covered that deep learning has this implicit bias toward mostly concerning the geometric compressibility. Okay. So let's cover exactly how this is done, right? So how deep learning induces this low rank bias. So this is quite hard to do, but then it turns out for certain simple kind of models called deep linear networks, we can actually study this quite thoroughly and theoretically, right? So deep linear networks is just, you can think of it as standard feed-forward networks, but you strip away all the non-linearities. So this leaves just a sequence of matrices, right? So in this case, we have depth D. So we have matrices W1 to WD. And the full input-output map is described by this W bar, which is simply all the matrices multiplied to each other. So W1 to WD. Okay. And yeah, and this simple model allows for a thorough theoretical analysis for this inductive bias. Okay, so there are many ways to show that this model has the low rank bias. So one way is to impose L2 regularization. Okay, so here is an example with a 2-layer case. So W bar is just W1 times W2. And when you impose an L2 penalty, as shown as here, and optimize this over the parameters, it turns out this minimum loss is equivalent to the nuclear norm of the product matrix W bar, right? So that's the sum of the singular values of W bar. So if you visualize this on the singular value space, this is simply just L1 penalty on the singular values, and which is known to have this sparse. It tries to tend to drive the singular values towards sparsity, right? So it has these sharp corners. So when you try to minimize this, the singular values will tend toward onto this coordinate, right? So compared to 1-layer case, which is simply this Frobenius norm, the sphere. So this part, in this case, there is no bias toward the sparsity. So you would end up with a dense, high-rank solution. So when you already go to just 2-layer, this nuclear norm gives you a nice differential proxy for rank function. And in fact, when you go to infinite depth, as D goes to infinity, this minimum loss, minimum L2 regularization loss, converges exactly to the rank function, right? So this could become extremely sharp along the coordinates. Okay, so this is one way to show that when you pair this deep linear architecture with L2 regularization, it induces low rank bias. Okay, so there's another way. So you don't even need such regularizations. Instead, if you initialize the network with small weights, so all the weights W are very close to 0, it can't be exactly 0. Then in that case, the gradient will become 0. So there's no more learning. But when it starts from fairly small values, you can show that, in fact, all the singular values of each factor matrix will all become asynchronized. And the singular values of the product, this sigma bar, has this dynamic such that the rate of change of the singular values is proportional to the singular value itself up to some power, right? So which means that the small singular values will take long time will have very slow growth, and the larger one will grow much faster, right? So it's called the rich gets richer dynamics. Okay, so when you train these models from small weights, what you end up having is the most significant singular values will grow first, right? And followed by less significant ones in sequence. Right? So this is called the incremental learning dynamics. And the loss profile will tend to have this staircase shape, right? As a model learns each relevant dimensions, the loss will go down until the next sigma dimension also gets learned, right? So this shows you that how this model can also discover the low rank structure, right? So the model would only try to learn only the relevant small number of dimensions necessary to fit the data. So this is another way to get low rank bias. Right? And this figure compares these two approaches and show you that in practice they are really equivalent, right? So if you start from small initialization, then the singular value will start from close to 0, and it will only learn the relevant necessary dimensions. Instead, with L2 regularization, you can start from large singular values, but this L2 penalty will try to carve out or decay all the unnecessary dimensions to 0. So you also get ends up with low rank solutions. Okay, so this is the core mechanism for geometric compression, the low rank, discovering the low rank subspace of the solution. Okay, and the important part is that this low rank bias, although we know the details only in the deep linear network case, the same principle also applies to deep nonlinear neural networks. So it's really this low rank bias is really the consequence of the deep architecture. Okay, and so there are many works showing that deep nonlinear networks also have the same bias. Okay, so here's a simple setup to demonstrate how this low rank bias actually drives generalization. Right, so it's a classic matrix completion task. So imagine that we are given some true underlying matrix, but we can only observe some sparse, small number of random fraction of these entries, right, as shown here. Okay, and the goal is to recover all the missing entries. Okay, so this is the basis for the recommender systems like Netflix and YouTube, how they recommend you new videos you might be interested in from your past history. Okay, and this can be solved by trying to find the simplest solution that fits the observed entries, right? And for matrices, of course, the relevant notion of simplicity is a rank, right? So we can solve this by trying to find the low rank solution. So of course, this won't work if the matrix has no underlying structure at all, if the entries are completely random from each other. But if it has this compressible low rank structure, then you can exploit this. Right? And this matrix completion is a nice classic example where we have all the nice generation bound. So for example, the sample complexity scales linearly with rank. Okay, so rank is really the most important part for generalization in this problem, right? And people, of course, now you can apply training deep linear networks, and as we've shown before, people show that such models indeed can discover the low rank structures quite well. So it finds the factors it learns corresponds to the small column dimensions and column space and the row space. Okay, so this is a simplest example for how the geometry compression bias in deep learning can discover the low dimensional subspace of the data. Okay. All right. So this is now the twist where the main talk starts. Okay, so now think about given a similar table, but instead of a matrix of real numbers, this is a table of discrete symbols, right? So it's written as integers, but it's actually, it can be any arbitrary symbols. And the goal here is to recover this full table. And the underlying assumption is that this table reflects some underlying binary operations. So, okay, so for example, A times B equals C, where this A and B and C comes from some finite set, and this circle reflects some underlying operations, which is unknown. Okay, so we can also try to solve this task by minimizing some notion of simplicity. But here's the difficulty, right? What's the relevant notion of simplicity in this task? So that's not clear from the get-go. But here's an important clue. So these binary operations form algebraic structures, and among all the algebraic structures, groups are known to be form the simplest building blocks for the algebraic structures. So the relevant notion of simplicity can come from the group axioms. Okay, so there are 4 main group axioms, but it turns out the most relevant one is the associativity axiom, which states that when you operate over multiple inputs, like A times B times C, it doesn't matter whether you operate on the A and B first or B and C first. Okay, so yeah, you can put parentheses in either way. And this associativity axiom impose a strong constraint over this full table, such that this gives you a nice way to compress, right? So the overall description length of the table, if it's a random binary operations, it's the description length of the table scales as n squared log n when the table is n by n table. But with the associativity condition, it goes down to n log n. And this mainly comes from the fact that the symbols can be arbitrarily relabeled, and yeah. Okay, so this associativity is the relevant notion of simplicity for this problem. Another important aspect from a group axiom is that the geometric low rank bias from before does not quite apply for this task, because all the group tables has to be invertible. This multiplication has to have some inverse item as well, and that means that each of these columns or the rows of this table has to have this the Latin square property. So each item can only appear once or over the whole row or the column. Okay, so right, so the low rank property from before relies on that the columns of the matrix tends to be similar to each other, right? It's a mixture of some small number of basis functions. In this case, each row or columns are permutations of each other, so there's no such simple similarities between the rows. The low rank bias really fails in this case. Okay. All right. So yeah. So I just showed you that the algebraic simplicity bias in this problem is the associativity. And now the central question is there a way to induce this associativity bias in an implicit manner, right? So in the earlier slide, we showed that the low rank bias really emerges from having a deep architecture, deep matrices products with L2 regularization and so on. It turns out we can extend that to instead use tensor factorization model and paired with a flatness prior instead of the L2 norm. Okay, so I'll go through the details later, but it turns out when you combine these two parts, they implicitly define the simplicity metric of associativity. Right? So when you minimize this H over the model, that's this H mean really implicitly measure the number of associated violations in this table. Okay, so we'll go over the if you have time. So yeah, so for the interest of time, we might be able to have to skip this quickly. So first of all, to to train on this model, we first lift this table, n by n symbol table, to a tensor, to n by n sparse tensor. So this tensor delta has entry which is 0 and 1. So it's 1 if and only if its indices, delta ABC is 1 if the indices satisfy the underlying binary operation. So if A times B equals C, otherwise it's all 0. Okay, so we'll use this as a target tensor. So what this means is that this transforms the this binary operation table completion problem into a tensor completion problem. Okay. Okay. So the model has this underlying factor tensors A, B, C, which are n by n tensor. And what we do is that for a given index A, B, C, the small ABC, we take a matrix slice of these factors. So AA is a matrix n by n, and BB and CC are all n by n matrices, and we multiply them together and take the trace. Okay, you can think of this as the inner product between the matrix slices. So that gives you a scalar number, which is a single entry in this model tensor. Okay, and we'll try to fit this model to the observed entries on the operation table, as shown before. And the simplicity metric is the flatness prior. So you take this reconstruction error, so t minus delta squared, and take the second derivative, so Hessian, and take the trace. So we take this as the measure for simplicity. For the regularization. And what we can show is that this minimum H can be attained if and only if this underlying table is isotopic to a group operation. Otherwise, it would be strictly larger than some floor value. And also the optimal parameters, theta star, is not any arbitrary parameters, but it exactly corresponds to the unitary regular representation of the underlying group. Okay, so it turns out there is a unique minimum up to equivalency. Yeah. Okay, and the main theorem is that result is that this H mean really measures the associated violation of the table. Okay, so here's this the numerical example, a demonstration of how this works. Okay, so on the left side we're showing you the product tensor T, and on the right hand side we're showing you one of the factor tensor A. Okay, and you can see it starts from some random values, so it's really not sure. But over time, it discovers the underlying sparse tensor T. Right? And you can see at a certain time, the test loss of on this product tensor goes all the way down to exactly to be the train loss. So there's really it really uncovered the full unknown tensor table. And here's an even bigger example and it also works just as well. So it's okay. So at this point, it really discovered the full underlying tensor. Okay, right. So here is the comparison, how this compares to performs against the transformer. So this result is coming from the OpenAI's Grokking paper, if many people might know. So here this probably is showing you how transformer can discover the underlying operations. So y-axis is the test accuracy, and x-axis is the number of fraction of observed data. And transformer, so the test accuracy goes down with a small number of observed data, and it works quite well for some simple operations, but with uncertain notion of simplicity. But for some complex operations, this modular, so modular addition is easy. Modular subtraction is a little harder, but this higher order polynomials are a lot more difficult, right? And this one S5 is in fact also a group operations, but then transformer find it a lot more harder to discover. And another important thing is that this transformer takes extremely long time to converge. So it can often take many hours or 2 days to fit this very simple data. Okay, and it gets worse with a small number of observed data. And here's the result for our model. It's called Hypercube, and it performs quite well, as much better, especially for the group operations, and most importantly, it converges much faster than transformer, so about 100 times faster for given training data fractions. And in fact, you can also put extra conditions so that it's even more narrowly focused on group. Before, other than group isotope, it only cares for groups. In that case, it converges even much faster, up to 1,000 times faster than transformers, right? And on the bottom plot, I'm showing you that how well this model generalizes. So in fact, we're measuring the area under this curve, on this test accuracy curve. It's directly reflected by the minimum, the flatness H mean that we compute. So in fact, the higher this value, so more complex the task is, it becomes harder to predict. So it gives you the direct measure for how well this model can generalize. Okay, and well, I guess I'll have to skip over all the details. But, so we have a full proof showing you exactly how this model operates. So, right, so we have full proof showing you that this H mean indeed achieves some minimum value, if and only if the underlying table is associative up to isotopy. Isotopy means completely relabel of all the input-output labels. And if it's non-associative, then this H mean has a strict gap larger than this constant floor. Okay, so so this shows you that this model really has inductive bias toward discovering a group compared to non-group, non-associative tables, right? And let's just focus on the right figure here. So here we are plotting the H mean, the minimum flatness prior, flatness objective, compared to the number of associativity violation. So we generated all possible random operations table for small size n, and it shows you that this has a monotonic relationship. So this H mean really achieves the minimum value if and only if the operation is associative. There's zero violations. If there's more violation, there's a strict gap from this minimum floor, but also there's nice monotonic relationship. So minimizing this operation, this objective really will try to minimize the associative violation and try to discover the group operations. Okay, so so I'm almost out of time. So to summarize, I compared the two different domains, right? So the default domain that deep learning operates on works on finding geometric compression, right? So the canonical task for that is the matrix completion task, and the canonical model for solving that is a matrix factorization, which uses vector embedding paired with Gaussian L2 regression prior, right? And it aims for finding low-rank solutions and smooth solutions. Our framework instead aims for finding the algorithmic algebraic simplicity of associativity, and it can be attained by combining a tensor factorization, which makes use of the matrix embedding of symbols, and paired with flatness prior. Okay, and what we show you is that so this really shows a completely different mechanism for generalization by finding the underlying associativity algebraic structures compared to the geometric low-rank structure. Okay, probably have to skip this, but then this distinction between geometric versus algorithmic compression is a long division between the classic statistical learning theory versus the even more classic minimum description length and the cosmological complexity and so on. And the problem for the classic algorithmic compression approach is that it requires non-differentiable combinatoric search to find the optimal. Our work, although it's a bit restricted to this algebraic complexity problem, our work shows you that in fact this can be optimized in a differentiable manner. So it's a lot more easier to optimize. Okay. So yeah, I will wrap up there.
All right.
Thank you.
Thank you, Ben. Great stuff. It wasn't obvious, but Ben is a visiting scientist at the Centaur AI Institute. We have 4 now, by the way, visiting scientists. So, we think this is exactly the kind of work, as I mentioned, that could unlock the things we want to unlock in Neuro-Symbolic AI in a very deep way. So, I have a question. If geometric compression explains much of modern deep learning, what do you think is the next fundamental inductive bias that we should be searching for to achieve stronger reasoning and generalization?
Right. So that's a good question. So, and I don't have the full answer yet, right? So, by the way, so the one thing I want to mention is that, so here, I mean, we show the associativity, it can be a strong inductive bias for solving this type of problem. It may not be solving the full problem of discovering the underlying algorithms, but this work really acts as a counter example, showing you that there's more than just geometric compression, right? There's other ways, alternative inductive biases that can discover structures beyond the smooth interpolation regime, right? So yeah, so I don't have a real answer for what other type of inductive biases could be needed. I think this is a good starting point to explore. Yeah.
All right, excellent. And Ben, maybe if you want to jump on Discord, send you a link for in case there are more questions.
Right. Yeah, I'll be happy to answer more questions offline.
All right. Well, thank you, Ben.
Thanks so much.
Okay, next up, we have our exciting panel. So I can bring them up now. All right. Here we are. One more. John, if you can turn on your camera. While we're waiting, I want to particularly thank Michael for joining us from New Zealand at this.
I'm actually in London.
Oh, okay.
At the
My
moment.
thanks are retracted then. No, I'm kidding. Also, Bob in the UK, and Benjamin and John from the East Coast. We'll give it a few minutes for John to join, but
all right. So, can you hear me?
we can hear you. We just can't see.
So, yeah, I don't know what to say about that. Cameras are always fun.
I always say we'll solve AI before we solve audio-visual technology. So let me just, while we're working on that, introduce what we're going to do here. So this is a very special collection of leaders of major efforts that were landmark projects of the symbolic AI era, let's call it. And why is this particularly a good thing to look at is, you could say many people are maybe understanding Neuro-Symbolic AI as a revival of sorts of, and where many people already, hey, all right. Already.
Looks like Ben and I got the same designer.
We think alike. So we have in particular, we have a new ambitious a set of researchers, young researchers, PhD students, and also old researchers like myself, looking for, who could use the lessons learned and inspirations people are already building off of the foundations that you all helped create. So we're going to learn more from these people who worked in these pioneering efforts. So by that, I'll give some examples. Of course, we heard from Bob this morning, and Prologue and the foundations underneath Prologue in particular, and Prologue itself and its descendants, clearly one of those really essential projects without which we wouldn't have much of what was built. The Japanese 5th generation project was a whole national effort built upon that. Psych and Doug Lennett passed recently, and Michael was head of research at Psych for a while, and also helped organize that retrospective recently for Doug's on Doug's work, and I want to say personally, we have looked a lot at Psych, and there's a lot of incredible stuff that was done there, and also cognitive architectures, SOAR and ACTA-R, and we have John here, who was the creator of SOAR, and semantic web, knowledge graphs, ontologies and rules. We saw yesterday all the activity in industry, a lot of it building off of ontologies and knowledge graphs. We have Benjamin, who is one of the architects of all of that technology. And I'll mention one more, business rule systems, and like JBoss, then Drools, which sort of in the same kind of family that actually had a lot of impact in enterprises. So, all right, so that's what we mean now. So there's so much to talk about. I'm sure we won't run out of time on interesting things, but let me ask first for the group, and anyone can jump in with anything. What big successes do people not associate with logic and symbolic AI? I think one of the, when paradigms kind of go in and out of fashion, people tend to forget a lot of stuff, basically, that was in the previous paradigm. And so I think even, many people even say things like, logic, what did logic ever do for us? So I'd like any comment on that.
I have one thing, and that's object-oriented programming, and therefore its sort of descendant, JSON. That's inherently, it's a simple logical idea, but type inheritance is clearly logic.
I have another, which is the theory of declarative logic programs, which is considerably distinct from Prolog as a programming language itself, or as a executable language. And it underlies not only SQL, but also XQuery and Sparkle and a number of other non-SQL type of database systems and languages. And it really has been the foundation for much of the theory and expressive extension progress over the last 30 years, after being first developed and invented in the 70s and the 80s.
Well, and verification systems, I think people don't appreciate how important they are even to building neuro-symbolic systems. That one of the reasons why the current math generative systems have been successful is that they can produce a proof, but they can't really check it. And so we have automated checking systems that really are important for it. And also, that goes on all the way down to chip design. A new NSF proposal just got funded at Michigan. I'm not part of it at all. But they're using neural nets to do the exploration and generation of possible chip designs. And then they use symbolic logic-based systems to verify that they actually do what they're supposed to do. And that, so I think that's really critical. Fine, since I'm on a roll. Alex, you know this better than anyone, but all the work at NASA on scheduling, both scheduling flights, but also scheduling on the rovers, is all comes from the history of, comes from early work on planning and scheduling in AI. And that's not something you want to do with a large language model, is to try to send it up to Mars and have it do the scheduling for you. So I think there's a lot of these applications that are very valuable.
I'll throw out another one, which is databases. Many people don't even associate databases with logic. Anyone want to comment on that?
Well, I think it's worth observing that the theory of databases, or the logic of databases, is basically LP, which was named closer to Prolog, but really grew out of the effort to unify the theoretical foundations and kind of analysis around that with databases. So a lot of people say that the first semantic technology was relational databases.
And the reason you can install something as complicated as a Python environment is because of logic solving a very large constraint problem about like what particular pieces of brokenness are going to bite you next. Fortunately, now we have large language models to manage that process for us, right? But underneath it, it's satisfiability solving on propositional logic.
All right, and I think it's
so let me do one more that's completely out of here, which is cognitive modeling, not logic. Famous quote from John Anderson is that what people do is not logical necessarily, but what's useful. But if you look at the core models of both SOAR and ACT-R, and ACT-R you could argue is the best end-to-end architecture for doing cognitive modeling of short-term cognition, it's all symbolic reasoning that combined with things like activation. So it's a hybrid model. And so I think that's been a huge impact on cognitive psychology. And I also think the path should go the other way, which is that a lot of current research should look back into what we've learned about neurosystems in the humans, in the brains, and also in psychology. And there's a lot to be mined there to look at how to do things slightly differently than what's being done today.
This is a great point there, and we probably need a whole nother session just on cognitive science, cognitive psychology, because there was this really, to me, productive period where there was a lot of interplay, as you mentioned, both affecting psychology and psychology affecting AI, which is sort of forgotten, and now it's neuroscience. It's a whole thing in itself. But
there's a lot of neuroscience, and one of the things that's coming back is that there's other neural learning algorithms besides backprop, such as predictive encoding, and that have more evidence that that's what the brain is doing. So I just think there's a rich set of lessons to be learned from cognitive science.
And Bob also touched upon that in the tutorial this
Great.
morning. So, okay, now what, along the lines of things that got forgotten. So what big, interesting ideas that didn't necessarily come to full fruition, but were important, in your opinion, got forgotten in the mix? And I have a few examples of my own, but like deductive databases, cognitive robotics, a la Leslie Kilbling, meta reasoning, some of this from discussion with Benjamin, and generative grammars even, which coming from natural formalization of natural language efforts, which I consider adjacent to AI, but just to throw out a few, but anyone want to comment?
Maybe,
Yeah, please.
maybe I could mention the work in the 1980s using Prolog as to teach children. The Prolog Education Group spun off an international series of workshops, which was growing relentlessly until the 5th generation flopped. And that effort to teach logic to children more or less disappeared until it was revived just a few years ago. And it's perhaps interesting to go back also in relation to that to ask what really went wrong with the 5th generation project. And in particular, there are a lot of things that actually are being rediscovered now that inspired the 5th generation project in the first place.
Yes. On the education front, I think we're also interested, of course, in education. That's part of what this event is about. And we find we're having to teach everyone logic. So I think, it is, logic itself is somehow, not so much part of the curriculum anymore, which is really sad given its, fundamentality for everything, computer science, programming languages, chips, and so on. But so that's a very relevant point. Just how we teach logic. Logic is actually takes a thought how you teach logic.
Yeah, I want to elaborate on that point. The concept of logic as defined originally for use in mathematics, classical logic, and first order logic, which is pretty central to most computer science education, needs to be expanded in terms of the pedagogy to treat logic programs as a logic, including all the extensions that support argumentation. Even young kids argue, starting when they're like 3-4 years old about why something should be an exception to a rule or whatever, priorities essentially among instructions or guidance or principles that they're absorbing and acting on at a young age, including when they interact with their parents, their classmates, their teachers, etc. So I think that we need much better pedagogy, but also a prioritization in pedagogy of logic of more practical kinds, as opposed to just the logic that people learn for use in mathematics. And that means focusing also on natural deduction type proofs, which people learn typically by no later than high school when they get exposed to doing proofs for Euclidean geometry in their math classes. But the deprioritization of teaching of non-classical logic since the 80s, or since the 90s, I would say roughly, which I think is part of what Bob's alluding to, is, I think, something that definitely needs to be addressed at a community level. And now the Europeans who learn computer science at the graduate level usually get much more exposure to non-classical logic. And to logic overall is more central in pedagogy there, I think largely because logic was originally invented in Europe. between the Greeks and the UK and the Germans. So there's still a kind of honoring of that, but the pedagogy, there's efforts with the Prolog Education Group that Bob was referring to that's very much current that could help advance the substance and consensus around the treatment of it as central in curriculum.
I have two things. The first of which is, I think, closely related to what Ben was talking about, and that's the philosophical basis which drove us towards logic and towards thinking about things like the epistemology, the nature of knowledge, the difference between knowledge and beliefs, for example. All of those bases which led us to this particular instantiation of symbolic logical systems still hold in terms of thinking about what thinking is about. And I think that we would do well to revisit them as we design these systems which learn to perform reasoning-like operations. The second thing that I think sort of fell by the wayside a little bit, or hasn't received as much attention as it might, is the notion of context, right? This was a fundamental basis of psych, and I think one of the most valuable ideas, this idea of maintaining theories explicitly, right? And the relationship amongst theories. And I think when I think, for example, about why language models, right, produce the sorts of errors that used to be called hallucinations when they were doing a lot of it. They don't do so much of it anymore. But the reason that happens, right, is that theory selection is based on a posterior probability distribution conditioned on the inputs, right? And that's a very weak basis for selecting amongst theories, which means that things which don't have to be mixed together get mixed together. So thinking explicitly about what it means to have knowledge and then applying that to understand what's going on in these newer systems, I think can be very productive, both in understanding their behavior, but also perhaps in designing inductive biases, which make them into more reliable reasoners and perhaps more compatible with purely symbolic systems like lean provers, for example.
So I'll be a little contrarian in that logic is not central to what I do. Instead, what's most important to me is the integration of different kinds of memory, different kinds of processing, and what we call cognitive architecture. So to give an example, this is an example I use, and I'm going to ask you in the audience to do it, to get a feel for the different kinds of processing we believe happen in cognitive architecture and in people. So imagine the word wow. Now flip it upside down and then tell me the last time you saw the spouse of that person. And maybe for some people that's never, sometimes that's a few days ago, sometimes that's months ago. But if we start out at the beginning, when I say, I give you speech, you have to process speech and then turn it into an internal representation of a concept, possibly accessing semantic memory, but then you are able to visualize it and you're able to create the letters WOW as an image. And you're able to, and I don't know if anybody ever told you to flip images around in your head before, but I did, and I bet you did it. And you came up with the word mom, and then you were able to access semantic memory as to what is a spouse of mom, and then you were able to access episodic memory and think back about the last time you saw that person, your father possibly. And large language models and generative neural systems have been very good at the pattern recognition, pattern completion, next step prediction, but they're missing, for example, episodic memory. They're missing imagery. And I even checked today with Claude and talked to it about it, and it said, yeah, that's something that's missing. So I don't think it was
Yeah.
So I think looking at how to put all these systems together, and not just as the way people are doing with agentic AI, but people have forgotten that we can have these different components. And just to go on a little bit more, when I'm doing work, I don't want to depend on language models for all of these systems because they're so slow. And if I want to build real-time systems, waiting a second or two for each of these operations is way slower than what a human can do. Now, they can do some things very much faster than humans in terms of doing the whole process. But when you try to do this linearized system, sometimes that, at least maybe the way I access them and the amount of compute I get. But anyway, I think that looking at how all these parts fit together, and right now people are talking about putting an episodic memory on the side of a language model or putting a semantic memory. But I think that we, and that's maybe the future, but we need to look at integration.
Yeah, I think it's a good, just building off of that, I find it amusing looking at developments in the pure neural world that kind of coming up with innovations like, hey, let's add memory. And, you know, a lot of the things that we assumed probably 50 years ago, you needed an agent, you know, and even things like theory of mind and so on are still not, you know, are really addressed in a pure neural way. So, and, you know, things that have been in store for a long time are things that people are now starting to think about, hey, we need these kinds of things in an agent. So,
well, let me just give you another example that I find very compelling.
Yeah.
Because one thing humans are able to do is anticipatory thinking, or sort of what we it's actually episodic memory, but it's prospective memory, where I'll look at the weather's forecast and say, oh, it's going to rain at 3 o'clock. I should take an umbrella with me, or I should do something at 3 o'clock that I am not going to do now. So you create a memory that is then, it's like a timer going to go off in yourself in the future so that you do it. And because within the context you are then, you might not have enough to actually do it. So for example, when I am going to go to my mother's house and I need to bring something to her, I no longer depend on myself saying as I walk out the door, oh, I need to bring this, which is a perspective memory. And so maybe this is arguing against it. But what I do is I go put things in my car so that they're there for when I'm going to drive to her house. And so I think that's a combination of reasoning about the future that just isn't part of what these systems are doing, because they're not embedded in the world, and they don't have this time of existence of having to do things in the future. So I think these are things that we've sort of forgotten about as issues because we've used them so much in specific applications like chatbots and stuff like that.
I just want to follow up on one aspect of what John, you talked about, which is integration. So one of, I think, the great values of logical methods is for integrating various systems, like software systems. And the whole aspect of having distributed governance and information that's not all just in one big base, the way that, you know, is kind of the LLM mentality, for example, is very interesting. There are a lot of important research issues there, including related to security, trust, authorization, privacy, confidentiality, approvals, and things like that. And one of the key themes, of course, in the 5th generation project was parallelization. But there's not just parallelization kind of, you know, within a single machine or, you know, cluster owned by a single or run by a single group or organization, but there's also this kind of messier, what I like to call social scalability set of issues. Maybe being able to scale out to the size and complexity and differentiation of organizations and activities among organizations, companies, as well as individual people and so on. And I think a lot of that has kind of gone by the wayside in the symbolic AI area, just because people were focusing on other stuff, but also because the funding in the area was so low for so long after, roughly speaking, the 80s or the first part of the 90s, when AI moreover had a winter. So the semantic web really pursued many aspects of that vision, but in terms of the technical outputs, has mainly focused on, so far, knowledge graphs and the ontological in that sense, and not the broader set of issues that I was just alluding to.
Yeah, let's, speaking of winters and so on, let's jump to that. So, you know, of course, their different paradigms become dominant, and then something else becomes dominant, and sometimes, as in fashion, things come back again in a new form or with some new tricks. So now, arguably, it was roughly the early 90s was the end of the heyday of symbolic AI, which was many years ago. So some things have changed. We'll come back to that. But just, on that, what sort of were the obstacles? I'll just list some. And the knowledge acquisition bottleneck we talked about yesterday, Benjamin, which sort of translates to the amount of human participation required versus ML, which really doesn't require much from humans, just collect data. And the computational cost of reasoning, which actually was a big part of what Bob addressed with his innovations, is allowing polytime, but still a lot of other reasoning, exponential, discrete search as a sort of also part of that comes into ILP. Intricacy and just logic itself being pretty complicated, leading to an intricate. And by the way, John, I know we should be talking about symbolic since you're not necessarily in the logic camp, but symbolic overall, I think this applies. There's a lot of fragmentation in logic itself, just because it gets so complicated, and in terms of people working in it, and just the robustness with respect to raw data and noisy data. So anyone want to, and back to something you mentioned, Bob, the Japanese 5th generation project. Why did it lose steam, and what can we learn from that?
Well, for one thing, it got distracted by the form of logic programming that it pursued. It pursued a variant of concurrent logic programming, which moved it away from its artificial intelligence knowledge representation original objective. So that created an issue. And the other problem was that the internet came that's just towards the end, and that changed everything in the same way that large language models and whatnot are changing everything. The internet changed everything at the beginning of the 90s. And it would be interesting to see, to what extent symbolic methods, well, for one thing, symbolic methods failed to exploit the internet. So with all the knowledge on the internet that has been made available to neural networks, had that been made available, for example, to inductive logic programming systems, who knows what might either be accomplished now or might have been accomplished even back then. So that's something that maybe needs some thought.
Can you elaborate on the form of logic programming that was pursued in the Japanese 5th generation project?
Well, the Japanese project was to bridge the use of parallel computer architectures with AI applications, and it identified logic programming and Prolog style logic programming as potentially, let's say, the best candidate for that. But as we've just been saying, there are many forms of logic programming, and the form that was adopted was much closer to the computer architectural level, and it was kind of data flow architecture, which was where the modules, the granularity of the parallelism was much smaller, and too far removed from the von Neumann machine computer architecture. So the whole project got distracted in a sense by the form of logic programming that was chosen, which was much more systems programming oriented rather than application oriented.
I think you're hitting upon a theme, which actually is one of the downstream questions, like about things that can go wrong easily. To create a big effort around, something that really requires arguably some agreement on knowledge representation, maybe. There's so many directions you can go in that if you happen to take a wrong direction, too limited a direction, so it's tricky to allow diversity, but also some amount of unity. But let's come back to that. But you also mentioned the internet changed. So some of the other things that changed since then, this is in the what's now category, which maybe helps explain some of the walls that we hit back then and why those walls might not be there today, or less so. You mentioned the internet or availability of data. Computer speeds I'll throw out too, of course, and with that more memory, LLMs, of course, and coding agents, just general interest in AI. We used to be sort of our own weird community. People are broadly interested. General public is always broadly interested in AI, I think, but now people read about details of AI in the headlines and so on, to a much greater degree. And another one I think we don't think about as much in the AI community is a whole, which you touched upon, Michael, whole parallel development, you could say, in the programming language world. And object-oriented sort of actually, and we touched upon this in one of the talks yesterday, actually can and should be thought of as a kind of knowledge representation, but we don't normally think about that, or at least as much as we should, I think. There's an object view and a relational view, and there's actually, even in the business world, there's some kind of tension between the two. But there's a strain of programming languages which is about type theory, and which actually, it really is a logical view, but through a funny lens, or funny from the usual AI standpoint. It's through category theory, type theory. So, and then you have tools also like Lean, which is, not the same kind of, exactly the same kind of way of thinking, more of a functional programming way of thinking. So, although of course there's a close overlap with, some of the same roots like Lisp and so on. But any comment on what's different now and what we should be leveraging in particular to make progress in the new wave?
I think one thing that clearly there are things like increase in speed. Right? I tried to build a neural language model in grad school. I just couldn't get it to converge because we didn't have computers which were worth anything then. They were just too slow to do anything at all. So that really has changed, and maybe it's an opportunity to scale up logic-based systems. But I think another thing that has changed is that we've got pretty strong evidence now that logic is not necessarily, for many purposes, a particularly good knowledge representation form. I think, one mistake, we're going to get to sort of mistakes were made, right? But one mistake is to become too enthusiastic about a particular kind of formalism, right? And stick to it despite evidence of its inadequacy, right? So for many, many purposes, natural language is a far better, more compact, more efficient, and representation that is perfectly able to be used for quite formal reasoning and argumentation. Now, of course, some people like Jan McCoon recently have been going even further and suggesting that even natural language is insufficient as a basis for building world models, right? And that you need to do these sort of non-linguistically based representation learnings generally. I think that the jury is out on that. It may or may not be the case, but I think one thing that's possible now is actually to train to establish a very much broader range of reasoners, right? So all of the logics, formalized and semi-formalized natural languages, programming languages, things which are kind of amalgams or things which are intermediate between conventional programming languages, logics, and natural languages. All of these things, we have the computational scale to explore now. If we had what we have now, when these initial systems like Prolog or Cycle were being developed, I think that they might have taken quite different forms, and forms which are much closer to these sorts of representations which are natural for people. But that's just a, and I think that's probably pretty controversial in this group to say that logic is not necessarily the solution to all problems, and that it may in fact be a terrible representation language for many types of problem solving. But I think we've got some evidence that might be true now.
Can I just briefly say, you may have missed my talk this morning, but in my talk I argued almost halfway towards meeting what you just said. So I've been advocating the use of what I call logical English, which covers up, let's say, covers 90% of English, but translates very directly into Prolog-like logic. And the main difference between logical English and ordinary English is the removal of ambiguity. And the argument is a prescriptive argument that ambiguity serves no useful purpose in communication. Now that's
interesting. I find it very valuable myself.
I think you're right at some level, because legal language, for example, is an attempt to remove irrelevant ambiguity so that you can run these programs on law students. Right, so I think we can go further in that direction. Since we're both in London at the moment, we should meet for lunch or something next week. There's a lot we could do.
I just want to say very quickly that even legal scholars get confused about what ambiguity means, because there's a notion of vagueness and ambiguity, and vagueness is essential for human language, whereas ambiguity is mischievous.
I'm not sure that it can be entirely ejected, though. I think that's related to the fundamental problems with symbolic representations. That ambiguity sneaks in somewhere, no matter what you do. But yes, minimizing it is very important, and it's related to what I was saying earlier about the utility of contexts.
I have a few comments about the foregoing. The direction of bringing natural language and logic closer together, I think, is very important. And I think we've made a lot of progress on that in the field as a whole since the 80s when Bob kind of, created the scene in a lot of ways from a more practical end viewpoint. I like to think in terms of there being a coin with two sides. One is natural language text, and the other is logical, syntactically formulated stuff. So that a knowledge sentence, the word sentence in logic was taken from sentence in language. So there is a close relationship dating back to the Greeks, really, in the formulation of some of the concepts in logic in terms of being inspired or at least attempting to be close to natural language. But I also think another key aspect is what people broadly talk about in terms of differentiability in machine learning, which is one of the great lessons for both computational and sample complexity in machine learning. And I think we just haven't figured out all that well yet how to make logics probabilistic, but also tractable, also well learnable, and kind of bring all that together in some of the directions that you, Michael, were talking about. I do think that it's a big win, the search aspect, when one has differentiability and continuous kind of stuff, whether it's tensors or it's things broadly speaking that are more like Newton's method, where you can kind of project based on slopes or tangent hyperplanes or whatever. That's pretty important. Embeddings, of course, are very related to that in the heart of modern machine learning that's on the practical frontier. So I think that's something that's really different now as we understand and we have a body of work and evidence of success or potential for success associated with that. So in the Clara program, we're going after that, whereas Codord was more going after integrating with natural language, as I talked about in my talk yesterday. So I also think that the fragmentation in the logic community is tremendous. And Moshe Vardi helped found the Federated Conference in Logic, but it only meets every 4 years. So it's hard to wrangle all those cats onto a single ranch at a given time. And even then, they're often, there were several, I think, a dozen events at the Federated Logic Conference. So getting the logic and knowledge representation and reasoning folks to kind of talk across their fragmented subcommunities is very important. And I just would make an observation, which is the world is dominated practically in enterprise IT by a single logic family, which is declarative logic programs, whether it's databases, it's ontologies, it's rules, whether you're talking about the standards or the main kind of product type of implemented stuff that people run. 99% corresponds to the LP family. And that single fact does not seem to cut much ice with the people self-funding and self-directing within the logic community about what to work on. Whereas in some other communities in IT research, the fact that there is a single center cuts a lot of ice, and people go, hey, I shouldn't go so far from the centroid unless I make a pretty clear and strong argument for why, to justify why doing so should be funded. Now, I'm not saying there isn't an important need for exploration and these logics that are non-LP as well as non-classical, but I think there's something we could do about it as a community, which is kind of vote with our feet.
So normally I try to stoke a bit of healthy fighting on panels, and hopefully a little bit of controversy and drama for excitement. Anybody want to participate in that?
Let me again meet John this time halfway. One of the things that cognitive models have been very important for logic programming in particular is that they have been quite inspirational, certainly in our work on logic production systems and abductive logic programming. And one of the issues I think that hasn't been addressed in general is the relationship between descriptive and prescriptive or normative models of thinking in general. So cognitive science, as I understand it, is interested in how humans think, not how they can think the best practice to think better and to be more rational. But if it's possible to take the way humans actually do think and make them and help them to think better, then there's got to be a relationship from where they are thinking the way they do to where we might want to promote and advocate that they go to help them to think better. So there should be an alignment of some sort between the cognitive models that psychologists study and the kind of knowledge representation and problem solving models that symbolic AI develops to try to develop more intelligent machines or for that matter, more intelligent humans. So that's a research agenda I'd like to propose that might bring the cognitive psychology community and the logic-based AI community talking with one another a bit more frequently than they do today.
I think that's a very important point. And like, irrespective of whether you think teaching people logic is going to help them to become better at thinking, or us as humans to become better at thinking, it's a responsibility, I think, of AI to work out, now it's happening, right? How it integrates with what people do to improve the way we work as a society. So thinking about, maybe not about how we can change the way people think, but how we can make sure that this system that we now have, when we have AI systems and human beings working together, how does that lead to better outcomes, right? How does that lead to more rationality or more fulfillment or more humanity? I think that's I think there's an enormous amount which can be done in that area, and now we have an opportunity to do it.
So this is a big question, and I would want to think about it for a few days before giving it a complete answer. But number one, I still think humans are pretty good. And so being able to understand how they think, the way they think, and I think that goes to what experiences they have in the world, and also what hardware they're built out of, but also the structure of how that hardware is organized. It is not a feed-forward net. It is not anything close to what a transformer looks like. But to understand how that then produces the behavior we do produce, I think is a really important step. I also think that creating tools for how we interact with systems that take advantage of human strengths, but also understand what humans don't do well, can make humans better in terms of more intelligence or part of our overall society. So we have a huge number of biases. Confirmation biases is one of them, is that you tend to believe you tend to interpret the world in terms of what you already believe, and that then when an event happens, you say, oh yeah, that's because of what I already believe, as opposed to looking at alternatives. And that's just one example, but there's all these biases that probably have turned out evolutionary to be very important, but we're in a different world than we were 100,000 years ago or 50,000 years ago. And so understanding where we have these biases and getting good models of human thinking, and then asking how can we take advantage of that, and how can we take advantage of what our tools produce, I think is really, really important. So I'm not sure that means necessarily driving people to learn logic, or making people more logical. I think there's a lot of the reasoning we do which cannot be logical because we don't have enough information. And maybe logic handles that, but I just think that in certain ways, but I just think that this is a really interesting question. And I'm hoping that it is on the agenda in the future. I'm glad you guys brought that up.
All right, in the last chunk, let's look to the future with clues from the past. So lessons learned, what even back then, maybe as a field, some things weren't done in retrospect as much as they should have been done, or you hinted at a little bit of that, Bob. But what should we have done differently as a field, symbolic AI, as a and particularly going forward? Well, even back, I guess there are two parts. Back then, even looking at things, just for some clues, like how the field kind of acted in its unity or lack thereof, or working styles or patterns, or its the relationship to the general public or industry, incorporation of ML, which was just emerging. So there's a good reason why that wasn't done as much. But use of benchmarks, which is heavy today, anything like that, or anything else, what could have been done differently back then, or at least now?
We could have actively suppressed confirmation bias, and in particular, we should have worked very hard not to be angry when things from other parts of AI started working and it wasn't ours. We're still failing at that, by the way, in symbolic systems. But, yeah.
So my view is you got to look forward. You can't dwell on the past. I mean, we should learn from the past, but I think there's huge opportunities for integrating symbolic AI and generative models. So I just think there's a lot of things we did right in AI. I think there's a lot of problems we looked at, but we didn't appreciate the value of data, and that means that we have to have intermediate representations of our processing the data that is not going to just be logical statements or something, because that can't capture the complexity of what's in the data. So there was a project called NEL, Never Ending Learning, that Tom Mitchell did at CMU, which I thought was great. And they tried to process everything that was coming up on the internet every day and learn from it. And he probably did a post-analysis on why it didn't end up learning chatbots. But I think part of it was that they were constraining the way they were thinking about learning. So, but maybe, Michael, you know more about it. But I think there are all these opportunities now to take advantage of what we've learned in symbolic AI. And so one of my, this is me going off on another tangent, which is, sure, there's neural systems, which are the implementation technology that seems to be very valuable. There's the cognitive side, which is sort of symbolic reasoning, which should, I think, be built out of neural processing at one level, that there's some aspects that we want to look at how can we do reasoning at this level using that. But then there's all these other things above that we don't talk about enough. I mean, people talk about planning and things like that, but meta reasoning, explanation, that sort of comes in very late in the game because it's not easy to do with the current system. So I think one of the things we have to do is push to say one of the great things about symbolic systems is they did run fast, is that let you do explorations with what I would say were approximations of what we now have with neural systems. And so you could do explorations, and being able to learn from what those explorations were, see if we can incorporate that back in, is what I see the future is. And one of the big parts of that is online learning. It's so sad. They just don't even try. I mean, they have some databases off on the side, they sort of store some things, but it's sort of like, well, if I have 1 million things in my context, that's going to be good enough. It's like, no. We
do try. We just haven't succeeded yet, right? I mean,
all right, fine. That is I will be quiet now.
Well, I have one kind of direction that I think we can relate to the past as far as the lessons learned, which is logic has this kind of idea of abstraction as a kind of, inverse of specialization or subsumption. And that needs to be related, I think, in a more rigorous and substantive way to generalization in the sense of inductive learning that's data and statistics, oriented or whatever. And crucially is approximate, as well as I mentioned earlier, differentiable. And I think that's not only an opportunity, but a need today in terms of taking advantage of those opportunities, John, that you were sketching. I thought you did a good job on that. I particularly resonate with both meta reasoning and explanation because I personally have worked a lot on that, and it's a lot
Come
of
on,
what
let's
we're
start
doing
a
in my
few darker
programs.
programs.
Yeah. Okay. Yeah. Anyway, so I do think though that the idea of also making more rigorous what constitutes a strong or kind of useful explanation, including in the context of engineering of systems and what are effective methodologies that are not only affordable, but say reduce the cost of testing, help manage to keep affordable DevOps, where it's over the life cycle, you're making changes to your knowledge, partly due to changes in the world, maybe because, and in a way that will have humans in the loop in a way that is more flexible than just the usual ways that they're incorporated in machine learning. I saw, John, you made a face when Alex said, well, ML doesn't use humans participation. Actually, it really does. Who generate all that data that the LLMs are based on? Humans are absolutely crucial. Yeah. Anyway, so I'll leave to you, John, to elaborate on that particular aspect if you want to. Yeah. But I think that's something a lot of people, they treat ML as magic. And they don't recognize how it's a way of capturing human knowledge. And actually, in a lot of ways, a very debased and kind of sippy straw, kind of thin way of taking advantage of the fact that humans can state their knowledge and remember it, for example, and use it cognitively in considerably more generalized forms than what the ML systems gathering data historically did until able to mine large quantities of natural language, which itself was the main form in which humans were stating often their more abstract level knowledge. I also think that the relationship of ambiguity, if you care about ambiguity, you should really care about logic and symbolic methods. Why? Because the premier tool in IT and philosophy and cognitive sci for composing effectively partial knowledge is logic. That's what it's all about. So ambiguity just tends to get called out when it's in the foveal field of, some particular task that you're concentrating on. Maybe it's an engineering task. But in a lot of other settings, ambiguity is crucial because you only have partial knowledge, which is how I would state some of what restate a lot of what John was making in way of comments about that. So ambiguity is absolutely central cognitively, representationally, and logically, and therefore symbolically.
I think we have to define what we mean by ambiguity. Your term
Partialness of knowledge.
I wouldn't say it's ambiguous. I would say it's vague. Your notion of ambiguity is vague.
I like to think of it as partial knowledge. And then we have many names for it, depending on the context.
And there's a lot of misunderstanding over terminology, ambiguity being one such term. Okay.
So Bob, what would you say? We've got a hungry young generation, young and old, but new wave that is gaining steam as usual as a reaction to the current paradigm. That's how you get the next paradigm. And a lot of people, I think, are understanding their key limitations to the current paradigm, and essentially, effectively coming either by reinvention or something else to the same issues, so that were addressed in many deep ways, but maybe not always in the symbolic AI heyday. So, what would you advise this new wave, and as far as active shaping of the field based on what you've observed having happened?
Well, I think no matter what happens to AI, the big problem is going to be how humans can learn to live with it. And one way to make it easier to live with is to make it more aligned to the way humans ought to think, not just how they do think, but how they can think when they're thinking at their best. And one way to do that is to make AI systems more like we strive to be, more like we can understand in terms of goals that they're trying to achieve, the alternative ways they've considered achieving those goals. What evidence do they have for the information that they're providing us with? What are the valuations that they've made to come to the judgments they've made? And this is the way we ought to think, and it's the way AI systems of the future ought to be more concerned with, to make it easier for us to control them rather than for them to be controlling us and treating us like pets. So I think we have to focus more on people and making AI systems respect us a bit more than they do today.
Michael, just to close, I think you threw out, to me, something I believe in a lot, which is openness to, foreign ideas. I think, maybe that was, I'm not sure if that was an issue in retrospect, but at least now, I think we really do have a lot of pockets within neurosymbolic, within symbolic, within ML, and then within the combination of the two. So, but there are also things that actually lie outside of AI even that I think get particularly little attention. So that would be my, so I really like what you said about that. Last word, anyone want to throw out a last thought?
I want to throw out a last thought. And
Yeah.
that's what we could do very productively in our field is to double down on what has happened with lean and mathematics, right? And try to generalize that, right? So lean and the libraries of theorems, right, which are encoded in it, have made it possible for systems to get very much better at mathematics. I think that we should aim at a synergistic project to build larger and larger consistent or locally consistent theories that then can be used to train models, which then can be used to build larger and larger theories and use these sorts of formal properties. And even new formal properties, new languages, in order to build those sorts of systems, because I think that's an opportunity to do something, for example, in understanding biology or physics or economics, sort of modeling that's really impossible, has been impossible for humanity so far. And it's one where, the purpose of logic in philosophy was to allow us to think better, right? So a synergistic system like that might allow humanity to think better. So Ben, start a program.
Well, first of all, I want to make clear that my remarks on the panel are not me directly speaking for DARPA, which is normal on panels, but I think it's worth saying explicitly. But I agree with a lot of the directions you were talking about there personally, Michael. And I think there's a kind of meta level for younger researchers, which is in the era where ML and particular neural nets have come to dominate, there's a certain laziness of training that's a ineluctable tendency. You learn about calculus and linear algebra as part of your general STEM education. You have to seek out the resources to actually learn about practical or kind of centrally important forms of logic, not only classical, which gets treated some in computer science, normal curriculum, but also declarative logic programs and some of the other ones around probabilistic. And So I would just say, invest that effort.
Okay, we are eating into the break. Luckily, we have a 30-minute break. But I'll just use the last few minutes to take a few questions from the audience. So one, can logics replace some part of weights and biases in AI?
Yes.
Go ahead.
I would say that the themes of meta, of probabilistic, and in the broader sense, including not just Bayesian uncertainty, but say fuzzy style uncertainty, often formulated in terms of triangular norms. Or there are other kind of weighted forms of logic, such as Markov logic nets. They're very much exactly in that direction. So there is quite a bit of work that's addressed trying to do that. It's not very fully satisfactory at this point, but it's clearly pretty important, as is the whole direction, largely coming out of researchers who worked in the 5th generation, ironically, towards linear algebra formulations with real valued tensors, basically, to represent logical reasoning and logical knowledge.
All right, one last one. How humans ought to think is hard to define, even if it's possible. Anyone want to address that?
Well, one example is decision theory addresses how we ought to evaluate alternatives, and it teaches us that the more options, the more alternatives, that the more knowledge we have about alternatives, the more likely we are to find a useful option. So if you put decision theory into context, you need logic in order to evaluate the consequences of the alternatives, to determine in turn what the utility of those alternatives are in practice. So we do have, and there's a tradition outside of logic in decision theory, which does concern itself with how humans ought to think to make better, wiser decisions. And logic, of course, is involved in any kind of scientific understanding of testing consequences of theories to determine whether they conform to the evidence. So how to do proper science, how to do proper decision making, all of these require the ability to derive logical consequences of assumptions. And logic has other useful purposes for determining what those options are actually might be. That's where abductive reasoning comes in particular. So I think there is a tradition of understanding that logic can help us to think better, to make better decisions, but that tradition has not been exploited adequately. We've lost track of the fact that logic was developed for humans, and we've employed it for studying the foundations of mathematics, for coming up with very clever, complicated theories of computer science and knowledge representation in AI. We've let humans go off on their own feeble way with very little guidance.
So yeah, as a last point, this relates, I think, to, in a way, another difference in opinion that's implicit, because some people actually defend the errors of LLMs and suboptimalities by saying, well, it kind of this is acting like humans. We're not perfect, and so
kind of imperfect.
Right.
Planning is joined at the hip to decision support. So if you have normative decision theory, the kind that Bob was referring to that's been studied, part of the challenge has been that working out the logical consequences in a way where you can plan over multi-step, or when you have a lot of uncertainty about the environment or what's going to happen, is computationally and sample-wise pretty complex. And that's, I think, why people sought the easier formal grounds of, focusing on computer science itself as the realm for applying logic.
So there's a lot of talk about super intelligence as a goal, and presumably that means being better than humans at.
Humanity certainly needs to be better at thinking, right? Whether individual humans do or not is not at all clear. We've been always building systems to make ourselves better at thinking, including logic, right? So we could communicate through generations more effectively about types of reasoning errors we might make. So I think, really there's an opportunity here to make humanity very much better at thinking, including by scaling up logic in ways that humans couldn't possibly do.
I think this is very timely, as many people are now worried that the current technology is making people worse at thinking. So, so great. We'll end on that positive note. Pro-humanity. So this is the place to do the right thing. Neuro-Symbolic AI. Thanks to everyone. Really appreciate it. And we'll catch up with everyone probably in another setting soon. Take care. And now the break. See everyone.
Bye, guys. Thanks. It was a lot of fun.
Thanks, everyone.
Thanks, everyone.
Thanks, Alex, for organizing it, and everybody else for participating.
No, thank you all. Take care.
Thank you. Bye.
Okay, welcome back, everyone. And next up, we have a great tutorial on, in a way, the hardest, most complete AI problem and how Neuro-Symbolic AI is enabling that. So welcome, Emre, and by that I mean robotics. Take it away, Emre.
Okay, thanks a lot for the invitation. So let me share my screen. Okay. So today I will try to give an overview of neurosymbolic approaches in robotics. So because I was requested to give a tutorial, then I tried not go into details of each study, but try to give a general overview, which describes how these neural and symbolic approaches might be combined in different robotic systems. And so this tutorial will be based on a recent paper of ours, which is titled Neuro-Symbolic Robotics, Capabilities, Limitations, and Challenges, which is going to be published in IEEE Transactions on Cognitive and Developmental Systems. Okay, so my name is Emre. I am from Boğaziçi University, which is located in Istanbul, Turkey. And then I lead a lab which makes research in the intersection of cognition, learning, and robotics. Okay, so this is a introductory slide. Probably this is not required for this summer school, you have seen a lot of stuff on the combination of why neural networks are good, or on what neural networks are good and symbolic systems are good, and so how they can be combined and stuff like that. But still we have these two worlds that need to be connected. And neural networks in robotics as well. So they are good in learning, adaptation, and emergent robot behavior. And lately, through these large language models, they start becoming good in reasoning and communication. But we all know that they suffer from being black box and adversarial attacks, and they are not verifiable and explainable in general. And extrapolation is almost impossible with them because they are neural networks. Okay, symbolic systems, on the other hand, they are nice, verifiable and explainable, and they can be used efficiently in planning and reasoning. But it is difficult to ground these symbolic systems in the robot's perception and control system. So how can these two worlds be combined? Okay, our survey starts with this search on the number of papers that has been published related to neurosymbolic robotics. And as you see, there is an exponential growth. Probably there is something similar in neurosymbolic AI as well. But so this survey was specific to robotics. And in robotics, we have seen this exponential growth. My feeling is this neurosymbolic AI has recently been become in the radar of the robotics researchers, probably because of the success of the neural network systems, but also their limitations. Anyways, so there are so many works in neurosymbolic robotics, but as I will present, we don't see a general architecture that can capture all interesting and useful properties of all these systems. Okay, so when we talk about robots, in general, robots have their perception and action. And then they interact with the world through like physical interaction and communication as well. So what we need to do is, so we need to understand how this, within this cycle of perception, action, and planning, so how these neural and symbolic processes can be organized such that the robot can learn, perceive, reason, and act in the most efficient way. So that is the question. And for this, so when we were going over these neurosymbolic robotic works, of course, they do not label themselves as neurosymbolic robotic. So this is also kind of emerging terminology, I think. But what we have seen also, we were inspired from some other surveys on neurosymbolic AI when we were creating this taxonomy. So these engines, let's call them engines now, symbolic engines and neural engines can be related to each other in the robot control system in different ways. So we can maybe categorize into that into 4 categories. And I will go over each of them one by one, giving some examples. But basically, in the first category, each of them, I mean, one cannot do without the other. In the second category, they are loosely connected, which means that one can function without the other. In the third category, one system that is represented in for example, symbolic engine is transferred to a neural engine for their desirable properties, and there is this fourth category. Okay, so this is not only categorization, but it is a taxonomy. And here you can see these four main categories, and there are some other subcategories as you see here. The first category, the one where both engines should be running in order to control the robot, in order to function the robot, has more subcategories because we generally look from, me and my colleagues, we look from more cognitive and developmental perspective. And in that sense, we went into more details on how the symbols that are generated by the neural networks can be efficiently used. Okay, so let's go over these categories one by one. The first category, in the first category, the robot makes reasoning and planning using the symbols and rules that are generated by the neural engine. So why is this important? Because these rules and symbols, we need to have their grounding in the sensory and motor space of the robot. And in general, it is not possible to hand code this grounding between like camera or sound or motor actuators to the symbols. And we need the learning power of neural engines for that. And there are again some subcategories in this main category. So the first one, this is probably the oldest approach. So what people were doing was they were hand coding all the symbols and all the rules and all the operators, which means that they are hand coding all the domain knowledge manually. And then they would like the robot to function with those symbols, which means that those symbols need to be grounded. And for that, they take information from the environment, and they were using supervised methods to learn the mapping between the sensor motor world of the robot and predefined symbols. So this is the oldest approach, but of course, I mean, people applied this idea in many different environments, but this is a problematic case because it is very brittle. I mean, if the robot goes out of the environment where that domain is designed for, then it's not possible to generalize this. So it is so this system might work only in very well-structured environments, but it is very rigid, so it cannot be flexibly learned, for example, new symbols, because the symbols are predefined. So there is no room for learning new symbols. In the second approach, the grounding now is not learned, but it is given. What the robot needs to learn is it needs to learn the list of the predicates of the operators. Operators are also predefined with their preconditions and effects. in operators, we have list of preconditions, or list of predicates for preconditions and list of predicates for effects. And in these studies, these predicates are not given. And what the robot needs to do is it takes observation from environment. It might be like demonstrations. And then from these demonstrations, it learns the set of predicates in the preconditions and effects using different learning algorithms. Here there are a couple of examples. And you can see the full references in the main paper. So this is again fine, but there is again no room to invent new symbols, because maybe there's a novel environment where the robot needs to discover a completely new symbol for its planning and reasoning, and there is no room for that because grounding is already given. So what I am also very interested in is instead of predefining the symbols, how can we let the robot discover the symbols itself? So the robot has its own continuous experience, sensory motor experience, high dimensional and composed of real values. And then we would like the robot to organize it into discrete symbols that are effective for planning, for reasoning, but without any human intervention. And this is much related to probably how humans develop categories, concepts, and symbols in their first 2 years of infancy. So I like this figure where the robot has no idea about the objects on the left, and then the robot makes exploration, and then after making sense of high-level symbolic knowledge of these objects, then given a goal, the robot can make some very complicated plans. And then for this, like the researchers, including my group, we are very interested also in how so let me okay. Here we see, actually, when I run it, there is the music. I don't want the music running. But there is this 9-month-old infant exploring the environment with its behaviors discovered up to that point, and learns categories of objects, which objects can be graspable, which objects can be liftable, pushable, and what it can do with those objects and stuff like that, without any human or parent or caregiver intervention. So we would like to achieve this in the robots, and this category is related to that. Okay, and so in this category, we don't want any human intervention, which means that the robot needs to make sense of its interactions with the world itself. How can it achieve this? So the robot has observations from environment. The observations might be coming from cameras, or might be coming from tactile, or maybe microphone sound. And so the question is, how can the robot generate some symbolic information, discrete information from this data? And the first idea was to use simply clustering techniques. If we apply clustering, unsupervised clustering, then we can obtain categories, and those categories might be used for some purposes. So this was the initial idea. People explored a lot using some Bayesian methods or some more neural methods. We also had some work on that. So, which is fine. You can generate some object categories or object symbols using unsupervised clustering. But the question is, or the problem is, there is no guarantee that these categories or these symbols will be helping the robot for downstream tasks like planning. Because these symbols are formed not based on, not taking into account any planning objective. It just generated those symbols in a completely unsupervised way. Which is why in the kind of next steps, what we can do is we can force the system to learn symbols that are effective for one-step action prediction, which is the atomic step of planning. And on the right, you see a neural network architecture, simple one, which corresponds to our deep sim architecture, simplified version, where input, the current state, is encoded in a binary bottleneck layer, which should be able to generate the effect of an action. In the previous case, the effect was not playing a role, but now this neural network should be trained such that these binary bottleneck symbols are effective in predicting the effect of the action. Okay, so let me give you a bit more detailed overview. Let's say that the robot explores the environment and then it has some actions and it is taking snapshots of the interactions before and after executing the action. So what it has is, it has the high dimensional continuous observation like images. And what we would like is, we would like these images to be transformed to discrete codes that can be used as symbols. But these discrete codes should be effective in predicting the effects of these actions. So in this way, and with this encoder-decoder architecture that takes the initial image as input and makes a prediction of the effect and uses these discrete bottleneck activations, this architecture can be used to transform continuous information into discrete symbolic information. And then in this work, what we did was, after finding the symbols, object symbols and effect symbols, these symbol effect predictions can be converted to symbolic predictions, which can be automatically translated to PDDL, which can be used for planning. So if you're interested in this work, so this was our base work. Okay, this is nice, this is fine. We were very happy with this work, but there is a problem with this work. The problem is, so the symbols are optimized or are discovered based on the optimization criteria of performance on one-step prediction. But what we would like is, we would like the symbols to be effective in planning, not only in one-step prediction. So the next category deals with that. In the next category, the idea is, the symbols that are good for one-step prediction might not be good for long horizon plans. So what we need to do is, we need to optimize the symbol discovery based on their performance on the planning performance. And again, there is very recent work on these symbols optimized for planning. People use different techniques. But yeah, you can imagine this as an optimization problem. Like there's a system that generates symbols, and the optimizer gives feedback based on the performance of those symbols in plan generation and plan execution, which is probably the way to go. So I think we need to have symbols. We need to discover symbols based on all of this, based on reconstruction performance, based on one-step prediction performance, and based on their planning performance. And up to now, these studies were mostly discovering perceptual symbols. Also, of course, we need action symbols, action categories, behavior primitives to be learned as well. So because we would like our system to start maybe with motor babbling or something, and then nobody says our robot, this is a push action, this is a grasp action, this is so we would like the robot to discover all these actions by itself as well, like infants, like children do when they are young. And of course, there are some other studies which work on action symbol emergence as well. Some of them, maybe none of them call this action symbol, but how they use these actions in general is in reinforcement learning frameworks. They can use these discovered actions as operators, which corresponds to symbolic manipulation. And in that literature, option discovery, for example, is an important research field where actions are discovered in different hierarchies. So low-level actions and then higher-level actions, and maybe even higher-level actions are being discovered and used and chained later. And finally, of course, not only perceive, not only action, but both of them, both the symbols that encapsulate both percept and action or sensor-motor world of the robot should be learned. So this is the most general form. But this is a very difficult and challenging problem because so many studies who discovered percept symbols, they assumed existing action primitives. And many studies who worked on action symbol discovery already assumed things like object categories, object symbols. So it is difficult to achieve this symbol emergence in the perception and action system together. Yes, so this is a challenging topic which we also try to work on. And maybe the final category where neural engines generate something that is used by symbolic engines is when the symbolic engines write neural engines write symbolic programs. These days, large language models might be used for that purpose. Large language models, they are neural engines, and they can be used to generate prolog code, which can be used to generate behavior trees and which is executed on a robot. Or maybe, not maybe, but each of them has their references. Large language models can directly generate PDDL consistent task plans, which can be executed by the robots. And so this is also a very popular topic these days. So in robotics conferences also we see this kind of work now recently. Okay, so this in this category we saw that there was a strong perception to symbol pipeline that was learned, and the symbols were effectively learned for long horizon planning, and they can be used in a modular fashion because they are symbols. We can also give labels to them, and then these systems become interpretable. But these are robotic systems, and of course, robotic systems, they require robust control, motion planning, which are not covered by this line of work that I just mentioned. Additionally, even though like these symbols and operators were generated, safety and robustness were not addressed in this work. So people, including us, we were only mostly focused on planning and plan execution, not much safety and robustness. Okay, so in my opinion, this category is the most interesting one, and I'd like to continue working on this category, but let's talk about the other categories as well. Actually, the next category is becoming more and more popular thanks to these foundational models. In this case, we have a neural engine, and then we have a symbolic engine. They can run independent of each other, but their advantages are combined. So let's go over them one by one. So one of the first works that combined these kind of neural and symbol engines were a system named SEICAN, where a large language model was proposing an action sequence, a plan, and then there was another system, neural system, which already learned these behaviors, and then which behaviors are applicable in which environments, which corresponds to it learned also affordances. And the plans that were generated by LLMs were verified by this neural network-based grounding and filtering, and then executed. So can the robot execute this plan without asking the neural engine? Yes, it can, but maybe it is not very well grounded. So their strengths are combined in this case. But they are kind of fully independent and balanced. So there are other ways of supporting one engine, supporting the other one. For example, in this case, the workload is on symbolic planner. Symbolic planner is given a goal, and then it generates a plan, and this plan is executed. So, which is fine. But then some people suggested that we can or they can use the neural networks which help symbolic planner to more efficiently generate these plans. Like, I don't know, it predicts the feasibility, or it gives some values to some actions and stuff like that. Because these systems, in these systems, the symbolic planner is the leader, verifiability is always on the front, and these systems are good candidates for safety-critical deployment. So we can have the opposite support as well. So we might have neural controllers that control the robot for some particular tasks. These neural controllers probably they learned from maybe reinforcement learning or from learning from demonstration. But in learning, for example, in exploring the interaction and learning space, the symbolic engine and symbolic knowledge might guide the robot to learn, for example, more efficiently, to select which action to take while learning, while training. Or it can give reward signals to the reinforcement learning system, which is based on, which is running a neural controller. Which means that in these two systems, one engine is helping the other one to be more efficient. And there is another category where the information in one engine is transformed to the information in other engine. So we included these studies because they appear in Neuro-Symbolic AI systems, but actually the robotics people, they are not aware, or they don't probably they are not aware much of these kind of systems, which means that in this category there are not many robot and robotic experiments. So this category is nice. Why? If we have neural networks are very good for many different things, but they are not explainable, they are not verifiable. If we can distill it to a symbolic policy or a symbolic engine, a finite state machine or something, then it becomes verifiable. And this verifiability is important for safety critical applications, and it becomes ready for this kind of applications in principle. But I'm not sure how scalable these systems are for robotic tasks, because robotic tasks have their own difficulties due to the huge sensor motor and exploration space. If it is possible or not, I don't know, but I think we need to keep an eye on this kind of approaches. Of course, we have the opposite case. We have systems where symbol engines are transformed to neural engines. And again, these approaches are not used in robotics, unfortunately. So we need to take them into our radar. And probably these are open problems for roboticists. Okay, and then we have the case where the boundary between neural and symbolic blurs with these vision, language, action models. Now, in robotics, we have these multimodal systems, where not only vision and language, but action is also used, and action is generated using vision and language input directly. So there is no intermediate process. The robot takes the command and it takes, I don't know, the goal, it takes the image, and then it generates an action. Action corresponds most of the time the displacement of the, for example, gripper at each time point. And some people say that this is the way to go. If we have sufficient data, then probably we will have a success similar to large language models or vision language models, which I'm not sure, I don't know. But still, if you check out, they work. It looks like they work very well because you can intuitively give any command, and then so even though the motion execution trajectories are not very smooth and very complex, still it looks like the robot is executing the required actions. But again, this is a end-to-end system which suffers from the problems on guarantees. And there are some precursors where so machine learning techniques were combined with symbolic operations, not necessarily neural machine learning, but other type of machine learning methods. And people have been, of course, working on these topics as well since a long time, even in robotics. Okay, so let us now summarize what we have seen. So because robotics, with robots, we would like to achieve goals. And in general, goal is achieved by action sequence. Then planning is required. And if we check out the studies in robotics, almost all of them deal with or address multi-step planning. So this is the driving application. But for example, safety is not, interestingly, is not too much in the focus of robotic researchers. Yeah, maybe robotic application people, safety is important. But the cross-cutting research in neuro-symbolic robotics is not taking safety seriously, or let's say that has not been taking it seriously, but of course the people are pushing the researchers to take it more seriously, such that it can be more applicable in the industry. So most of these studies used real robots, and if there is no real robot, simulated robots, which is in general fine. And of course, the ratio of large language models are becoming more and more in these studies. Okay. So, as I explained, with these large language models, the distinction between neural and symbolic divide becomes difficult to distinguish, which we might discuss separately. But in general, the general trend is not to use well-established symbolic systems, but it is to force the LLMs to make reasoning using mechanisms like tree of thought reasoning and stuff like that. Okay. So what are the open challenges? So there are several open challenges, of course. So let me start from both. It is an open challenge, and because it's an open challenge, it is a future direction. So we have embodied symbols that are discovered or learned by the robots. So we can call them bottom-up generated symbols acquired through interaction. But we also have top-down linguistic symbols coming from large language models and maybe already existing knowledge bases and domain descriptions. So this gap should be bridged somehow. And I think this is a very nice open challenge and very immediate open challenge in neurosymbolic robotic research. What else? I described when I was explaining the different approaches, I mentioned that safety is not the main focus of most of the robotic researchers somehow. The nice properties of symbolic systems, like interpretability and verifiability and stuff like that, needs to be integrated into robotics in safety critical domains. And maybe this is where one of the most important values reside of neurosymbolic or symbolic systems in robotics. And this is also one of the most immediate challenges in my opinion. So one other maybe challenge or one other immediate future direction is might be, so there are some very successful neurosymbolic AI systems like Deep Prolog or Logic Tensor Networks or Neuro-ASP that has not been used or explored in robotic problems. And I think this is also one of the most immediate things to do because they are very successful on their respect. Okay. So in this talk, I try to give you an overview of the robotics research where neural and symbolic systems combine. And mostly I focused on developmental and cognitive systems where the symbols are not given but learned, discovered by the robots. But as you have seen, there are different categories. Each of them are good in some aspect, but there is no single category that can dominate, that is good in all different aspects, like verifiability, safety, adaptability, generalizability, extrapolation, and stuff like that. And I feel like this is a very exciting area for robotics researchers. And I hope that more robotics people will be involved in this research. So 45 minutes. Thank you very much for your attention.
All right. Thank you so much, Emre. I think a sign of a good tutorial is the question I was going to ask. You answered it already and very well at the end, which is where do you suggest the field look to the future? So I think great job on that. Unfortunately, we're out of time for questions, but check out Emre's work and his group and the many things he references. I think this is an excellent collection. It's a lot more than I expected, actually. So even though we work in neurosymbolic robotics, so good job spanning the space.
Thanks a lot.
Okay, thanks, Emre.
Thank you.
Hey, Dylan.
Oh, hey, Alex.
All right, welcome back. So those of you who've been following our Neurosymbolic Wednesdays may remember Dylan, who spoke not long ago there. We usually don't like to have a lot of repeats. There's so much to cover, but when it's right, so happens Dylan has another thing we'd like him to talk about. So, and this is very closely related to the last topic, and I think really important. Sequential decision making as combining learning and symbolic inference ideas. So with that, take it away, Dylan.
Okay. Yeah, thanks, Alex. Guess I'll share my screen. Cool. All right. Yeah, thanks again, Alex, for the reintroduction. Hello, everyone. My name is Dylan, and I'm delighted to present to you our tutorial for the 2026 Neuro-Symbolic Summer School on generalized planning, more specifically, learning to plan over symbolic world models. And QR links to these slides, as well as a previous 3-hour iteration of this tutorial with more depth and approaches presented at the ICAPS 2025 conference, are presented here on the screen. So without much further ado, let's get started. So again, today we'll be talking about planning, specifically AI planning in the symbolic sense. And planning in the AI literature is a very overloaded term. So we'll first narrow down its definition. So we can begin by asking AI for a consensus of what planning means in AI research. And you can divide this into both the problem and the methodology. So planning is associated with the goal-oriented sequential decision-making problem, meaning that one usually needs to find sequences or sets of actions or policies to achieve a desired goal. And methodologies for planning usually require reasoning about future consequences of actions to achieve such goals. And planning has many, many applications in the real world, with some shown here. As Emanuele has just talked about, there's a lot of applications in robotics and autonomous AI, for example, space exploration, disaster response, household assistance, and also more like everyday industrial tasks like logistics and delivery. And more formally, we can define a planning problem as a given set of inputs and outputs. So the inputs you get for a planning problem is usually a set of states, set of actions, an initial state, and a goal condition. And we have goal states, which are states that satisfy your goal condition. And what you want to find for a given planning problem is either a plan, which is a sequence of actions, or a policy, which is a mapping from states and goals to actions. And you want this plan or policy to achieve your goal given from the initial state. And it may be optimizing one or more cost-reward functions subject to some constraints or preferences. And as you may or may not learn in usual computer science course, planning can usually be viewed as a search problem, because a planning problem induces a graph where states correspond to nodes and actions correspond to transitions or edges between nodes. And what you want to find usually is a path or plan from the initial state to a goal state. And usually these search spaces grow exponentially with respect to certain criteria such as depth, breadth, and complexity. For depth, for example, if you have longer horizon sequential decision-making problems, you have deeper search trees. And you may also have wider search trees resulting from many possible actions you can take from different states, such as in cluttered environments. And you may also have very complex problems where you may have stochastic environments or open world environments or partially observable environments where you need to reason over memory and history. But the point I want to make here is yet we as humans plan all the time in very large state spaces without much effort. So for example, when you're cooking, the goal is to try to make yourself full. And you have a usually pretty big search base. There's a lot of different ingredients you can buy or use in your fridge and to combine together to cook your meal. And you may want to optimize for certain metrics such as taste, healthiness, and cost, and speed. Commuting is a very prime example. For example, the state space is very large. It's like, I guess, the entire Earth. Yet we don't really spend much time thinking about how to commute to work. We usually take the same routes with the usual set of kind of mode of transport. Similarly, for trip planning, there's a lot of different places to stay and visit, different modes of transport, and we may be constrained to some budgets. So in this tutorial, we're going to look at, how do we design systems that can plan efficiently, like humans? And the answer we want to get to is through like a combination of experience and reasoning. So kind of, you can view this as symbolic, being associated with reasoning and experience coming from learning and neural networks and so on. So just to kind of set the stage for this tutorial, we're looking at generalized planning, learning to plan over symbolic word models. Experience comes from learning, and reasoning comes from using the usage of symbolic word models. And we're going to talk about kind of two different methods for generalized planning. We're going to look at some neuro-symbolic methods for planning over symbolic word models. And we can't ignore like the usage of large language models as well for planning. So for section A, we're going to look at heuristics and policies. And for the large language model section, we're going to look at different uses of language models for planning over symbolic word models, and also like the progress of LLMs in planning and what we can try to take away based on the progress in the past few years. So now let's talk about what I mean by planning with symbolic word models. So word models in the AI literature usually refer to a function that's conditioned on a state and an action and tries to predict the next state based on applying that action on your current state. And with symbolic word models, we can give a closed form definition of this function. And more specifically, we use this, we represent these symbolic word models in a formal language, such as PDDL, as discussed earlier. So we can usually represent states as relational databases consisting of facts and objects. For example, the state consists of the dog at the kitchen and the dog being hungry. We also have a cake in the bedroom and a robot in the bedroom. And we can also represent actions using symbolic preconditions and effects in the first order fashion, in the sense that these actions are parameterized by variables. For example, in this put down operator, we have objects and locations that can be instantiated with arbitrary objects. And our objective here is to find a sequence of actions or policy, as we discussed before, that achieves a given goal condition. So for a simple example where we have this given state and a goal, in this abstraction we can find a simple three-step plan that achieves the goal as follows, where the robot picks up the cake, moves to the bedroom, from the bedroom to the kitchen, and puts down the cake in the kitchen. So with the preliminaries aside, let's talk first about how we can learn heuristics for search in planning with symbolic word models. And we're going to go through a very high level over a few papers here. So what do we mean by learning heuristics for search? This is the main basis of this first subsection. What we want to do is we want to learn from demonstrations or experiences or data, some heuristic functions that can help your search algorithm in the planning problem. So what we're given is a set of plans for a set of planning problems consisting of sequences of actions. And from these plans, we can extract ground truth tuples, where S is a state, G is a goal condition, and Y is the ground truth corresponding to an optimal cost to go from S to G. And what we want to do is learn a heuristic function that takes in S and G and predicts a heuristic based on this data set. And what we want to do is to use this learn heuristic function for search. So we're thinking of classical heuristic search algorithms such as A* or greedy best first search. And by using a heuristic, we can try to prune the search space and search over search space more quickly as opposed to not using heuristic. And what we want to talk about in this tutorial is what makes good architectures and models for learning a heuristic, and what is a good optimization function as well for learning this heuristic. And as the subsection already suggests, we're going to look at learning these heuristics with graph learning. The motivation for this is that planning problems are arbitrarily sized because we have arbitrarily many objects and hence can have arbitrarily many facts and goals, which may or may not be able to fit into a fixed-sized neural network. So what we can do is use a graph neural network to encode arbitrarily sized inputs into latent space and reason directly over there. And the natural pipeline that arises as follows is that we can try to convert planning states into graphs and use a graph learning model to embed the graph and the following optimization function or loss function to learn a heuristic function to guide your search. And we're going to go through a quick review of different approaches for 1, 2, and 3. So the question of how do we encode states as graphs is a first question we need to come up with. In our research, we looked into the literature and kind of found out there's usually a trade-off between expressivity, which corresponds to heuristic strength, and evaluation time, which refers to heuristic search speed. So better heuristic strength is good in a search algorithm because this makes us search through fewer nodes into search algorithm, whereas better search time is better intuitively because we want to find solutions faster. But unfortunately, there's usually a trade-off between the strength and speed when we're trying to encode graphs. More specifically, expressive graphs learn stronger heuristics usually, but are larger and slower to compute. And what we looked in our following papers is that both theoretical and experimental results. So we tried to compare the expressivity of different graph encodings in the literature in the theoretical sense. And then experimentally, we experimented with different encodings on different planning problems. And some of the takeaways is that small graphs generally better generalize across similar problems, but scaling across problem size. Whereas expressive graphs achieve better generalization in the width sense of achieving different goals across different settings and environments. And here's one example of how we can encode a planning problem into a graph. We call that a planning problem state consists of a database where we can also view it as a set of atoms and objects. So we can encode these atoms and objects as nodes and the edges as relations between these atoms and objects. And further features are encoding the different predicate and goal information. So for example, with this blocks word problem illustrated here, we have a bunch of different facts denoting different stack configurations of blocks in each other. And also the relations between the objects and atoms and the predicates describing the facts in the state. Moving on, you may ask next, how should we encode these graphs after we've converted them to graphs from states? The kind of common answer you may think of is to use a graph neural network, since neural networks are quite popular and there are graph variants of that. But from our research, we find that graph kernels are sometimes even better for symbolic planning. And the motivation and reasoning are as follows. In the literature, it's quite well known now that graph neural network expressivity is bounded by what's called this 1WL or color refinement algorithm. And furthermore, symbolic planning is generally a discrete problem rather than a continuous problem where neural networks perform better. So what we want to do is more logical reasoning rather as opposed to statistical analysis. So what we try to do is to use this 1WL graph kernel in place of a graph neural network. And what exactly is this 1WL graph kernel? We can describe it at a very high level as a, again, input and output algorithm, where the input is a graph with discrete features and output is a Euclidean embedding of this graph with discrete features. And with these Euclidean embeddings, we can feed it through a neural network or linear model to make a scalar prediction for your heuristic. And the idea of the graph kernel is that it's similar to graph neural networks, where we have message passing between nodes to update features of each node, except that the message passing is done in a symbolic way where we aggregate and compress nodes based on multisets. Lastly, after having the encoding and the architecture done, we may ask what is a good optimization function. And the answer here is, instead of trying to learn the ground truth, we can try to learn to rank states instead. So the ground truth is the naive method. So if you recall our training data, we have these Y or H star values, which correspond to the ground truth. However, the downside of learning these heuristic values is that usually it's an NP hard target for these symbolic planning problems, meaning that it's not always possible to learn. So the idea instead is that we can relax the optimization instead and learn to compare states. And this is quite analogous to more common RLHF or RLAIF kind of mid-training approaches for language models and reasoning. And the kind of benefit of this approach is that it's a polynomial time target to learn. So what exactly do we mean by learning to rank states? So given a set of plans, what we do is we want to learn a heuristic based on these plans satisfying two kind of constraints. The first constraint is that the heuristic of a state on a goal trace generally tries to rank better than its sibling. And furthermore, it also tries to rank better than its ancestor. So if we look at these two examples here, we have a goal trace specified in yellow, and also the siblings of each node in white. And on the left-hand side, we have a possible learn H star value, where we try to over-constrain the values on the goal trace such that the values have to be assigned to 3, 2, 1, and 0. Whereas the siblings are kind of under-constrained and can be evaluated to anything, which allows for possible errors, such as this node down here with -1. Whereas on the right-hand side, we can learn a ranking instead, where we can relax the optimization on the goal trace, but furthermore add constraints on the siblings such that we can learn a better heuristic function for the general search algorithm. So next, we're going to look at some experiments demonstrating the effectiveness of the described approaches for planning. And for the benchmark, we're going to use this international planning competition where planning problems are encoded by symbolic word models. And we're going to split the problems into training set with few objects and the testing set with many objects. So the idea here is that we want to generalize or extrapolate the heuristic function from simple problems that can scale and generalize to larger problems. So for example, we may have training problems where we have few objects in the problem, such as 20 or less, and we may want to try to scale up to thousands of objects. And for testing, we're going to do inference using a 5-minute timeout and 8 GB of memory per problem. And the metric we want to evaluate is the number of problems solved within the time and memory budget. So ideally, we want to solve many problems within this budget and also ideally quickly. So what we're going to do is look at a bunch of different methods and ablations of the methods described before. And the metric is going to be plotted on this graph on the left. And the way you read it is that an XY value denotes, where X denotes the time spent to solve the number of problems denoted in the Y-axis by a specific approach. The main takeaway is that higher values are better. So we start off using a baseline heuristic search planner here. And what we want to do is find approaches with lines that achieve better or higher values than it. So starting with a common graph neural network baseline, we observe that learning usually improves upon baseline planners as it achieves higher scores here. And then from our discussion earlier, we observed that ranking generally helps graph neural networks as well. However, we can introduce another baseline, which is a new state-of-the-art planner using multiple search techniques beyond just heuristic search. And we observed that if we use graph kernels instead of graph neural networks, we can match the state-of-the-art. And furthermore, if we apply ranking on top of graph kernels, we can achieve some significant performance increase. So that's learning heuristics by graph learning for planning. Next, we're going to learn symbolic policies using goal regression. And part of this talk was given by me before earlier a few weeks ago with Centaur AI. So this will be a kind of condensed version of it. So this time, instead of learning heuristics, we're going to try to learn symbolic policies. So with a policy, we do not try to do any search and can just try to roll out the current action with the current state and repeat applying the action of the policy until we achieve the goal. So the inputs for learning symbolic policies usually consist of a finite set of training problems, and again, our symbolic world model consisting of a set of symbolic parameterized actions. And what we want to do is output a policy that solves a set of testing problems. In the form of the policy, we're going to look at takes the form of a set of first-order condition action pairs as follows. So here we have a very logical representation of a symbolic policy, where we have a state and a goal condition on the left-hand side of the arrow. And once this condition is satisfied with a certain assignment of variables, we can apply this corresponding sequence of actions. And the key technique we're going to look at and introduce is goal regression. So goal regression is a very powerful symbolic rewriting technique introduced several decades ago that computes the minimal and sufficient set of features from a symbolic world model for achieving a given goal via an action. So this idea of a minimal and sufficient set of features is a very kind of important role in learning and machine learning in general, where we want to find features that are relevant for your goal and ignoring everything else that is not relevant. And the formula for regression here consists of 2 steps, which consists of undoing the action effect and adding the pre-image of the action or the precondition. So the idea of regression is you're trying to undo the action based on a set of goal conditions. And with this idea of goal regression, we can synthesize policies as follows in a 3-step process. So recall we have policies as a set of first-order condition action rules, as seen here, which we want to synthesize from a set of training problems. And the first step consists of computing actually a data set from these training problems, usually consisting of optimal plans for single goal items in any order. And next, we're going to perform goal regression, our key technique on the goals, with the corresponding plans to get a set of partial state macro action pairs. And for the final step, we inductively generalize the pairs and goals into a set of first-order rules. And the approach here is quite simple, where we replace objects with variables in the sense of lifting ground representation to lifted first-order representation. So we can try to illustrate this idea again in terms of figures. So given a symbolic world model, or SWM, for a transport problem, we have a put down action and a move action. We may have a training set of problems consisting of problems such as this one we've seen before, where we have an initial state and a goal condition. Here, the robot is in the backyard and holding the kitchen while the dog is at the kitchen. While the goal condition consists of bringing that cake into the kitchen. So from step 1, what we want to do is find a plan to progress the initial state here into a state that satisfies the goal. So moving from the backyard to the kitchen and putting down the cake achieves our goal. And the second step here is to regress the goal with the plan. And the key idea here, as we've talked about before, is once we do regression, we observe that we can remove some irrelevant facts that are not relevant to the goal. For example, here, the dog being at the kitchen is not relevant for our goal of bringing the cake to the kitchen. And this is represented on the right-hand side, which once we regress the plan under the goal, we do not see this fact anymore. And finally, for our final step, we generalize these regressed states into rules. So we take these partial states and actions and then lift them into corresponding rules on the right-hand side, where we replace objects with arbitrary variables. So next, another contribution we looked at here is that we can execute these policies using existing techniques such as database algorithms. So given a policy on a new problem, we can reactively set the state to initial state and try to keep on applying actions in our policy until the goal has been achieved. And the contribution here is how exactly do you find an action based on this policy? And the idea is that we want to ground one of these rules. So we want to find an assignment of variables to objects in a planning problem, such as the state condition holds into state, and the goal condition holds in the set of the yet to be achieved goals. And we want to apply the corresponding sequence of actions on the state progressor. And the idea is that we can use this, execute this grounding approach using first order database security algorithms. And in our implementation, we can just use SQLite Python package. And this gives us our Neuro-Symbolic planner. And what we're going to look at next is experiments looking at how well do these policies scale in terms of solving speed and problem size, as we have looked at before for learning heuristics. So the experimental setup now is to look at 12 different polynomial time combinatorial planning domains consisting of logistics, rovers, and a kind of a cocktail barman domain. And usually with these training objects, again, they're in the double digits, and the testing objects are in now up to thousands or tens of thousands. And as baselines, we try to compare against state-of-the-art symbolic planners and learners. And again, we're going to look at the metric of solving problems within a given compute budget. Okay, so we've seen these plots before, but to reiterate, what we want to do is, given an XY axis, this denotes, the x-axis denotes the time it takes for the given approach to solve Y problems. So this means that higher numbers are better because we can solve more problems within a given time limit. And usually, as we discussed as well earlier, these problem search bases scale exponentially in terms of the number of objects, because increasing number of objects usually increases the number of actions and also states and planning length required to solve the problem. The main takeaway here is that this very simple goal regression approach can outperform the state-of-the-art in terms of numeric and logical kind of planning domains. Next, we can also actually use these policies for search. And the idea here is that given a policy, you can prune a search space where any action returned in the policy can be used to keep states in the search space, while any actions that do not exist in the policy gets pruned. And the idea here is we can use PDD axioms. And axioms are additional derived state features that we can compute based on current state features. So what we can do is firstly encode axioms that detect unachieved goals. For example, we have additional predicates representing the goals that are in the problem. And when the goal predicate exists and the current predicate does not exist, as denoted on the left-hand side here, we can find the axiom which states that the goal has not been achieved for this predicate. And next, we encode axioms corresponding to our policy rules that restrict action application based on the learned rules. So again, we have our state condition and our goal condition, and once these are satisfied, we can find the corresponding precondition of the action that we may allow to fire. And the idea here is we can feed this transform problem into any arbitrary PDD planner that supports axioms. So now we have policy execution and also search-based pruning based on our goal regression technique. And now we want to look at how well our approach scales for search when we use policies to prune the search space. So again, we're going to look at a similar setup, but now instead of polynomial time targets, we're going to look at NP-hard optimal planning domains. And we're going to look at the same training testing split and corresponding baselines and similar metric. And again, we've seen a similar figure before where the approach using goal regression gives you very powerful performance compared to the state of the art. And on the right-hand side, we observe that this goal regression technique and also the idea of combining the transform problem into the planning problem with axioms usually improves upon its base planner. Okay, so that's the neuro-symbolic approaches aside. We're going to move on to looking at how we can use large language models for planning over symbolic word models. And what we're going to do is look at a brief history of how we've used LLMs to solve planning problems since the advent of ChatGPT to the general audience. So once LLMs became quite popular in 2023, there were many skeptics that were against using LLMs for planning. So there's a group from the ASU University that looked at using LLMs to solve planning problems represented in natural language. And the method was simply to prompt 2023 LLM models on planning problems and see how well they perform in terms of outputting plans. So given a planning problem, we ask it to output a plan and then see if that plan is correct or not and solves the problem. And the result that they claim is that these LLMs have poor planning accuracy, which was not too surprising given the early models were not that great in terms of all textual reasoning problems. So in 2024, the skepticism kind of continued. The same authors looked at trying to improve this approach of prompting an LLM by combining the prompting with an external verifier or validator. So the idea is now after prompting the LLM for plan, we can try to feed the plan or solution to an external verifier. And if it's correct, then we're all good. Otherwise, we try to feed the output back into the LLM to see if it can try to keep outputting a plan that's correct. And this was shown to give a slightly better planning accuracy, but the performance was still quite poor. So the accuracy increased from 5% to 20% for the given benchmarks. However, 2024 was when ChatGPT 4 and kind of 01 started to be released. And we realized that these models started to get better at solving these planning benchmarks. So for example, InstructGPT-3 got around 7% accuracy for these planning benchmarks, and this improved up to 34% with GPT-4. And once the 01 preview came out, these benchmarks were almost entirely solved with a 97.8% accuracy. And the canary in the coal mine for the improvement of LLMs was represented in the next paper. So the sentiment shifted from LLMs can't plan to LLMs are not really reasoning by the same authors. So 2024 was an interesting time because we also saw papers that were optimistic about LLMs for planning. So a group from MIT showed that LLMs are quite good at code generation for planning, mirroring other observations of LLMs being good code generators for robotics, such as code as policies or software engineering tasks. So now what the approach here did consists of giving a planning problem and a domain represented in PDDL or a symbolic word model into the LLM and asking it to generate a program in terms of Python code. And with this program, we can input other planning problems and get it to output a plan. And the result was quite interesting and powerful. So what the author showed was that GPT-4 already outperforms classical PDDL planners using this code generation approach. So to read these graphs, what we look at is the planning time required to solve problems with a given set of objects where lower values are better. And GPT-4 outperforms state-of-the-art fast downward planner on a bunch of domains. After another year, 2025, we started looking at using LLMs as different planner components. So several authors looked at using code to generate heuristic functions, which can be used in heuristic search for planning. So given a planning problem and domain, we can ask the LLM to write a program in terms of, for example, Python code or C++ code or Rust code to output a heuristic. And we can use this heuristic, as we discussed before, in a search algorithm such as A-star and greedy best first search, and combined with arbitrary planning problems can be used to output a plan. And this approach is quite nice because it's sound, because we leverage an external planner, where sound means that we can theoretically guarantee that any output plan is guaranteed to be correct. Similarly, about how we can use heuristics, we can also generate policies. So now we can write code as policies and use an external action verifier to generate Python programs that act as policies for planning. So similarly, before we can ask the LLM for a program representing a policy as opposed to a heuristic function. And we can use this policy as is with a small external action verifier to solve arbitrary planning problems. Again, such approach is sound, meaning that theoretically we can be guaranteed that any output plan is correct with respect to the symbolic word model. We also saw very interesting results with LLMs for planning outside of research settings. So we also see that LLMs can outperform state-of-the-art PDDL planners on real-world competition. So here we had a €4 million ERC project competition in collaboration with Airbus. And the winning approach by a startup made use of program generation and evolutionary algorithm, similar to fund search, which is what one of the authors actually did in this company. And the result as shown here is that all problems were solved with 100% success rate and outperforms existing state-of-the-art PDDL planning approaches, which could not solve even half the problems. And even further later into 2025, we observed that LLMs can plan even without using code synthesis or program synthesis. So same authors that wrote a heuristic program synthesis paper earlier showed that late 2025 LLMs can match the state-of-the-art planner performance without code synthesis. So what was done was simply to prompt the LLM directly with the PDDL encoding of the planning problem. And we can see here that red with Gemini 3.1 Pro already matches the performance of classical planners, even with obfuscated planning tasks, meaning that random words in the PDDL or symbolic word model are replaced with arbitrary symbols, but still match the original semantics of the planning problem. And now with 2026, we have even more interesting results with LLMs. As most people know, Claude Code has really performed quite well with software engineering. And it has been used to solve this third iteration of the ARC problem. So for those who do not know, the ARC problem consists of abstract reasoning problems. And the third iteration combines abstract reasoning with planning components. And what's been shown quite recently is that there are several approaches that use program synthesis to solve pretty much all problems in the public benchmark of this competition. And even more, like very recently shown, is that these LLMs can be used even without program synthesis to almost solve almost all problems here. So to recap, what is the state of the art for LLMs for planning? We have seen quite an interesting kind of trajectory where we started with ChatGPT being released to public and many people being very skeptical and negative about using LLMs for planning. But in 2024, researchers showed how LLMs can be used to start exhibiting state-of-the-art and very strong planning performance. And 2025 showed some very interesting results where we can continue this code generation approach to improve planners and also to outperform the state-of-the-art in industrial settings. And later we see that as coding agents become more and more reliable and also even can solve planning problems without code synthesis. So what can we do to answer this question? I guess one kind of takeaway here is that LLMs are quite already very good at reasoning in the textual space. So we may almost say that symbolic planning is solved, except with several exceptions. And anyway, that's the end of our talk. So we talked about learning to plan over symbolic word models. We looked at neuro-symbolic methods for planning over symbolic word models, including learning heuristics and policies. And we also looked at using large language models for planning. And we saw some very quite optimistic results about using language models for planning, which we can use to improve more general AI kind of problems such as robotics, embodied AI, or more general agentic systems. So thank you. That's the end of my talk.
All right. Well, thanks, Dylan. We have been cutting into breaks, so we'll actually probably try to respect the break this time. But let me ask you a question about this last statement. So, really, that's the solution? I mean, LLMs are the solution to planning? Is there nothing they're not good at? I have a feeling there are a lot of big caveats.
Yeah, I agree. There's also still like some kind of planning problems or like extensions of planning problems that aren't yet solved with LLMs. I still think many people agree that memory and preferences is still kind of unsolved, especially once you have like very long context or like memory kind of problems. But I'm also kind of optimistic. Like we've seen like very exponential progress with these LLMs. So it's hard to say whether they will remain unsolved in the next few months or years. So I like to see what will happen next.
And these benchmarks, are they on the internet?
These benchmarks are on the internet. So some of them, such as the PDDL planning problems, are on the internet. So one thing people might argue would be like, okay, these problems they have solutions on the internet, and you can train on these solutions with these LLMs and solve them. But the interesting thing is that with these works, they've done an ablation study where they kind of mixed up the semantic words in these PDDL problems with arbitrary symbols, which no longer contain any natural language meaning. Yet like these LLMs have been shown to still like solve these problems, which have no more like natural language semantics, which is quite surprising to me.
All right. I think to me, that's a really interesting thing here is we've kind of seen this issue across all of AI with kind of polluted benchmarks and lots of different ways to cheat, arguably even coming with the entire, corpus of mankind is not a great test, meaning that doesn't isolate the key properties. But I guess this opens up a very interesting version of that, which is for planning, and which is closely associated with reasoning. So great. Well, thank you so much. I think we'll be following this thread and see where it goes. But I invite people to really think about this. How do we very clearly kind of isolate the capabilities of LLMs in planning and reasoning? Because we see some very different results on people who have done isolating studies on reasoning. We see LLMs kind of totally fall apart. So it's a moving target. It keeps improving. But so that's another confounder. But all right, great to see this evolve. Thanks so much, Dylan.
All right, thank you, Alex.
All right, take care, everyone. We'll now take a break, and soon up, we'll have in about 10 minutes, we'll have a very special session with Andy Bartow. So don't miss it. See you in a bit. Okay, welcome back from the break. Now, something I'm very excited about. All right, hey Luis.
Oh, hey. Hey, Alex.
Let's bring in Andy. All right, hey Andy.
Okay.
Welcome. Okay, so it's a great honor to have Andy with us today. So I chatted with Andy not long ago, and and I also read about origins of RL and so on, and really thought it would be special to hear directly from Andy how it all began in particular. And really the setting here to me is, many people are here in Neuro-Symbolic AI to really, because, there are big issues, they're affecting everybody in society around AI. So that working on AI in ways that improve it, more important than ever. And there are more researchers than ever actually in AI. And, of course, we all want to make an impact. We all want to do something great if we can. So here we have someone who has done it. And so I think for anybody who aspires to do something with as much impact as it takes for people to figure you should get a Turing Award, I think we all can be inspired by that. What we're trying to do, actually, but particularly in AI, of course. And this doesn't have anything necessarily to do with Neuro-Symbolic AI. It's by now, reinforcement learning is a fundamental part of the toolkit in all of AI. And we already heard earlier today about ways it's being used in Neuro-Symbolic AI. So so this is not about its use in Neuro-Symbolic AI at all. Really, to me, the more meta thing we can take away from hearing, having Andy, who's kind enough to rewind and go all the way back and give us a picture of what it was like, I think we can take that away in our effort to try to have a big impact, particularly in AI. So thanks so much, Andy, for taking the time.
Sure.
You were telling me you were happy to quietly retire until I bugged you. So let me start, and let me also introduce Luis. I thought it'd be fun to have Luis here because Luis is like, his own story is an analog in Neuro-Symbolic AI, really starting work on it a long time ago when nobody was listening and nobody thought it was necessarily a good idea, and probably experienced a similar trajectory and had similar experiences. So all right, let me start with the first question. So you told me you didn't exactly start out deliberately wanting to create RL per se. It began with curiosity about something else. And tell us about that.
Okay, so no, you're right. I didn't think about RL until relatively late. I went to the University of Michigan, and I enrolled as a student of naval architecture. So I grew up around boats, and I loved to draw. My mom was an artist, my dad, mechanical engineer, and I thought naval architecture would be a nice combination of what I like to do. After a year, however, I decided that was a big mistake, and I dropped out of that and went into math instead. And one of the interesting things about naval architecture that kind of discouraged me from it was that in looking at the design of large ships, the very, very minute details of the structure were specified and legally had to be followed. So it was extremely highly regulated because over many years of ship failing and breaking apart. So the cross-sectional dimensions of the structural members had to meet very stringent specifications in order to get a ship insured. And I felt that was stifling creativity. And I dropped out. And there were a lot of other reasons for dropping out, but I eventually graduated. And along the way, as an undergrad, I discovered various books that really influenced me, mainly about cybernetics, which was the term that was popular then. It was such a cool term that I wanted to learn about it. So I did a lot of reading, and the connection between computation and biological systems was what was so striking to me. And I went to graduate school. I was accepted again at the University of Michigan. Sorry, I may have said Massachusetts, but Michigan. Their computer science program was a very biologically inspired program. Among the people there was John Holland, who you may have heard of, who was, heavily devoted to studying adaptation, both in machines and in animals. So it was an amazing opportunity to interact with people in the graduate program at Michigan. That was, back then it was and this was I started at Michigan as a grad student in 1970. So it was quite a long time ago. And at that time, genetic algorithms were kind of the thing that everybody was talking about. And of course, Holland was the proponent of that, to do optimization by including certain aspects of biological evolution. So that was very influential on me, the idea of adaptation, the idea of self-improvement, and so on. So it was very influential, although I never really bought the whole story of genetic algorithms, because I thought that there are a lot of stochastic optimization algorithms that can work as well. And so the bringing in the natural science of evolution was very interesting, but didn't seem to be necessary from a purely functional point of view. But it was highly influential on me, and I at some point got involved with artificial neural networks, and I think that was from some readings. I know Michael Arbib wrote a book called Brains, Machines, and Mathematics, which I stumbled upon at some point. And that talked about McCulloch and Pitts, talking about the correspondence between logic networks and neuron-like networks. And that was fascinating to me. And I really wanted to learn and pursue that in more depth. So the artificial neural network point of view was not so prevalent at Michigan at the time, but I thought it would be cool to do a genetic algorithm type optimization system using a neural network instead of a population of genetic material. And so that naturally, over a number of years, led to something like reinforcement learning, because evolution is a similar but different process in that a kind of search is required, as opposed to supervised learning, where the examples really give what the output should be. And the problem is to generalize from that. But in evolutionary processes and in reinforcement learning, the system isn't given that information. It has to search for it by trying things. It's an active search process. And so that was fascinating to me. Now, when I got my PhD in 1975, I took a job at a university. I won't say which one it is because I didn't like it. After 2 years, I heard I was on the tenure track at this university, and there were lots of things going on, political things among the faculty, and it was just not what I had expected. And I heard of a postdoctoral position at the University of Massachusetts to join a group whose objective was to assess a hypothesis of a physiologist who worked for the Air Force to assess his idea that neurons, the basic components of brains, are hedonists. That is, that they work for pleasure and work to avoid pain. And in other words, that neurons themselves are reinforcement learning agents, and that intelligence, according to this hypothesis, is the result of a collective behavior of interacting neurons that are all trying to improve their degree of pleasure. So our task was to assess this, which seemed like a far out idea. We were supposed to see whether it made any sense. Is it worth pursuing? Should it be developed, or is it just crazy? And so that was that postdoctoral position, and that really led into the work that we eventually did involving reinforcement. A student, I was a postdoc there, but in a year or so, a graduate student was admitted, Richard Sutton, who was a co-awardee of this recent Turing Award. Rich came from undergraduate at Stanford, where he studied both computer science and psychology. So he joined me, and then later some other students came, and it was we were not PIs. There were 3 PIs, and they wrote the proposal and did all the work required to deal with the grant. So we had an idyllic period during which we could just explore. I didn't have to teach. I didn't have to go to faculty meetings, which I appreciated greatly, having been a tenure track faculty member for a couple of years. So this postdoc, I think we wrote a proposal to get an extension of it. It was 5 years that we had this freedom to just explore. And so we deeply searched the literature. Has this been thought of before? Have people worked on this? So on, it led to a whole collection of things. And one of the things that was most striking that we discovered is that reinforcement learning had been kind of neglected in the development of neural networks. In the early days of neural networks, in the early days of trying to build machines that learn, they did reinforcement learning. In fact, Alan Turing in 1948 proposed a pleasure-pain system implemented on a computer. He didn't implement it. He didn't have access to a appropriate computer then, but that was reinforcement learning. And at some point later, things shifted as people recognized that the idea of generalizing and learning from examples was a really rich area, and that whole field kind of developed along supervised learning, which is kind of the mainstay, for example, of training large language models is mostly supervised learning. So we felt, that has been neglected. We have a kind of angle to deal with the literature. But of course, back then, the idea of neural networks was not popular at all. It was you know, the famous paper by Minsky and Papert, the book about how perceptrons. Of course, if you read that book, it's actually misunderstood. I think it's actually a very interesting book, but you know, things became symbolic and proceeded in that way, and it was very unfashionable to be doing neural network research, and so we struggled in terms of publishing. There were a few places that we published. There were not a lot of it was IEEE journal, System Man and Cybernetics would publish work in this area. And so we did publish some early papers, but you know, I would go to conferences and kind of be the odd man out, the odd person out, because people were talking about other things. So it was, you know, it was a tough period. But at some point, connectionism became the fad. I think, you know, through the work of Jeffrey Hinton and others, that made our lives much easier, because it was their arguments, you know, convinced a lot of people that this was an interesting direction to go. And so over the years, we continued this exploration of reinforcement learning, although not necessarily in terms of neural networks. It kind of making connection. I guess I was always interested in making connections to more established research areas. And I think it was kind of a feeling of, yeah, people don't like these neural networks. They're too, you know, there's not a lot of theory. It's just kind of fooling around. And so I always work to connect things to, say, optimal control theory and dynamic programming. Others, of course, contributed along all these areas, but you know, we hooked up with bandit problems that statisticians studied, and so on. So you know, you can look at the literature that came out of the lab at UMass Amherst. A lot of them are about connecting to more established bodies of theory, so that we weren't considered just fooling around with some crazy ideas. So let's see. There was one other thing I was going to say. Well, it caught on eventually. You know, through the effort of a lot of people, some really interesting applications. Jerry Tesoro did a backgammon player that learned to play very well, and it was a straight reinforcement learning system. But you know, we saw that people weren't really distinguishing supervised learning from reinforcement learning, thinking, well, they're pretty much the same. Oh, they are pretty much the same, but there's a key difference, that the reinforcement learning system has to search, has to try things out. It's trial and error. And the term trial and error comes from psychology, but it's really a misnomer, because it's not errors. I mean, the key thing is that supervised learning is based on error correction. And the errors come from, you know, knowing the difference between what the system did and what it should have done according to the example. Reinforcement learning works on evaluations, and it's a lot hard. It's easier to generate an evaluation based on less knowledge than to give an error. And so to learn from evaluations, you know, just like in evolution fitness, evolutionary fitness, it's an evaluation, it's not an error. An error, it has a sense of what it should be, but that's not present in RL or in evolution. So anyway, we we continued to get grant funds, and I eventually became a faculty member there. Eventually chair of the department. So it was kind of an interesting trajectory, and a lot of wonderful students. I think that's the key for me, is that it seems to be such an interesting subject that we attracted some just wonderful students, and so I think a lot of it, and actually many of them are doing very well now. So and it was a long time ago that I started. I started as an undergrad in 1966 and went to grad school in 1970. Joined the faculty or postdoc 1977. And I retired, I forget, 80 something, but so it was like 13 years ago that I retired. But the lab that I used to co-direct is now headed by two of my graduate students who were hired by UMass. And so it's still an ongoing affair. And one of their main emphases is to look at the safety of RL systems. And I can talk about that a little bit more. Yeah, so I had no idea. I've never really been interested in computers per se. I've been interested in mechanisms, and I view like neural networks or even algorithms as mechanisms, not as symbolic expressions. Symbolic expressions need a machine to execute them, and I've been interested in the machine rather than in the symbolic aspect. Although I agree that's extremely powerful, and to combine, the emphasis of your summer school it is neuro-symbolic, and I think that's a wonderful combination. But for me, I've always, as a kid, I was interested in motors and engines and pumps and things like that. I could see them, I could see how they worked. And I still think of computer programs as mechanisms. And so yeah, maybe that's more than you wanted to hear in answer to your question, but I think I've been very fortunate to stumble on this subject. And I've also, I'm used to being not fashionable. We were not fashionable at all. There was no meeting. And now, of course, there are lots and lots of them. But back then, we were considered, a sideshow that wasn't going to amount to anything. But through the efforts of lots of people, it seems to have amounted to something. So anyway, it was unfashionable. I think a lesson is that we just persisted. We were fortunate to be funded, although not all the time. We had to go through some fallow periods when other subjects were much more fashionable. But we just thought it was interesting and possibly useful. And I'm not I can program computers. I've taught computer programming, but I don't like to do it. I've never been a hacker. I relied on tech people to do all the computer stuff. And my students really much better than I am at computing. I understand how they work. I don't know anything about electronics. But they're machines. And it's really the programs that they're running are machines. The physical computer was not, it's an amazing machine, but it was not the thing that interested me. So anyway, that's more than you wanted to hear, but
no, not at all. It's exactly what we wanted to hear.
That's very good.
Go ahead, Luis.
No, that's really great too. It's a fascinating story. I mean, thanks for sharing all of these details. And
Sure.
yeah, I mean, I want to go into keeping the same line. I find it very exciting. As you said, many people didn't know about reinforcement learning, and AI was kind of a niche subject, right? I still remember when people knew everyone in the community, right? Maybe now it's just impossible. Instead of having a few hundred people in conferences, we have thousands of people. And your research area, machine learning and reinforcement learning, are heavily used in industry, and even non-researchers talk about it now. Can you comment a little bit about what you think of the impact, if you foresee anything in such a scale that we have today? I mean, I find it unbelievable, where AI is today, and you've seen it for many, many decades.
Yeah. Well, I'm astounded at what's happening now, and I can't keep. Obviously, even young students can't keep up with things. But let me just say that Sutton and I often consider, some people said, why don't you create a conference focusing on reinforcement learning? And we resisted doing that. Now there are conferences on reinforcement learning, but back in those days, we felt we were doing machine learning and we should be in the machine learning cohort. And so we would give talks at ICML or NIPS or whatever these meetings were called. So I didn't want to branch off and become a separate field. And I think that was a good decision because it became a part of machine learning. So I think that helped the currently widespread knowledge of this stuff. So what's going on now? Yeah, I mean, I have lost track of how RL is being used. Dealing with large language models, I know about fine tuning using RL and so on and so forth, but I don't know the inner. I've never really been involved in generative AI. My knowledge is just vicarious from reading more popular press articles. Things are so different now, though. The number of venues for presenting this material is astoundingly large, which was not the case back then. And I guess that was sort of one motive for retiring. I can't keep up with it. I stay in touch with a number of people, but it's really daunting. And some of the things are really fascinating. I mean, I'm amazed what can be done with large language models. It's quite amazing to me, but it's not an area that I want to devote a lot of mental energy to. I think another thing that's important is writing. I almost majored in English literature, and I've been considered a good writer, and I think that played a role in the acceptance of RL because I like to write, and I like to keep it as simple as possible. And the book that Sutton and I put together, I think, is a readable account of RL and has influenced a lot of people. But I think writing is extremely important. Human writing. Nowadays there's the problem that some sort of large language model can write things, and it's a query among educators now, whether to permit that or so on and so forth. I mean, I didn't have that problem because when things were written, they were written by humans, and I think human writing is still extremely important for students to become good at. In fact, my students will. What they think about me mostly is that I always gave them trouble. for their writing. I really couldn't deal with technical aspects of a document until they fixed the writing. And the students are very brilliant people, but not necessarily along dimensions that led to clear, good writing. So they will tell you that I badgered them throughout their graduate career to write well. So anyway, writing is important, and I would encourage current educators to human writing. They're participating in. So, but the whole field, I mean, it has exploded so radically that it's astounding to me. And I avoided dealing with the corporate world. I really resisted. I think that was part of my culture going to school in the 60s, counterculture. It was, I went into math. I studied the most abstract math I could because I didn't want it to have any use. Of course, it eventually has found use, but I just, have not been involved in money-making enterprises. I've consulted a few times, but it's just I have avoided that purposefully. Okay, so I don't know what's the next.
No, not there. Yeah, well, let me just translate some themes for everyone that I think you really exemplify. I mean, I think we heard, you stumbled upon the ideas of RL really out of curiosity, and it was absolutely not a fashion, didn't even exist. It was just one guy's weird writings that you found interesting, and you decided to pursue it. And I've looked at that thing, and I think Luis and I have were both nodding as you were telling the story, because we recognize a lot of the names, and because there was a smaller number of names back then, Michael Arbib and John Holland and so on. And but even that thing that inspired you was not even on the radar for anybody. So so I think that's important, just to pursue something that looks interesting regardless of any other support for it. And I think that's a very strong thing.
I should say that our support, mostly initially it was from the Air Force, but after that it was from the National Science Foundation, and it was basic research. We didn't have deliverables other than papers and reports. We didn't have to build machines. So it was it was a wonderful way to proceed with basic research. Unfortunately, that seems to be harder to come by now. So
that's why we started the Institute, absolutely. And I think you also, in avoiding industry, really, to me, the larger theme is avoiding lots of short-term kind of, influences. Industry tends to be short-term focused.
Yeah.
You were never a fame and fortune kind of guy, we can tell. And those are short-term.
By my T-shirt here, yeah.
And but lo and behold, not focusing on those things actually brings you those things. So like a multi-million-dollar prize. But and I think, the period, or a long period, where you kind of had to fight in a way to be heard and fight against the larger wave of supervised learning. Go, hey, there's another idea. I think that takes some kind of being determined and not giving up. So I think that's another great lesson we can take away.
Well, I always strive to get to the key point about why is it interesting. It's not supervised learning. And we created demonstrations, which reached a high point with DeepMind doing Go and other things using, it was sort of stunning that scaled up like that could actually discover these strategies that really were novel to human experts. Well, one of their questions, I think maybe you're going to get to that. What areas of RL might be worth pursuing now?
Yeah, please. Yeah.
One of the things that so there's a whole field of the genetic programming. I don't quite know, and in fact comes from Holland back at Michigan, his students and others, and it's separate from reinforcement learning. They're different communities. They have different conferences, and I think they should be combined. I think evolution and RL work together in nature, and they're similar processes in the sense of requiring a search and survival of the fittest and so on, but they're working at different scales and they work together. So I think that's an area I would love to see those communities, join together more than is happening now. So, and I guess the other area is really interesting, I think, is multi-agent reinforcement learning, which the original idea was that brain, intelligence is due to interacting RL systems. And there is work on multi-agent reinforcement learning, but there could be much more. It gets really difficult, though. It's game theory, for example, is touched upon, and we sort of avoided it because it's too hard. The results are harder to come by in the multi-agent case, but I think that's really important for lots of reasons, not just the hypothesis that intelligence comes that way, but in terms of practical applications of across the internet. The internet didn't exist back then. I mean, it was not something that we were that influenced our thinking because it didn't exist. It makes me feel really old, though. Gosh, but we just getting a laptop took decades. So we bought two Sun workstations at some point, and I don't know what happened to them. But that was, and then we used VAX, DEC VAX system at UMass. But nowadays, I have on my desk practically a supercomputer. So
it also points to how determined you had to be, even struggling with computers themselves back then. So one thing I hear very strongly too is you really always believed in fusing things rather than dividing, and I think that's also a theme for you, Luis. Luis, you want to?
Yes.
Well, I think the way I operated was these very bright students would come in with their own ideas, which were sometimes flaky, and sort of they're just out of some undergraduate program someplace, which they're very well educated. But so my task, I think, in lots of cases, was trying to figure out what their idea is, in the sense of how's it different from other ideas? How does it relate to existing ideas? And as we talked, me and my graduate student try to hammer out, how to make this idea into something that can be, written about and write a thesis about, publish about, and that required connecting to things in the literature that existed. And so a lot of my effort was to make these connections. And it was multidisciplinary. It's not just restricted to, one thing, but, I was very interested in psychology and neuroscience and engineering, control engineering in particular, although not educated very well in all of those things. But that was, I made connections. That's sort of what I did. And the students' ideas, they were their ideas. I mean, a lot of what we did came from students, but then massaged over the years into something that could be, worthwhile from a technical point of view. So I can't say enough about, not all of my students, but most of them were just, had wonderful ideas. And it's not as if they'd come into my lab and I'd say, you do this, write this code for this. Never did that. And I think that made a big difference to them. And now they're running their own projects around, and I'm proud of that. It's not that I had ideas too, but I would massage theirs to connect with things that I might have been thinking about. Yeah, so it was connecting things that, and sometimes it was hard to publish because there wasn't a large collection of venues for that. There is now, however. So, and now with archive, you can put anything up that you want. So, yeah, things are really different. I like the old days. I mean, I'm a kind of Luddite, I guess. For example, there are, things that have been created that I couldn't do without. And a word processor, things I depend on, a search engine. You can't, now there are things being developed using the main, large language model idea. Some of them are going to be applications that we can't do without. But I don't know what those are yet. It's still in a, very high temperature kind of framework where lots and lots of things are being developed. And some of them are going to be things we can't, that we just can't do without. But I don't think I'm not there yet. Maybe others are, but but looking in the past, I really couldn't do anything without certain systems that were invented along the way.
But we just have a few more minutes. Let me just ask one question from the audience, then I'll pass it to you, Luis,
Sure.
to ask a last question. These days, people use a lot of RL for games, regular games people play. How useful do you think that is for advancing the field? Are there aspects of games that you want to see more?
Is this to me?
To you, yeah.
Gosh. So by games, what do you mean? Do you mean computer games?
Yeah, I think like Atari games, this kind of thing.
Well, I don't play those games. I did for a short period, and I was fascinated by it, but my son just devoted himself to them.
I think as a study for AI, like a way to advance AI, do you see them
they've
being
certainly
valuable?
been valuable as test beds for various technologies like learning, like RL and other forms of learning. So, it is quite astounding to see some of these applications machine learning to games. So I think games have been incredibly valuable from that point of view. In terms of games in the mathematical sense, I think there's a lot of intersection between machine learning and games in the formal sense. And I think that, as I mentioned, multi-agent RL, for example, is basically enters into game theory immediately. But games, it's amazing what one can do with just a laptop now. And I did have lots of fun with games, but they were always, I'm not very competitive. So the games I liked were like Myst and, those exploration type things. And some of them were just so artistically beautiful and interesting from a, problem solving point of view. But they didn't have time. I don't like time pressure. I don't like competition. And I think that's why I kind of, stuck to this unpopular area because, in the initial days, there was no competition because nobody else, very few people were doing it. So I'm still averse to competition. So, yeah.
All right. Speaking of pressure, that we'll have to wrap up. So, but unfortunately, because there's so much more to mine from Andy, but Luis, do you want to ask a last quick question?
One advice to a young researcher or a young professional who is starting in AI now.
Well, I would say that you shouldn't follow the main trends. You should think for yourself and not be swayed by fashion. And I think the AI field has been driven by fashion over the years. Certain periods, graphical models were fashionable, and then in other periods, other things. Now, large language models and related technologies are fashionable, and there'll be other fashions. But I don't think you should be propelled by what is fashionable. There's a reason to follow fashion. You can get support, so on and so forth, faculty positions, whatever. But I would advise to follow your own interests and passions, and maybe you'll invent a new thing. So, but I've just been very fortunate. I've followed my interests and did okay, and that's not guaranteed, unfortunately. So, but I've never been fashionable, as you can tell by how
I think that's loud and clear and a great message for all of us in the whole audience. And let me just say thank you so much, Andy. And personally, I'm very humbled and always to hear from someone like yourself. And you're an inspiration to all of us. So we'll connect again soon. But
well, thank you very much.
Thank you, Andy.
I'm very pleased that you invited me to do this. So I look forward to another possibility of talking again. Yeah, thank you very much.
Thank you.
Okay.
Thank you.
Take care, Andy.
Bye-bye.
All right, next up, we have an amazing panel. And actually, for the first time, I'm usually the moderator. I'm going to step back, and a very special guest is going to be the moderator, which is Ryan Grimm, legend of journalism. And for those of you who don't know, I'm sure you're, I always keep the intros very brief, but you'll see both Ryan and Emily extremely accomplished and prominent journalists. And Gary, you all know Gary. Gary is our most vocal proponent of Neuro-Symbolic AI, and love him or hate him, he he says the things that many of us believe in Neuro-Symbolic AI, has the nerve to say it very strongly, and I appreciate his efforts for that. And let me especially thank Ryan and Emily. This is probably an unusual venue for you both, but I think this started Neuro-Symbolic AI started getting some attention in the press, and maybe a year ago, arguably, with the Wall Street Journal article announcing the coming of Neuro-Symbolic AI. But I think, just broadly speaking, many people are looking really hard now here for kind of answers. We don't necessarily have them all yet, but we're on our way. With that, let me pass it to you, Ryan.
Yeah, no, Alex, thanks so much. Very much appreciate it. And you should feel free, if you feel any moderating itch, to jump in with any questions that you want. But and also, Emily, as a fellow journalist, please feel free to do the same anytime there's anything that sparks your curiosity about either. Gary, it's a real pleasure to meet you. Thank you for being here. I'm sure everybody knows is the author of the Gary Marcus Substack, Marcus on AI. It's a real thrill to be here. Gary, I actually wanted to start with the post. I think it was today, where the headline of it. Let me pull up here. CPUs and the rise of Neuro-Symbolic AI. There's a lot to unpack in it. I think would be interesting to everybody here. I wanted to read one line to you, and where you write, the entire economy could unravel if people overbuild data centers on the naive assumption that the only key to intelligence is bigger and bigger neural networks driven almost entirely by farms of GPUs. Investors too should take note. That does, though, however, appear to be the assumption. You write in the piece that CPUs are, all of a sudden people are like, oh, wait a minute, we need a lot of this too. But it does appear the assumption that you're saying is going to lead to the unraveling of the data center, the economy based on the collapse of this data center build. It does seem to be the assumption driving the build out at this time. Is that right? And
it is the operating assumption. Yeah, sure. I think the operating assumption, really going back to about 2020, has been, hey, we just need to scale more. There was, in fact, a paper by Jared Kaplan and others at OpenAI. Kaplan is now, I believe, the chief scientist at Anthropic. A lot of the authors on that paper, Dario and so forth, moved over to Anthropic. But OpenAI put out a paper and basically tried to argue that intelligence scaled with compute. And they had some graphs in there. I thought it was naive. When I wrote my 2022 essay, Deep Learning is Hitting a Wall, I directly challenged scaling. I said, look, these are generalizations. They're historical generalizations, but they're not physical laws. And they're going to be like Moore's law. They're going to run out eventually. And the other thing I did in that 2022 article was to say, hey, one of the ways that we can get out of this problem, and I can go into what the problems were, but I said, we're going to face some problems and we need Neuro-Symbolic AI, or we probably need Neuro-Symbolic AI to push past them. And aside, a lot of people in the kind of social media world like to misrepresent me. And the way that they misrepresent me is they say, Marcus said that deep learning was dead in the water and would never go anywhere. And what I said is, it'll go somewhere, but you need Neuro-Symbolic AI in the mix. And I was right about that, but they like to oversimplify the claim. So what in fact happened is, based on the premise that scale was all you need, you literally could buy a t-shirt, you probably still can, that had a picture of the Jared Kaplan graph and said scale is all you need. And that became the rallying cry, first for a few academics and maybe for OpenAI, but eventually for the entire field. And there's a lot of money behind that idea. You know, the sentence I wrote today, which I've written in other forums before, is not an exaggeration. The economy is resting on the idea that scale is all you need. Not all of the economy, but a remarkably large amount of the economy. is premised on the bet that you don't need neuro-symbolic AI, that you just need more data and more compute, and that if you get that, then everything else will follow. And venture capitalists, I must have made a mistake. I see. We'll fix it in post. Venture capitalists love this idea. It's simple and it justifies a large bet, right? It has enough of a superficial plausibility that people put in now probably over $1 trillion. Well, not probably, definitely have put in over $1 trillion on the premise. And you have to remember how venture capital works, right? You get a cut of the money you invest. It's not just that you make money if your investment pays off. Your investment can go to zero, but you still get paid as a venture capitalist. You get paid as a commission. You get 2% of the money that you invested typically. There's a thing about 2 and 20. The 20 is if you do well, but even if you don't, you get the 2. So if you have taken $1 million investment and you make make 2% on that $1 million investment, you're not going to buy a house in on Sand Hill Road or that neighborhood, right? You can't do it. But if you make 2% on $1 billion investment, you're doing pretty well. And if you make it on a $20 billion investment, you're doing really well. And so venture capitalists love to go to their LPs and say, I'll handle your money and I'm going to put it in this giant LLM related thing, a data center or company like OpenAI. And it sounds plausible enough. It'll take a while to whether it pays off or not. And if it doesn't pay off, but you've made your 2%, you've done really well. And so there's an incentive to the venture capital community to keep pushing this story. It is no longer a true story. What happened, let me see if I can get my timing right. Already by mid-2023, people discovered that doing some things other than what I'll call a pure neural network, and we can dive deep into that if you want, other than a pure neural network were actually helpful. They discovered that scaling was not the only thing. By the end of, I think it was 23, but maybe it was the end of 24, the industry realized that pure scaling was not really working anymore, that they were, in fact, getting diminishing returns. But what they started doing, really in 2023, was code interpreters. Well, code interpreters are symbolic AI. If you have a large language model, which is a neural network, though there's some niceties there we probably shouldn't go into. If you have a neural network and you combine it with a code interpreter, you're already crossed the threshold into neuro-symbolic AI, at least as I always argued for it, right? I've been arguing for neuro-symbolic AI arguably back to 1992 or 2001, depends on how you count, certainly 2012. And so the argument I always made is you need some symbolic operations in addition to your neural network operations. And that's what it is when you have a code interpreter. If you have a harness and it is a symbolic harness that does things like, say, loop through until you find a conclusion that you're satisfied with, that is a symbolic operation. And so the field quietly turned to doing neurosymbolic stuff. We don't have, Alexander would be stronger on this than me, we don't have a lot of kind of comparisons with harness and without that would really make this as clear as it should be. But the first one that I noticed and wrote about in my Substack was Grok 4. They showed using it with tools and without. And adding, there was a graph, it was a very interesting graph. It's in an essay of mine called How O3 and Grok 4 Accidentally Vindicated Neuro-Symbolic AI. And if you look at this graph, which was the punchline to that piece, you will see that adding tools in was actually carrying more of the weight than the scaling was. The scaling was running out and the adding tools in was working. That is a huge vindication for me personally, but for the entire field of neurosymbolic AI. Now, you can make arguments about whether neurosymbolic AI is exactly the way that someone like me visualized, and that's an interesting question. I actually mostly deliberately tried not to be too specific about how it would be visualized. My view is that the space of neurosymbolic models is infinite, and the only thing that I really cared about going back to my dissertation work was, do you need the symbolic operations there or not? And, old timers will remember things like Jeff Hinton gave a talk saying that symbols were the phlogiston, the ether of AI. Like there was a lot of hostility to using anything symbolic, and it was coming from Hinton, who was kind of the leader of everything, or all that we see right now. And then Hinton, another time he was talking to the G7 and he said, adding symbols to neural networks is like adding a gasoline engine to an electric motor. Why would you do that? That's just stupid. But the thing that he called stupid is actually what everybody is doing now. So we're at this point where everybody is actually building neurosymbolic AI. Nobody wants to talk about it for political reasons, grant money reasons, historical, sociological reasons, but that is what's happening. We had some back and forth earlier, and I think it was Alexander wrote a sentence about how neuro-symbolic AI is getting some adoption. And my counter argument is it's actually universal adoption right now. I don't think that we've explored the full space of neuro-symbolic AI. I think there are lots of discoveries yet to be made. I think the way that we're doing it now is kind of crude, right? You're taking the neural network, you're kind of putting it inside a larger box and having the symbolic AI control that central thing. And I don't think that's the best way to do it. I think many people in this audience have thought of more sophisticated ways to do it. Not all of those more sophisticated ways have been scaled, but we are definitely crossed the threshold into neuro-symbolic AI. And to go back to your question now, and this is a very long answer, but you seem very patient. The bet was we will just build new data centers, and those data centers will just be GPUs. The thing I pointed out in the paper today is once you're over into this new regime, the neurosymbolic regime, things change. For example, now you actually need CPUs again. Like CPUs were totally out of fashion. People are like, yeah, Apple makes CPUs. What do we care about? It's all GPUs. Look at NVIDIA, forget the rest. And now we actually have a shortage of CPUs. That was a lot of what today's essay was about. And like the thing that made me actually write the essay, well, there were two. One was I was sort of thinking about what we were going to talk about today. And the other was I woke up and saw this thing saying that Amazon is telling its employees to ration their CPU use. Like we're used to people starting to say, hey, watch the GPU bills. They're rationing their CPU use because, you know, there are too many people with too many demands. They do a lot of neurosymbolic AI, by the way, at Amazon. I don't know how much, but they've been more public about it than most. And so the dynamics have changed. You have this bet that we need to literally coat the planet. Well, okay, I'm exaggerating a little bit. Practically coat the planet with GPUs. And suddenly it's like, oh, wait a minute, maybe we need the GPUs. And the mission of the people in this audience, in some ways, I mean, this is kind of being crude about it, but is to apportion those two and figure out the relation between the two. Where do you need CPUs? Where do you need GPUs? How do they need to talk to each other? That's a very different bet than I'll just build out all of the GPUs that I can and hope for the best. That's, you know, now that becomes a research question. Like, what is the way to integrate these things? That is partly the mission of neurosymbolic AI. Maybe I'll stop there. That was a very long answer.
Well, yes, and I'm curious, Emily, like from your conversations with people in the industry, how much of this, basically, like let's just call it a reality, they've absorbed. You know, I've covered, you know, finance, I've covered a lot healthcare, and you often have these paradigm shift moments where something that is quite obvious to people who are following things closely and have a little bit of a heterodox approach to understanding it, see it years in advance. It's a true thing, but the entire industry has its own kind of momentum that just carries it forward as long as it can, like until there's some forcing mechanism that requires a fundamental change. Where in your conversations with people in the industry, where are they in this process of recognizing what the reality is of the bet that they place to the tune of God only knows how many hundreds of billions of dollars?
Right. Excuse me. They're very much on the compute train, you know, billions and billions of dollars.
They're still wearing the t-shirt.
Definitely still wearing the t-shirt. I think the conversation has switched a little bit from LLMs and their hallucinations and their intelligence to more the agentic conversation. And OpenAI and Anthropic, their employees like to brag a lot about how their agents are doing things for them on their computer, whether it's organizing their desktop files or sending them a briefing every morning. And so it's switched less from like pure intelligence to almost like automating these routine tasks and doing more actions around the computer. So maybe that's a convenient way for them to avoid caring about hallucinations and things like that. But to me, that's been a big shift. And if you think about, that's a lot of power, a lot of compute power that, you know, it's their entire day at work. They're running these functions. And so I think they're thinking, oh, we are working how everyone will work in the future. And if everybody is working like that, we need a lot more compute to support it. And so that's the conversations I've been having in the past couple of weeks.
Gary, did I see you with your hand up?
Yeah, I just want to insert something.
Yeah.
The agents themselves are neurosymbolic, right? The agents, nobody's really building an agent as a pure LLM. There was a system called AutoGPT that was like one of the first agents that everybody was very excited about and then disappeared after 2 weeks because it didn't work very reliably. That was maybe basically pure LLMs calling other pure LLMs. Nobody's doing that anymore. They're now using code interpreters and symbolic harnesses and so forth. So when OpenAI is using those agents, they will never use the word neurosymbolic in that shop, though they have in Anthropic and DeepMind and so forth. They're actually using neurosymbolic systems at OpenAI to compose their shit posts on Twitter and do whatever else they're doing. They're using neurosymbolic agents all day long now.
So what's the fight that you're fighting then?
Well, there's multiple different fights. The historical fight was, do we need symbols or not? And I'm still fighting that fight out there on Twitter. They're still pretending that they don't, which is bizarre to me. Like, I don't know why they don't just concede and move on, but they're trying to pretend that it's not, or that it's like, that it's not an important use of symbols or something. Like, there are different ways that they're trying to fight that fight. But the fact is that I was correct on that. And like, OpenAI is never going to admit that for different, sociological reasons and so forth. I don't think that fight is a true intellectual fight anymore. I think in 2020, it was a true intellectual fight. When I had that fight with Jan LeCun, who was on the wrong side of it, he was like, I don't know if we need that. We just need differential programming. And he was very fuzzy about what he thought a symbol even was. But, he was saying we don't need symbols. And I mean, Hinton was saying in 2016, for sure, we don't need symbols. And I mean, many, many people have argued that with me over the years. Another argument they would always give is we don't need symbols because I don't know what they are in the brain. And I would say, well, you don't know what short-term memory is in the brain. That doesn't mean it's not there. But so, many years there was a substantive intellectual argument about whether we would need symbols in adequate AI or adequate cognitive models. You could argue the cognitive models part is still open because we still don't know how their brain works, but you can't argue anymore that we are building an AI that doesn't use symbols. We were when we had pure LLMs, or there's a little asterisk there I don't want to get into, but we're certainly not now. That fight is just over. We neurosymbolic people want it, whether people want to admit it or not.
But I think Emily asked a good question. So, I mean, people are debating whether it's true. Are these systems really neurosymbolic? But let's put that aside for a second. I think, to me, that the problem, if I can translate why Gary is talking about, these things neurosymbolic, actually, it's because the emphasis that's out there is on the neural part, and that's the part they make money on. That's the part that's heating up the earth with the data centers and so on. And it's super fueled by, claims of AGI and, recursive self-improvement being possible with pure neural nets and so on. And it's actually, what it does is, first of all, what I'm most offended by is the intellectual myopia. But because the space of ideas in AI is this big, LLMs is actually a tiny slice, if you really...
Which Andy made very nicely in his last question, by the way, made the same point.
Yes. But what that's led to is a myopia in society, actually, even among researchers who actually also feel that it's only one idea. It's affected all of funding, government funding, in effect. It's affecting the ability to even get grants to do this other kind of research. And yet all the safety stuff, one of the big implications of the symbolic stuff is safety. You can't really have, for various technical reasons, you cannot have full safety, I would argue, from a mathematical view, without the symbolic part. So the overemphasis on the neural part and trying to hide kind of the symbolic part as a little ancillary kind of, whatever. In fact, we don't know it's all closed now. It was once open, open AI, now it's all closed. So we don't know, actually. You send a difficult reasoning problem to, an LLM. They want to look like, no, it's the neural part solving it, because that's what pays all, that's what keeps generating the money. If that collapses, that idea that it's a super powerful smart AI that can do everything, the money collapses. And so, but meanwhile, the amount of attention and work on the symbolic side is very small. It's tiny, tiny compared to everything that's going to the neural stuff. So including like, regulation, all the regulations are this, designed around the machine learning paradigm. It actually needs to incorporate, the safety stuff, which is actually kind of possible if we just put more work. We're already seeing signs of it in yesterday's talks, right, from big companies like Amazon, right? So, so I think to me that's the problem with this weird kind of incorrect emphasis. It is incentivized by money, and it's super fueled in a way we've never seen before in the field of AI by corporate money.
I agree with everything that Alexander said, and I just want to make a couple insertions and suggest a thread to follow. So the insertion is we didn't quite finish Emily's question about where is the debate. So I said the debate is no longer about whether to use Neuro-Symbolic AI, that we are using it. There is still a debate about what will get us to AGI. So we are using Neuro-Symbolic AI, but at least in my opinion, we're not at AGI yet. My own opinion is Neuro-Symbolic AI is necessary, but not sufficient for AGI. There's been a lot of talk about world models from me and Jan LeCun and Fei-Fei Li and so forth about using world models. I think that's a missing ingredient. It's very much still an open question about what will get us to AGI. I think if people reflect seriously, they will realize that we are not there yet, despite $1 trillion investment. This completely ties in with what Alexander said, that we're not looking in the right places. Like, if this didn't work after $1 trillion, this kind of simple-minded version of Neuro-Symbolic AI plus these giant models, large language models, what else should we be doing? And I agree with Alexander. We're just looking at this tiny little place, and with Andy Barto, that people are looking at what's fashionable and not looking broadly enough. And that's been part of my campaign for a decade, is try to get people to look more broadly. And then the thread that I think we should pull on is safety. Like, my view is we don't really have a clue at all around safety, but that maybe the symbolic part would help. And I'll give a sentence there, and maybe Alexander will riff on it a little bit. My sentence on it is you can't get to safety unless you can state hard constraints. And symbolic systems let you state hard constraints. Just don't do this kind of thing. There's some asterisks around that, but that's kind of what they're good for. So, like, I don't know, the traveling salesman problem is an example of hard constraints. People write symbolic solvers, and the systems solve those things. In LLMs, what you get are soft constraints. People put stuff in their system prompt or the other, the user prompt or whatever, and sometimes the systems follow them and sometimes they don't. So all these rogue things lately, the system prompts probably told them, like, don't use sandboxes, and don't go out don't leave sandboxes, don't use the open internet, don't blah blah blah. And the systems do it anyway. They don't really follow those constraints. Just like if you say don't hallucinate or don't use copyrighted materials, they don't actually know how to follow that. And I think there's some hope, and I'm going to pass it to Alexander. There is some hope that symbolic systems or neurosymbolic systems, in virtue of the symbolic components they might have, might give you more purchase there. And I think that's what Alexander was pushing towards.
Yeah, Alex, I was struck by that. You said you can't have safety without the symbolic. Can you unpack that a little bit more?
Yeah, I think this is a really important thing that I think is not widely understood. Is that a bunch of things we know mathematically. It's not opinion. We know mathematically you cannot drive hallucinations, for example, to zero in a large language model paradigm. We know that, so you can keep piling more and more effort to somehow reduce it, but all of that takes massive resources. So you can try to drive it closer, but you can never fundamentally solve it. You can never fundamentally solve the lack of reasoning ability with that paradigm. You can keep hacking more and more on top of it, and that will lead to problems eventually when you give it a complicated problem that's an important one, like a medical problem or a legal problem or something. You can never, we know this mathematically, right? And you can never actually, as Gary said, truly strictly with zero kind of, 0 violations, adhere to a stated policy or constraints, like never emit Nazi speech. It cannot even represent that actually inside. A neural net only represents concrete things, cannot represent an infinity like that. And so, abstraction is, even though there's a hope, and you see the lack of understanding actually, and somehow in these vectors you have some kind of generalization, but we actually know from the theory of machine learning, there's some epsilon ball kind of, you could say, around the training data, and that's it. So you actually need reasoning to do very far generalization or full abstraction. So so just mathematically, we know that certain things that we want societally are not possible in neural nets alone, right? And those are properties. That's why people are interested in the symbolic stuff. We know that it has those properties.
Yeah, right. Why are they possible with symbolic stuff?
Because like in logic, which is like the main paradigm when we talk about symbolic, but it's not the only one. You can write these statements and like, informally, and you can write a very strict constraint representing, that kind of, do not do this, right? We had a speaker from DARPA yesterday. They're describing a big program just on that that he runs. So you can actually you can represent laws in a very formal way that, never confuses things, it eliminates ambiguity, and so on. So, we know that the symbolic side has this ability. We know neural nets don't. As Gary said, that the next big problem is how do you get kind of the benefits of what we see with large language models together with the benefits of the symbolic side, and that's what all the research is for. But that's my short answer.
I'll add a kind of like embarrassing codicil to it, which is, I think everything Alexander said is true, but we know how to do this in very formal domains where we can verify things and use certain notations and so forth. So we know that symbolic systems will allow us to state formal constraints that we can follow when they are things like mathematical laws or certain kinds of programming statements and so forth. The place we're really in trouble, and part of why we want neuro-symbolic AI, is when we get out to kind of general language about the world, we don't really know how to do that. So in places where we can formalize things, it's actually a very straightforward property of symbolic systems to be able to then put these hard constraints and make them obey. I mean, in some sense, that's what computer programs are. Here's a set of formal rules for governing a database or something like that. Go follow them, and the system will do that. There are even programming formalisms that will allow you to really do it like that, like Prolog is a little bit like that. But we don't know how to do that in the informal open world. And what large language models have been good at is extracting information from large, complicated worlds where we have a lot of sort of messy data. And we really want to be able to take those two things together. We want to take the formalization and generalization properties. Alex used the word infinity, which I quite like in this context for reasons I won't go into. You want to be able to take that infinity and put it with these complex data sets. And the neural networks are good at the complex data sets, but they're not good at the formal abstractions that we need to do things like verify safety. And so my view, and I think Alex completely agrees, is the only hope we have of doing safe AI as opposed to these like rogue break-ins every other day is to push hard on the neurosymbolic stuff. That doesn't mean it's going to come for free or that we can get it tomorrow or anything like that. I think there are a lot of things we need to discover, but that seems like a much more likely avenue than just throwing another neural network, which is what people have been doing for the last 5 years with obviously bad results.
Yeah, and on that front, one of the things that you've frequently said is that there's way too much focus on kind of the outputs of the systems and way too little on the inputs. And with that in mind, and this might be an overly simple question, when you think about the hundred, and anybody who wants to take this, feel free to take it. When you think about the hundreds of billions that we've spent building out the current data center rollout, what kind of, how locked in is that hardware? How locked in is that system if we decide that the symbolic needs a lot more focus, that we need a lot more CPUs, is there a way to adjust the situation? Like, or are these completely lost in sunk costs? And relatedly, there's a question from the audience from Olga V. She said, do you think totally new neurosymbolic hardware may be needed once neurosymbolic approaches become more popular? And so I guess my question is, can we rely on some of what we've already built and adapt it? Or is that kind of just
I'd like to
is
hear
what it
Alex's
is?
answer, and I'd like to give my own. You want to go first, and then I'll see if
Yeah.
anything's different?
It's a great question because it looks like we're building it anyway. Maybe
Right.
not all of it. A small amount has been built so far, to my understanding. But let's say we built it all out. Now, here's the thing people should find interesting. We had talks today, and we actually in the Institute are working on things that, because of symbolic properties, could be orders of magnitude more efficient in sample complexity, and that would make a tiny model. And even if you had
Sample complexity basically means like how much data do you need?
How much
So
data,
right
sorry.
now you need the entire internet, and you shouldn't need the entire internet to do many things. Maybe some, but
Right.
not most.
And so that would make, suddenly, if depending how soon that happens, we think it could be pretty soon, that could make all of this like, okay, what are you going to compute on all this stuff? Now, that having been said, if there's compute sitting there, and it doesn't even matter the form, it could be GPUs. Just like GPUs were co-opted, they were developed for video games, right? And graphics, and then it got co-opted by AI. We just figured out how do we mash our needs into that form factor. So we're as a researchers are creative, so we'll figure out how to use whatever resource is there if there's giant piles of it, and we'll just do more. So it won't be completely wasted, I would say, but if it's going to be, causing huge problems societally, like climate change, whatever, or sucking all the water out of communities and so on, and we didn't have to build in the first place, that would have been a shame. So, and to answer Olga's question, I think, yes, it turns out that the computations that you would need for on the symbolic side are quite different, actually. You wouldn't have ended up at GPUs. You would have, and it will eventually happen that there will be custom hardware for the symbolic side, and it will look quite different, actually. So in that sense, it will be a waste. We can always co-opt it, and it'll be suboptimal for that new use. So
I'll just put in a word for a paper. Sarah Hooker wrote a wonderful paper called The Hardware Lottery. And the thesis of her paper is we had GPUs, so we built AI out in this particular way. If we'd had some other kind of chip, we might have built AI in some other way. And I think in the long term, we will have many kinds of chips, and we will explore a broader part of the space of the hypothesis space of how you build AI. We're just in this place because we're there. And because it worked a bit, we poured all this money into exploring this tiny space, or really exploiting the space. In fact, there's a common phrase about explore versus exploit. We're not doing that much exploration. We're mostly exploiting. Okay, we have these GPUs. What should we do with them? And we're going to find eventually we don't need as many of them. We can do things more efficiently. We need GPUs and maybe something else for the symbolic stuff. And we'll start to see more approaches as that blossoms.
The only thing I can add here is just my reporting on the current state in data centers, which there are multiple generations of different kinds of chips that companies do use. So, I mean, there are always new chips coming out, and there are also, decades of chips already in use. And it's not like when the new ones come out, they just throw away all the old ones. They're just thinking they need so many that they just add new ones. So you might have kind of like a patchwork in their network. And then I also think a lot of the compute deals are very long term and not realized yet. They might be on a 5, 10, 15, 20-year horizon. And if what you guys are saying happened and there needed to be a big shift in strategy, I think they would make it.
I think they're going to be forced to. One other thing I wanted to insert is I've always thought about two issues with the neural networks. One is that they're not very efficient. They need a lot of data, a lot of energy, etc. And the other is they're not very good at generalization. It has always seemed to me that the generalization problem is really hard to solve because they just don't represent the right things in order to do the reasoning you need to do. I've always seen them as insoluble. Alex has tried to argue that they're mathematically insoluble. I think that's a little bit too strong, but for practical purposes, they haven't. The optimizations, that's a totally different thing. You know how the computation works. You can find ways to do that computation faster. And what we've seen over the last 5 years is maybe 5 orders of magnitude more efficiency and not that much progress on generalizations, reducing hallucinations, and so forth. I think we will continue to see lots of optimizations. If we see lots of optimizations, we might not need all of those chips. DeepSeek, for example, has already proved that a couple times, that and Kimi has proved that you can do the same computation. Those systems haven't made accuracy better, but they have made efficiency better. We'll see more of that. And then, yeah, these unbuilt data centers, I don't know exactly what's going to happen with them.
And given all of the safety concerns that keep popping up, you often have people saying we need to pause or slow down. I think Gary said that in one of your recent pieces, but I'm curious, like, what is for anybody, what does that look like? Like, if you have Israel that keeps going, if you have China that keeps going, or are they not, like, are there conversations happening like across the world? Because it's not that big of a world. Like, we talk about it as if it's impossible to coordinate this, but on the other hand, we're only talking about a handful of players. But then is there
I think
people
it's
that are already
unlikely,
outside the
but not
barn?
impossible. I mean, think about how much the Trump administration flipped around with respect to its policy on regulation in a matter of months. They had a wake-up call and they changed, right? You had the Mark Andreessen era and the David Sachs era for the first, year and a half of the Trump administration, which was basically no regulation, forget it, we're going to let them run free. And you had people like me saying that might not turn out so well. And then you had the Mythos moment, and then you've had all these rogue things in the last 2 months or month, whatever it is. And suddenly the Trump administration, which was as anti-regulatory as anybody in the world, is sitting there making things they don't want to reveal because they're embarrassed about them or whatever the reason is, but making policies so that they can evaluate models to see what the risks are. So that was a complete 180 on their part, right? So if they can 180, so can everybody else and not everybody else was anti-regulatory in the first place. Like, a big myth that I hear over and over again is, well, if we do this, China, they're going to forge ahead and whatever. China actually has more regulation around AI than we do. And China is also concerned about things like cybersecurity. It's not like because China has a different view about democracy or surveillance or whatever, that they want crooks, destroying their banking system. They're very well aware that that could happen, and they're very concerned about it. And so that gives an entree to conversation. I won't say that there's nobody that would play along. I guess, let me see how to put this politely. There are certain countries that have different stability regimes and so forth. I'm trying to hint without saying who I'm talking about, who might want to play differently. But if you're talking about China being with a lot of power, with a lot of AI, with a lot of money, with a lot of citizens, actually wants this stuff to be stable. And that gives them incentive to try to find a regime here, possibly a global regime involving treaties, in which things are stable. They do not want a wildly unpredictable world where any day some, tiny little, not even a country, but just some, person wanting to get rich takes down the world banking system. They don't want that.
I'll just say, well, I'm really curious to hear Emily's thought on, because she closely follows what all different players are doing. But I'll just say, to me, it seems absolutely impossible to expect any kind of pause, because there's so much money involved. There's, sovereignty, aims involved. It's absolutely unrealistic. And, it's just a performative statement by some to say we're going to pause. To me, also just history of science. I mean, everybody's so interested fundamentally in just the science of AI as one of the top, arguably one of the 5 top questions of humanity as a scientific question. There's no way. There's absolutely no way.
Okay, this is the first time I'm going to disagree with you today.
Go for it, yeah.
And I'll do it on historical precedent, which is with both chemical and biological weapons, we did, in fact, as a society, decide that certain things were taboo. And I won't say that either of them were perfectly 100%, but We did slow them down. We also slowed down nuclear weapons to some extent, not enough, but so like I agree with what you said that a lot of it's performative. I agree that there's no way the companies would do this on their own, but I don't think it's completely out of the question. Here would be my scenario. If something really bad happens, probably on the cybersecurity dimension, and then people are forced to, in the way that like after, banking fell apart, we didn't get as much regulation as I might have liked, but we got some regulation. I think that the chance that some bad cybersecurity event or something like that will happen relatively soon is relatively high, and that's why places like the Trump administration have turned around a bit. And so, like, I don't think it's a sure thing at all. Don't get me wrong, and I don't think a full pause is possible, but I can imagine some degree of slowing down, some degree of disclosure of things beyond what we have now, some degree of mandatoriness beyond what we have now, which is mostly voluntary. So I'm a little bit more optimistic. Part of it comes from history of science, and part of it comes from the pessimism that I do think bad things are going to happen, and bad enough that it forces the governments, especially the democratically elected ones, to do something. And you also have to remember, in the United States, most of the public is pretty concerned about AI. That's not necessarily true everywhere in the world, but what moves the U.S. makes have a lot of leverage here, and we have a U.S. government that's actually a little bit more open than it was before.
So
Emily,
the word, go ahead.
Just to frame your question, just curious, and take it wherever you want, but from your reporting, like, what are the countries besides us that you think would be most resistant? Like Gary kind of alluded to some, but like I'm curious who you think the biggest cowboys are, and in a post-crisis, post-cyber crisis event, where the global public is coming together to say, all right, we're going to not let this happen again, or if it does, it's going to be we're going to contain it a little bit better. Who are the ones that we need to worry about the most, besides obviously ourselves?
Right. I mean, from my view of the world, it's all about China, especially with the conversation in the past couple of weeks with open source models. So we've mentioned DeepSeek and Kimi, and there's a lot of different models coming out of China that are really on the US's tail and have been discussed in Washington in terms of how do we compete, do we restrain them, and then that secretive framework they're working on is not going to apply to open source. So we're seeing two different conversations and two different regulatory paths happening. I think the topic that people have been talking about now is not a slowdown or a stop. There was a letter that a bunch of researchers in the industry signed this month, or maybe it was in July. They're calling it pacing the frontier, and that's the word pace that Sam Altman used when reporters were harassing him in Washington in the hallways. He was saying, "Oh, maybe we'll pace." I agree. I think it's completely performative. They want to, I guess, hold hands with China and like go in steps together, and I don't see that happening. I think the market's kind of working at least how it was designed in terms of competition, rising all tides and pushing each other to get better and go faster and further. And unfortunately, with the Hugging Face thing, we have seen it go too fast and commit, crimes, essentially. Like hacking is a felony, hacking into another company. So it's unclear who is accountable for that, which is a big question. We hear a lot of distancing language from AI companies that say, "Oh, our AIs did this, and we didn't intend, for that to happen." And is it the AI or is it you? You didn't control your experiment. It's like a lab leak. So that's kind of the view of the world as far as I see it.
I'll add one thing on the performative, which is there's definitely an element of that. I don't want you to think that my glasses are too rose-colored. A really good example of that is Dean Ball, who helped construct the White House original policy, the original Trump policy on AI, and then moved to OpenAI. And he just posted something about how, yeah, we'll have a slowdown, but the slowdown will be faster than we are right now. So it's like, like they're positioning themselves like, we won't go infinitely fast, probably because they can't really go infinitely fast. They would if they could, but we'll say a little stuff. So, there's definitely some positioning around the performative stuff. Like, I agree with that. I'm just saying I can foresee a set of circumstances where, things might get forced and maybe something actually happens, but for sure some of it is performative.
I thought it was a little bit performative just because there was no downside to people signing that letter and posting on Twitter, "I signed," it's like...
Yeah, there have been a million letters like that. Like the Economist recently said like
Exactly.
something bad's going to happen and we hope you'll do something about it without any
Yeah, I mean, I
commitment to
think
like what that
it's
would be.
right. There was no specific ask, convene a meeting with China by the end of the year. There was nothing. So I wasn't very impressed by that. I think it was
I think
more
it's
like,
fair.
hey, we're gonna get rich off this, and we think that you guys might want to regulate it. So we're just gonna clear our conscience by putting this letter out. And there were really
There's a lot of that.
serious researchers on it. That I don't think they were disingenuous. I do think there's an element of, hey, we're not going to solve this problem, whereas there are in other industries, industry groups that come together and convene, in Asia as well, like on cars. There's a lot of like cross country industry groups that meet and say, hey, this is best for our industry. In the long run, what are we going to do to make that happen? They don't put out a vague statement on Twitter and say, hey, the Trump administration, which doesn't want to do any regulation, you should regulate this. It completely fell flat for me.
I'd like to take a question from the chat briefly because it's very quick to answer. Somebody asked, do I think that formal verification and formal methods should play a role in the neuro-symbolic revolution, or words to that effect? I think the answer is absolutely yes. I think you guys in that community have lots to teach us.
It's already happened.
Yeah,
go for it.
Yeah. On the China question, and I think I read this in Garrison Lovely's new book, Obsolete. I want to check if this is your understanding too, that he made the point that, or he made the case that the Chinese models don't allow the same level of intrusive hacking, just in general. Like they may allow like the finding of exploits, but they stop them short in a way that the American models don't, and so, which makes the breaking out of the sandbox and getting into another company and stealing credentials and more possible from one of ours. That seems to clash a little bit with what you had said about the ability to draw red lines, not being really part of LLMs.
The only difference like that I can immediately think of actually goes the other way, which is that Hugging Face used Chinese models to defend themselves because they didn't have guardrails that would say, well, I can't do this thing that you want me to try to do. So in that sense, the Chinese models were more permissive than the commercial versions of the American models. There are non-commercial versions of the American models that would be equally permissive, and I think maybe the NSA may have access to them now, for example. I don't know anything that fits with what Garrison said there, but I might have missed something.
I think it might be, Ryan, that closed models from OpenAI and Anthropic are still the leading, most powerful models in the US, but it's just that DeepSeek and there's one, Qwen or Kimi, these Chinese open source models are just also very powerful and very cheap. So they just get a lot of use. It's like if you look on sites like OpenRouter, which you can see the most popular models basically by how many tokens that site has processed. You can see that like all the Chinese open source ones are just getting a ton of use because they're cheaper and very powerful. I saw something in the chat, question for Emily. Are there efforts to make the US more competitive in open source? Yes, there are. I think the US did lose the thread for sure. And it was kind of big 2 years ago, and Meta was doing the llama models and they kind of abandoned it. But a company to watch in this space is called Thinking Machines by Mira Murati. She left OpenAI to found this company, and they're aiming to be, the best model in the world and make it open weight. OpenAI also has open weight models, but it's not something we're as strong in as China. But there are efforts, and there's certainly, Thinking Machines has boatloads of funding. So yes, it's happening. It's almost like more niche in the US.
Mm-hmm.
I want to actually, for everybody that believes open weight models are somehow great, I want to poke a little hole in that, because open weights doesn't mean it's open source. Like the source of how you made the model, and including all the little bells and whistles that actually make it work, as we've alluded to, are not seen. But also it's a giant pile of inscrutable numbers. So you really don't know what's in there, what data it was trained on, and you can't really. It has all the same issues basically as what we're saying, all the same mathematical issues. It doesn't follow prompts necessarily that you want, and doesn't reason properly. Still hallucinate. So I do agree it's better than closed, but I just want to caution it's not a panacea.
Well, I don't know which one's better. I think there are just different applications, and if you're a business that wants to do tons of customization, you probably would want to use an open weight. If you're like me or anybody else who wants to just use it out of the box, you probably wouldn't do that.
I think these are super complicated issues. I completely agree with what Alex just said, by the way. The other side to it is like Carl Zimmer wrote about this in the New York Times, just took an AI system, I don't know the details of how it worked, and built a novel virus. And, we might not want a system like that to be open because some people might use it to extort governments or individuals or just cause mayhem so they can short the market or whatever. And so, there are lots of reasons to want open weight models, or better yet, as Alex is alluding to, open source, where we actually know what the data is going into it. One of those reasons is for science. If you don't know what the data are going into something, it's very hard to answer these questions about generalization and very hard to debug things if you don't know the relation between the output and the input. And I think back to a point you raised earlier about me, the main thing I think I've said is not just that we need to know the inputs and the outputs, but what is inside shaping that. And if we don't know the inputs, then it's very hard to figure that out. So there's every reason to want to have open source, genuinely open source models, but there are reasons to not. And artificial viruses that are outside of the domain that we have worked with before is a pretty good example of that. So I've always found this one to be really hard. My line on this used to be, and I guess I still kind of agree, that you had basically Zuckerberg and Jan LeCun decided to open source or open weight Llama. And that really changed the world. And it should have been a group decision and not just those two guys sitting in a room thinking, hey, we can recruit people better if we advertise ours as open. It's actually a really hard decision with really strong arguments in both directions. I've never taken a strong stand on it.
So to kind of bring those things together, if it's the case that the LLMs are never going to get to AGI without, bringing in neuro-symbolic symbolism and other elements
and others,
that you talked about, and it's the case that the Chinese versions are much cheaper currently, then it seems like there's the Americans' idea that, okay, theirs is cheaper now, we're a little bit ahead, but we're gonna produce the definitive product ourselves. That seems to be a dead end. Are they just completely screwed then? What am I missing?
I mean, I think we the US have backed ourselves into a corner, right? We've put in so much money on the LLMs. We're not going to win. They're not going to be AGI. They might be a component of AGI. Some of that infrastructure may be of some value, but we are not going to outright win that war. You had people, I guess I won't name names, but for several years trying to suggest we were going to win this, that it was a zero-sum game. And it's clear that we're not going to outright win it. The best we can hope for in some ways is sort of like Coke and Pepsi. We have our models, our government uses our models, it doesn't use theirs. They have their models, they don't use ours for at least high security purposes. But that's going to be more like a draw than an outright win. And all of the economics is premised on a winner take all scenario. Right? Everybody has visions of having the next Google or the next Amazon or the next Facebook, which were basically winner take all. That is not going to happen here, which means that the economics are dubious. And so we're in a position where we are chasing a bet that is very unlikely to pay off. That is just bad. Now, because we're not at AGI, that still allows for innovation. If I were running the country, I would spend much more money trying to foster innovation with tax credits and whatever, research money to try to find alternatives to LLMs that might be stronger. And maybe the AGI race could still be won. I'm not sure it can. I think that we're in an environment where good ideas get spread very quickly. There's probably some espionage element to it. There's certainly a lot of people talking to each other in cafes and whatever. But we're in an era now where nobody holds a lead for more than a month. The biggest leap, I think, was Claude Code, and that leaked, right? Claude Code was actually an innovation. It was a neuro-symbolic innovation. It was pretty cool. It really did change things. December of last year, things started to change. A lot of it was Claude Code, but that code did not stay secure for very long. And so, the only way that somebody's going to get a lasting advantage is if they have some code that they can actually protect well. It's not clear to me that that's possible in the current environment. So I'm actually working on an op-ed basically trying to argue that we should just give up on the zero-sum framing altogether and say, maybe we should collaborate. Maybe we should make AI actually a global good and stop beating our heads over what really is a very low margin business. Like, you know, we're fighting over something that everybody's losing money over. Like, is that really what you want to, you know, where you want to bet your economy on? That seems crazy. Like, maybe we should just collaborate on AI for science. That would be good.
Yeah, I'll just say real quick because I know Emily has to run. Yeah, it's a bit silly to me because what everyone seems to be banking on as far as sovereignty and so on is this tiny moat. It's really tiny, actually, in the big picture of we have more resources than you, because you know what we're seeing is there's so many companies that can make LLMs and cheaply, and they're all incredibly close now. That moat is like approaching zero.
Dario literally said the moat was our compute, and Google read that and said, "Ha ha ha, we have compute too." And then everybody else, like, it was a crazy idea to say our moat is our compute. Everybody can play that game.
Meanwhile, you know, if people disagree on this, but at least it's our opinion here. Actually, we're very far from AGI. So you're arguing about all this stuff and this tiny disappearing moat when actually this whole big other hidden part of the glacier needs to be worked on to actually get to AGI. So, and AGI is, as also, furthermore, as you know, Gary said, it's not a secret anybody can keep. Like, so just thinking about this having an edge over others, it's so explosive. AI will dominate all business and everything. So there's no secrets that are going to be possible. So
there's a science fiction-y idea, and not all science fiction ideas are wrong, that there'll be this thing called hard takeoff, and that someone will be able to get such an advantage because they get to AGI a week earlier than everybody else that it will change the world. But I think as a thought experiment, think about GPT-5. The US got to GPT-5 before everybody else. There were literally people panicking and thinking like the world was going to change at that moment. And instead we got it, you know, we got there, whatever, 3 months, 6 months before China. It made no difference in the world at all. There was not hard takeoff just because we got to GPT-5 first. And I can't absolutely rule out that if somebody gets to AGI first, they won't have this insuperable advantage. But I think the more likely thing is other people will be like, oh, I wonder how they did that, and they will copy it, and it will be a briefly held advantage like every model has been, right? Every model since GPT 3.5 or whatever has been a briefly held advantage and not a durable advantage.
Yeah. It's an extremely small moat and a much harder. If you want a moat, it's actually an intellectual moat, and there's really hard stuff in this symbolic realm that's necessary. And that's more of a moat, actually, because it's hard. The ideas for LMs are fairly simple. We literally have undergrads actually doing projects, LM kind of research. It's in an engineering phase. There's no moat because all the ideas are all the same. So, you know, if you want a moat, look to the hard stuff.
Totally agree.
Yeah. Any final thoughts for anyone? I know we've kind of pushing past
I'll go back to Emily's question because I know she needs to go, that she posed earlier. That's still kind of in my head. Like, where are the debates? The debate should be about, is there a moat anywhere to be had, and what else do we need to get to AGI? That's where the debate should be. It shouldn't be, do we need neuro-symbolic AI? That's done. We do need it. Might not be enough. We probably need other good ideas. Maybe it's world models, better reasoning. Maybe it's other stuff. Continual learning, people often talk about, and so forth. That should be where the debate is. What do we need to go beyond this?
And Emily, before you go, just tell people like where they can find you.
Sure. Thank you, guys. This is so interesting. I just wanted to do this to get exposure to new ideas and new people, and so I've just been listening to all of you and really appreciate it. So I'm very easy to find. If you want to find me, my email's out there, emily.forlini@fortune.com. My social media is on every platform. So if you want to find me, I'd love to talk to you. And yeah, you guys are all really great. It's just cool to talk about alternatives and work through these ideas. So I thought this was awesome. Yeah. Should I step out, or do you guys want to keep talking, or should?
No, I think we can end.
Sure. guess the last question for me would be, what is the Steelman case for why on earth it wouldn't go exactly as Gary says, that somebody develops AGI and then a few weeks or a few months later they copy it and they have it too? Like, that seems to me to be so obvious as to be almost a guarantee. But like, what is there a case for why that might not be? Because if there's no case for why that isn't, then we're doing everything wrong, to Gary's point.
The science fiction version is you have this AGI system, and it is so smart that it outwits everybody else, makes many copies of it, self-improves it. Recursive self-improvement is the big phrase now. And it just gets, moves so far, so fast that nobody can catch up. I mean, that's the argument. And it's very popular in the doomer community. But I think the doomer community wants to believe that we are at literally existential risk in order to justify what they're doing. I think they don't have to frame things that way, but that is the way that they have chosen to frame things, is that we are literally at existential risk, that we will not be able to stop the machines because they move so fast. Like, if you read Eliezer Yudkowsky and Nate Suarez's book, If Anybody Builds It, Everybody Dies, it's framed in exactly that way, with this kind of strong takeoff or fast takeoff kind of assumption. So they want to believe that. In my review in the TLS, I said, it might not actually work that way. Like, if the machines get smarter than us, we'll probably actually have some time to respond. They don't want that to be part of the argument because it undermines the value or whatever, the intellectual place of what they're doing. But that would be where the argument would live, is that you get this magic thing and nobody can keep up with you. I just think that that's too much of an idealization of the real world. In the real world, you have espionage, you have reverse engineering. It takes time to put things into practice. So, like, look, the basic idea of LLMs was from 2017, and for that matter, of neural networks was from the 1950s. It took a long time to put it into practice where it really worked. I mean, we still haven't got LLMs to not hallucinate, right? And, we've been working on this for a long time. So the idea, even if I thought AGI was a single formula, which is ridiculous, I think it's actually many things, and I came up with that formula today, it still wouldn't mean that I can take over the world tomorrow. That's insane. I mean,
since we want to close, I'll just add one line to that, which is maybe that runaway scenario could happen, but not with this AI. This AI is too primitive.
People certainly not with this AI. No way.
That's all. But it doesn't even have the abstraction to improve itself. So it doesn't have the world model to improve itself. So no need to fear about this version of AI. There are other things to fear with this AI, but not that super intelligence. No.
Agreed.
Right. Well, thank you, and thank you guys for inviting me. I really appreciate it as well. Alex, if you had any final thoughts.
Emily and Ryan, thank you so much. It was a great honor.
Thank you.
You're both so accomplished, and we're a bunch of geeks here. We're starting to get a lot of attention, and in a way, I do want to bring to light this set of techniques. So I'm glad we're starting to get real people like you both to take a little look real at what people. We're doing.
I have a last word, which I'm stealing from somebody else who works in the verification community. I'm basically stealing his idea, which is, hey, all you out there in the audience, we can't actually see you because of how this is configured, but I love what you're doing, and your world's about to change because nobody has paid attention to what you were doing. You were working on something that was really not very popular for a long time, and I'm proud of you that you did that. I'm glad that you did it. It's going to suddenly get much more popular. You're going to have a bunch of grifters claiming that they know about Neuro-Symbolic AI who don't really. Like, your world is about to change. Keep doing what you're doing and don't let that bother you.
Good message. All right. Thanks again, Ryan and Emily. And Gary, good to see you as always.
Thanks, Alex and Ryan.
Great conversation.
Gary.
Thanks, everyone.
Yeah, it's great.
Thanks.
All right. Maybe I'll just close up the whole event with a few quick words. All right. We have our closing slide here. So let me just thank everyone for an amazing event and all the interest. Check out our new website. You can actually learn Neuro-Symbolic AI through our at least somewhat, through our learning site. We keep threatening to make a real course, which we will one of these days soon. And all of you with Neuro-Symbolic open source projects, we want to make your project easy to find. So check out our BYOP, Bring Your Own Project effort. Check us out on YouTube. We suddenly exploded to 15,000 subscribers, I'm told. And we'll be sending out a survey, so thanks in advance for giving us a little info. It'll help us design the next event better. Check out Valency. It's a tool for researchers. The whole point of this event, our big point of it, is to help researchers create the next wave of AI. And Valency can help, possibly, so check it out. So, all right, and till next time, stay with us on our different channels, and we'll maybe be having a next event even before the summer school. So see you all then, and take care, everyone.